Good evening, everyone, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, people, let me know in the chats quickly if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats with some fire emojis if every one of you can hear me out, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats. Everyone, people, everyone. Yeah, I think I am perfectly audible and visible to everyone. That's great. All clear? Yeah, all clear? Perfect, guys. Perfect. So, today we are going to kickstart this particular week as well, and this is going to be the first session of this particular week, right? I hope all of you are like ready to kill 5 chapters in this particular week. The first one, which I'm starting today, that is going to be the epic redox reaction. Yeah? Perfect, guys. So, my dear students, let me first of all give you the overview of the things. Like, what exactly are we going to discuss today? Let me tell you, today we are going to do one of the important chapters of your physical chemistry, that is redox reactions, right? And let me tell you, without this particular chapter, you cannot efficiently do electrochemistry. Yeah, you cannot efficiently do electrochemistry. So, this particular chapter, it forms the basis of the electrochemistry chapter as well. So, let's try to start this particular chapter from the basics, from the scratch, from zero itself. Slowly we'll scale up the things, right? And we'll cover each and every concept of this particular chapter in detail, right? Whether you have studied this chapter before or not does not matter. I'll be exactly starting from the basics, from the scratch, right? So if you all are ready to be with me till the end, let me know in the chats. Let me know in the chats if you all are ready to be with me till the end. If you all are ready to be with me till the end, let me know once in the chats quickly with the fire emojis, yeah? And this particular chapter will almost take some, I would say, some 8 to 9 hours to complete, okay? Some 8 to 9 hours this particular chapter is going to take to complete. I've added a lot of new questions as well in this particular chapter, right? Which maybe you would not have solved till now, right? But in this particular session, every single theoretical point, every single problem pattern, whatever things can be asked from the chapter redox, every single thing I'll be discussing in detail. Yeah? And I can see a lot of fire in the chats. That's amazing. That's great. And I would want this fire till the end, right? The Josh has to be till the end. So, let me first of all give you the overview of the things, the sequence of the topics which we are going to start with in the today's session. My dear students, we shall be starting with the first and the basic topic. You know that already. That is your oxidation state. Number 1. Oxidation state. The first topic. The second topic that we are going to cover here, that's going to be rules to calculate the oxidation state. Rules to calculate oxidation state. Some important structures. Some important structures, almost around 15 to 20 structures of different compounds we shall be discussing. After doing the structures, I shall be giving you the idea about what oxidation and reduction is all about. Oxidation reduction. Then we shall be discussing about oxidizing agents, reducing agents, and their applications. Once we are done with that, we shall be discussing about the term equivalent mass. Well, after doing the equivalent mass, in the equivalent mass, I must say, we shall be doing the N factor calculation in detail. N factor calculations. We shall be discussing some of the very, very, very important reactions of two important compounds. One is your KMnO4 and another one is your K2Cr2O7. Some very, very, very important reactions of these. Well, after that, we shall be moving into the balancing of redox reactions. Once we are done with the balancing, we shall be discussing about the concept of equivalence. And after concept of equivalence, we shall be discussing about normality, right, in detail. After doing the normality, we shall be discussing about law of chemical equivalence. Law of chemical equivalence. Later on, we shall be doing about the redox titration. Once we are done with the redox titration, we shall be discussing about the acid-base titration. And after finishing acid-base titration, we shall be discussing about the volume strength of H2O2. And my dear students, lastly, we shall be discussing about the types of redox reactions. With this, the chapter will be done and dusted. Okay? With this, the chapter will be done and dusted. Did you get the flow of the today's session, people? Yeah? Did you get the flow of the today's session? Well, mostly the types of redox reaction. This is a complete theoretical topic. Mostly I'll be giving you the PDF of this particular topic. Because this is all theoretical, you just have to remember certain definitions. Anyways, if we got time, I'll be teaching this as well. Otherwise, I'll be sharing the PDF of this particular topic, which is just the definitions of the redox reactions, right? That is something which I'll be sharing in my Telegram. And once we are done with the session, I shall be giving you the PDF, the handwritten PDF of this session, as well as the DPP of this particular chapter on my Telegram. And I hope you all are already the part of the Telegram. If not, then be the part of my Telegram quickly. That is Wassim Bhat Chemistry Official. That is the name of the Telegram channel, wherein I keep on sharing the handwritten session PDFs as well as the DPPs after end of every single chapter. So, are you all ready for the session? Well, this is the flow. This is the session flow which I gave you. Are you all ready? Let me know quickly in the chats. Till then, I'll have some water here. Yeah? Perfect, people. Perfect. All right, just give me a second and we shall be starting. Yeah? Okay. PYQs, everything is included in the today's session. PYQs, whatever concepts can be asked, whatever questions can be asked, everything I've included in the chapter. Don't worry. One thing I'll guarantee you, at the end of the session, you should be in a position to solve all the questions of the redox. Whatever material you have, right? Whatever study material you have, whatever booklets you have, right? You should be in a position to solve each and every type of question from your material, from your booklets, from the DPP, which I shall be sharing with all of you. Okay? That's my promise. But, you have to be with me till the end. You have to be with me till the end. And the ones who have not liked the session yet, I would highly recommend you guys to smash the like, right? Mark your attendance so that this session reaches to majority of the students, right? Whosoever is preparing for NEET 2025 or even 2026. And at the same time, do share this particular video with every single guy as well. Yeah? Perfect. So my dear students, let's get going then. Let's get started with the first topic, which I'm going to write on the screen. What is the name of the topic? It is going to be the oxidation state. Oxidation state. This is the first topic which we shall be covering in the today's session. The basic, the fundamental of this particular chapter. Oxidation state. So my dear students, there are few points which I'm going to write on the screen first of all. There are few important points which I would want to write on the screen first of all related to the topic oxidation state. I want you guys to take a note of those points and I'll be explaining them in some time, right? The first thing, how do we define the term oxidation state? Let me tell you, oxidation state is defined as the charge present on an atom of an element in a given compound. In a given compound. The charge present on an atom of an element in a given compound is what we call as oxidation state. I'll tell you its meaning in some time. Before that, I want to write few points here. Oxidation state, it is defined as the charge present on an atom of an element in a given compound. Let me tell you, the charge can be real or virtual. The charge can be real or virtual. In case of ionic compounds, I would say the charge is real. And in case of covalent compounds, the charge is virtual. The charge is virtual. One more point which you are going to add in your notes. What is that? Real charges arise. Real charges arise due to the complete loss or gain of electrons. Virtual charges arise due to the electronegativity difference between two atoms. One more point at the end, please note this. Oxidation state is defined. Oxidation state is defined for one atom of an element. Oxidation state is defined for one atom of an element. Now, my dear students, let's get to know about all these points. Whatever I mentioned here, let's get to know about them one on one. Yeah? I'm sorry. Did you take a note of all this stuff? Yeah? Did you take a note of all this stuff? I believe yes. I believe yes. Now let's try to understand all these points related to oxidation state one by one. Okay? One by one I shall be discussing all these points. My dear students, I'm starting with ionic compounds over here. I'm starting with the ionic compound. If I ask you, what is the most common example? What is the most typical example of the ionic compound? You will be telling me the most typical example of the ionic compound is nothing but NaCl. Right? This is going to be your answer. The most typical example of the ionic compound is nothing but NaCl. Yeah? Now, my dear students, if you look carefully, in case of NaCl, how many elements do we have? We have got two elements in NaCl. One is sodium, another one is chlorine. These are the two elements present in NaCl. If I ask you, do you see any charge present on sodium here? You'll say no. Do you see any charge present on chlorine here? Your answer must be no. As I cannot see any charge on sodium here. I cannot see any charge on chlorine here. But when you exactly see the formation of NaCl, when you see how NaCl gets formed, then you will be in a position to check the charge on sodium and the charge on chlorine. What does that mean? Have a look. My dear students, if I talk about sodium, you know, sodium is metallic in nature. Sodium is a metal basically. Chlorine is non-metallic in nature. Chlorine is a non-metal. Sodium is a metal, chlorine is a non-metal. You must be knowing this. And one more thing you must be knowing, metals have got high tendency to lose electrons. And non-metals have got high tendency to gain electrons. One thing is clear. So sodium here would be having the tendency to lose electrons. Chlorine here would be having the tendency to gain electrons. Now people, if you understand properly, then sodium, it belongs to group first. It's a group first element. If sodium is the group first element, I would say it will have one electron in its outermost shell. This sodium, it will be having one electron in its outermost shell. Now, is it easy for sodium to lose that one outermost electron? Or is it easy for sodium to gain 7 more electrons? I would say it is easy for sodium to lose 1 electron. And when sodium loses an electron, it gets converted into what? It gets converted into Na positive. So sodium got converted into Na positive. It lost 1 electron, right? Similarly, if you talk about chlorine, chlorine belongs to group 17. And you know people, if chlorine belongs to group 17, all the group 17 elements have got 7 electrons in their outermost shell. All the group 17 elements, they have got 7 electrons in their outermost shell. Now, is it easy for chlorine to gain 1 electron? Or is it easy for chlorine to lose 7 electrons? I would say it is easy for chlorine to gain 1 electron. And you know, when chlorine gains 1 electron, it gets converted into what? It gets converted into Cl negative. So I would say one thing clearly over here. I would say sodium has lost 1 electron completely and chlorine has gained that 1 electron completely. Sodium has lost 1 electron completely. Chlorine has gained 1 electron completely, right? Due to which sodium got converted into its cation and chlorine got converted into its anion. So my dear students, since we saw sodium got converted into its cationic form and chlorine got converted into its anionic form. Now, if sodium got converted into cationic form, chlorine into anionic form, can I say these are oppositely charged ions here? These are the oppositely charged species here. And you know, between the oppositely charged species, what kind of attraction will be there? I would say between these oppositely charged species, there must be electrostatic force of attraction. There must be electrostatic force of attraction between these ions over here. And my dear students, this electrostatic force of attraction, which holds these ions together, what do we call it as? We call this force of attraction as the ionic bond. We call this force of attraction as the ionic bond, number 1. Number 2, people, since there is complete loss and gain of electrons taking place, there is complete loss and gain of electrons taking place. And remember, the bond which is formed due to complete loss and gain of electrons, the bond which is formed due to complete loss and gain of electrons, either you'll be calling that as ionic bond, or you will be calling that as the electrovalent bond. you'll be calling that bond as the electrovalent bond. And any such compound which contains ionic bond or electrovalent bond, what do you call that particular compound? You call that particular compound as the ionic compound. Right? This is something which is very basics, which I'm telling you right now. Yeah? So will you do titrations today? Yes, I'll be doing titrations as well. I'll be doing titration. I'll be doing redox titrations as well as acid-base titration. Yeah? Now, my dear students, if I ask you one simple question over here. Now, if I ask you, do you see any charge present on this sodium atom? Or do you see any charge present on this chlorine atom? The answer now is going to be yes. Yes, we do see certain charges present on sodium atom and chlorine atom, right? If I ask you, what is the charge which you see on one atom of sodium? The answer is going to be +1. What is the charge do you see on one atom of chlorine? -1. The charge on one atom of sodium is +1. The charge on one atom of chlorine is -1. And my dear students, look at the first statement. The charge present on an atom of an element. The charge present on an atom of an element, right? What do we call that as? Oxidation state. So this is the charge present on one atom of sodium. So this +1, I'll be calling as oxidation state of sodium. This is the charge present on one atom of chlorine. So I'll be calling this as the oxidation state of chlorine, right? So what is oxidation state in general? Oxidation state is nothing but the charge present on one atom of an element. Yeah? The charge present on one atom of an element. I believe this is clear to everyone. And at the same time, my dear students, as I told you already, these charges can be real or virtual. These charges on the atoms, they can be real or virtual. So first of all, let me tell you, real charges arise on the atoms due to complete loss and gain of electrons. Do you see here? Complete loss and gain of electrons has taken place. And due to complete loss and gain of electrons, which charges arise on the atoms? I'll say real charges arise on the atoms. Perfect. So this +1, this -1, these are basically the real charges here. These are basically the real charges here. These are basically the real charges here. So one thing which you need to know here, real charges arise on the atoms due to complete loss and gain of electrons. As you saw in case of what? As you saw in case of ionic compounds, right? In case of ionic compounds, there is complete loss and gain of electrons happening, right? So the charges present on the atoms in case of ionic compounds will be the real charges. Will be the real charges. I believe this is clear to everyone. Okay? So I hope this particular statement is clear. The charge present on an atom of an element in a compound is what you call as oxidation state. This charge can be real or virtual. This is clear. In case of ionic compounds, the charge is real. Real charges arise due to complete loss and gain of electrons. Now, what about the virtual charges? What about the virtual charges? Let's get to know about this in detail. So, in case of ionic compounds, the charges are real. And real charges arise due to complete loss and gain of electrons. Now, my dear students, let's talk about the covalent compounds. Let's talk about the covalent compounds. Let's talk about the covalent compounds. Let's understand what is the meaning of this oxidation state in case of covalent compounds. Just a second, guys. I think there's a guy spamming. Who is this call mind the beast nonsense? Wait, let me block these people. I don't appreciate all this stuff here. Blocked. Calm mind is going to get frustrated now. Yes, you are blocked too. Some more people have come for the spamming and stuff because they don't want to study. So you're blocked too. There is some venom as well. Let me take out your venom. You're blocked too. Yeah, perfect. All clear, people? All clear till here? All clear till here? Till these spammers, they won't be able to comment again here, yeah, in the chats. Yeah. So before coming to my session, learn the rules first. Yeah. I don't have to call somebody to block you. I've got all the access here. I hope I'm clear with this. Now, people, let's talk about the covalent compounds in detail. Yeah. Let's talk about the covalent compounds in detail. So, first of all, what is a covalent compound? In chemical bonding, we have discussed the covalent compounds in detail. What is the basic thing about covalent compounds? My dear students, you know, in case of covalent compounds, what happens? There will be mutual sharing of electrons, right? There will be mutual sharing of electrons when you talk about the covalent compounds. Yeah. For example, let's assume that there is a single covalent bond between A and B. Let's assume that there is a single covalent bond between A and B, right? And you must be knowing how this covalent bond gets formed. I would say single covalent bond is formed when A as well as B will be contributing 1 electron each. So I would say A as well as B here, I would say A as well as B, both would have contributed 1 electron each. Both have contributed 1 electron each. Now this electron pair, right? Now this electron pair, there will be mutual sharing of this electron pair between A and B. This electron pair which will be mutually shared between A and B in case of the covalent bond. You know it already. Now, my dear students, I'm assuming one simple thing here. Let me assume that electronegativity of B is greater than that of electronegativity of A. For example, electronegativity of B is greater than that of electronegativity of A. Now you tell me, if electronegativity of B is greater than that of electronegativity of A, what does that mean? That means this B has got more tendency. This B has got more tendency to attract this bonded pair of electron towards itself. Now, if B has got more tendency to attract the bonded pair of electron towards itself, so I would say this electron pair will be closer towards B. And if the electron pair is closer towards B, I would say towards B, the electron density has increased. Yeah. And that increase in the electron density towards B is represented by delta negative. Similarly, decrease in the electron density is represented with delta positive. Decrease in the electron density is represented with delta positive. Perfect. Now, people, do you see any complete loss and gain of electrons taking place here? I would say no. There is no complete loss and gain of electrons taking place. I would say, what is happening? Shifting of electron pair is happening. And due to the shifting of electron pair, which charges will arise on the atoms? They are going to be the virtual charges. So these are not the real charges here. These are not the actual charges here. These are the virtual charges on the atoms, which came due to what? Which came due to the electronegativity difference between these two atoms, which came due to the shifting of electron pair between these two atoms. I believe this is clear to everyone. So, if I ask you, what is the oxidation state of A over here? You'll directly say oxidation state of A is +1. Oxidation state of B here is -1. But does this +1 mean that A has lost 1 electron completely? No. Does this -1 mean that B has gained 1 electron completely? No. Since these are the virtual charges, this -1 is simply going to tell you that the electron pair, which was supposed to be at the center, now that electron pair is not going to be at the center. The electron pair would have shifted towards more electronegative element B. Yeah? All clear? Point number 1. Point number 2. Point number 2. My dear students, let's assume that there is a double bond between A and B. If there is a double bond between A and B, so there would be 2 electron pairs over here. There will be 2 electron pairs over here, which are supposed to be mutually shared between A and B. So since there is a double bond between A and B, so I would say these 2 electron pairs, they would be mutually shared between A and B. Now, my dear students, I'm assuming one thing. What is that one thing? I'm assuming again electronegativity of B is greater than that of electronegativity of A. Yeah? Now you tell me, if B is more electronegative than A, That means B has got more tendency to attract both these electron pairs towards itself. If B has got more tendency to attract both these electron pairs towards itself, I would say the charge on B here will be minus 2 delta. The charge on A here will be plus 2 delta. Right? Now, if I ask you, what is the oxidation state of A here? You should say plus 2. What is the oxidation state of B here? You should say minus 2. Now, does it mean this A has lost 2 electrons completely? No. Does it mean B has gained 2 electrons completely? No. It simply means both these electron pairs, they are shifted towards what? They are shifted towards B. Yeah? Perfect. Sir, one doubt about the coordinate bond. Coordinate bond will be, I'll be dealing with the coordinate bond separately in some time. Just wait. There's the basics. Follow me. Step on step, we'll scale up the things. Okay, coordinate bond, I'll take separately when I teach you the rules. Perfect. Now, my dear students, imagine that between A and B, there is a triple bond. That means there will be 3 electron pairs over here, which will be mutually shared by A and B. Now, I'm assuming one more thing again. What is that thing? I'm assuming electronegativity of B greater than that of electronegativity of A. So, if B is more electronegative than A, that means B will be attracting all the 3 electron pairs towards itself, due to which B gets minus 3 delta, A gets plus 3 delta. So I would say oxidation state of A over here is plus 3, oxidation state of B over here is minus 3. Now my question to you, does it mean A has lost 3 electrons completely? No way. Does it mean B has gained 3 electrons completely? No way. It simply means that these 3 electron pairs, they have shifted towards B, right? Due to which B got the oxidation state of minus 3. So tell me, all these charges over here, are these the real charges or virtual charges? Let me know quickly in the chats. Everybody. Let me know quickly in the chats, everybody. Everyone in the chats. Quick, people. Are these real charges or virtual charges? This is something I would want to know from you. Quickly, everybody. Yeah? Absolutely wonderful, guys. Absolutely. Absolutely. So I believe all the stuff is super clear to everyone. I believe all the stuff is super clear to everyone. Yeah? Yes, JEE students can also watch this. No issues at all. Perfect. Now, my dear students, there are a few more things which you must be doing, or if you do not know, remember from now onwards. You know, in your periodic table, I must say fluorine is considered to be maximum electronegative, followed by oxygen, followed by nitrogen. This is something which I believe all of you would be knowing already. In your periodic table, fluorine is considered to be maximum electronegative, followed by oxygen, followed by nitrogen. Point number 1. Point number 2. You must be knowing about one more thing. On moving from left to right in the periodic table, I would say electronegativity generally increases. On moving from left to right in the periodic table, I must say electronegativity generally increases. Similarly, my dear students, on moving from top to the bottom, in the periodic table, I would say electronegativity generally decreases. This is something which I believe every one of you would be knowing. Yeah? So if you know this stuff, let's talk about this oxidation state a bit more in detail. Understand? For example, I'm taking a compound, let's say, I'm taking HCl into consideration. Let's say I've got a compound HCl, right? Now, there is a single bond between hydrogen and chlorine, correct? If I ask you between hydrogen and chlorine, which one is more electronegative? The answer has to be chlorine. Chlorine is more electronegative. If chlorine is more electronegative, I must say chlorine has got more tendency to attract the bonded pair towards itself. Due to which chlorine gets delta negative, hydrogen gets delta positive. So I would say the oxidation state of hydrogen here is +1. The oxidation state of chlorine here is -1. Correct? As simple as that. Let's say I'm talking about water. I believe all of you would be knowing about the structure of water, right? Which we discussed recently in chemical bonding as well. Perfect. Now, my dear students, in water, how many OH bonds do you see? You can see 2 OH bonds here. So, if you consider this particular bond between oxygen and hydrogen, and if I ask you which one is more electronegative, oxygen or hydrogen, answer has to be oxygen. I would say oxygen here is more electronegative. So this bonded pair is shifted towards oxygen, due to which oxygen gets delta negative, hydrogen gets delta positive. If you talk about this particular bond between oxygen and hydrogen, again, which one is more electronegative? Oxygen. So bond pair will be shifted towards oxygen, due to which oxygen gets delta negative, hydrogen gets delta positive, right? Now, my question to you, what is the charge which you see on hydrogen? +1. Charge present on this particular hydrogen, I would say +1. Charge present on this particular oxygen, you will say -2. And you know, the charge present on one atom of an element is what we call as oxidation state. Yeah? The charge present on one atom of an element is what we call as oxidation state. Similarly, people, let me take one more example so that it becomes properly clear to you. Let's talk about NH3. And in case of NH3, if I talk about this specific bond, this is the bond which I'm talking about here, between nitrogen and hydrogen, which one is more electronegative? Nitrogen. So I must say this bond pair is shifted towards nitrogen, due to which nitrogen gets delta negative, delta positive. Again, delta negative, delta positive. Again, delta negative, delta positive. So if I ask you what is the charge on this particular hydrogen here, you'll say it's +1. Charge on this particular hydrogen here, +1. Charge on this hydrogen here, +1. Charge on this nitrogen here, it's going to be -3, right? And the charge present on one atom of an element is what we call as oxidation state. So people, if I summarize this stuff, let me write HCl in compact form. Let me write water in compact form. Let me write NH3 in compact form. If I ask you, what is the oxidation state of hydrogen here? What does that mean? That means I'm asking you, what is the charge present on one hydrogen atom? Charge present on one hydrogen atom is +1. So its oxidation state is +1. Oxidation state of chlorine. That means I'm asking you the charge present on one chlorine atom. So it is -1. Oxidation state of chlorine here is -1. If I ask you, what is the oxidation state of hydrogen here? That means I'm asking you, what is the charge present on one hydrogen atom? The charge present on one hydrogen atom is +1. So +1 is the oxidation state of hydrogen here. Similarly, -2 is the oxidation state of oxygen here. Similarly, -3 is the oxidation state of nitrogen here. Similarly, +1 is the oxidation state of hydrogen, right? So I believe these two particular points are absolutely clear to you. In case of your covalent compounds, this particular statement, in case of your covalent compounds, the charges are virtual, right? And virtual charges arise due to electronegativity difference, right? At the same time, I believe this particular point is also clear to you. Oxidation state is defined for one atom of an element, right? Perfect. The way I wrote here, oxidation state of hydrogen is +1. What does that mean? That means on one atom of hydrogen in NH3, the charge is +1. I hope you got the basic meaning of the term oxidation state. If yes, let me know quickly in the chats with some fire emojis. Everybody. This was just the basics which you needed to know. All clear? Perfect, people. Perfect. So I hope you got the essence of the term oxidation state properly. Now, there are some rules which you need to know to calculate the oxidation state. rules to calculate oxidation state. This is something very important. Okay, rules to calculate the oxidation state. Certain rules which you have to follow, and with the help of which you can calculate oxidation state of each and every element. Let's get to know about these rules in detail. My dear students, rule number 1. Let me write the rule number 1 in a very compact form. What is that? I'll write in simple words. The oxidation state of an element, oxidation state of an element in free state, or in allotropic form, is taken as zero. So people, one simple thing. Oxidation state of an element in free state or in the allotropic form will be taken as zero. What does that mean? See, if I ask you what is the free state of hydrogen, you will say H2 gas. What is the free state of fluorine? You will say F2. Free state of chlorine, Cl2. What is the free state of iron? Fe solid. What is the free state of copper? Cu solid, right? What are the different allotropic forms of carbon? Let me talk about the main ones. Diamond, graphite. Okay? Whenever you see an element present in free state or in the allotropic forms, you'll be taking their oxidation states as zero. This is the first rule. The oxidation state of hydrogen here is zero, fluorine zero, chlorine zero, iron zero, copper zero, here zero, even here zero. Okay, remember this particular thing. Whenever you see an element present in the free state or in any allotropic form, right, you'll be taking its oxidation state as zero. This is rule number 1, which you will be remembering from now onwards. Rule number 2, people. Rule number 2. Rule number 2 is particularly for group 1 and group 2 elements. I'm writing it over here. The oxidation state of group 1 and the group 2 elements. Oxidation state of group 1 and group 2 elements is taken as +1 and +2 respectively. So first thing, if I ask you what are your group first elements, you'll say lithium, sodium, potassium, rubidium and cesium. They are your group first elements. What are your group second elements? Beryllium, magnesium, calcium, strontium and barium. These are your group second elements. These are our group first elements and these are our group second elements. My dear students, you must be familiar with the fact your group first elements, they are also called as alkali metals. They are called as alkali metals, and group second elements, we call them as the alkaline earth metals. We call them as the alkaline earth metals. Now, something which you need to remember over here, whenever you see the alkali metal, remember the oxidation state of alkali metal is always taken as +1 and the oxidation state of alkaline earth metal is always taken as +2. Right? For alkali metals, oxidation state is assigned as +1. For alkaline earth metals, the oxidation state is assigned as +2. For example, let's say I've got, for example, lithium hydride. One of the compound which I've taken, lithium hydride. Let's say I've got MgH2, right? Let's say we have got CaH2. Perfect. Let's say we have got NaCl. Perfect. So, if you look carefully, here you have lithium, here you have sodium. Both are group first elements. Without even thinking about anything, put the oxidation state of lithium as +1, put the oxidation state of sodium as +1, right? Similarly, here this magnesium and calcium, these are your alkaline earth metals, group second elements. Remember, group second elements, their oxidation state is always taken as +2. Okay? Leave the compound aside. Whenever you see group 1 and group 2 elements, group 1 elements, You just will be assigning the oxidation states as +1. Group 2 elements, you'll be assigning their oxidation states as +2. That's all. That's all. Right? That's about your group first and group second elements. Now, the third one. Now the third rule. My dear students, this third rule which I'm going to tell you, it is particularly for which element? I would say it is particularly for oxygen. This third rule is specially for oxygen. Right? This third rule is specially for oxygen. The first point for oxygen, which I would want you guys to remember from now on. My dear students, whenever you see oxygen present in its free state, whenever you see oxygen present in its free state means O2 form, right? You'll be taking the oxidation state of oxygen as 0. Number one. Number two. Whenever you see oxygen attached with less electronegative element than itself. Whenever you see oxygen attached with less electronegative element than itself, right? Generally, what do you see? Generally, you see oxidation state of oxygen there as -2. For example, you have got MgO. For example, you have got Cl2O. For example, you have got H2O. My dear students, if you look at all these compounds, everywhere oxygen is attached to less electronegative element than itself. And whenever you see oxygen attached to less electronegative element than itself, generally you'll see oxidation state of oxygen as -2. Okay, this was the second point when it comes to the element oxygen. Perfect. Now, my dear students, oxygen forms certain special compounds as well. One of those special compounds are what you call as peroxide. One of those special compounds are what you call as peroxide. For example, you must have seen, or leave the examples right now aside. Oxygen forms peroxides as well. And what are peroxides? My dear students, whenever you see oxygen in this format, O2 di negative. Whenever you see oxygen in this format, O2 di negative. Okay? Understand, oxygen has formed peroxide there. And whenever you see oxygen forming peroxide, oxidation state of oxygen will be taken as -1. It is simple. On 2 oxygen atoms, the charge is -2. On 2 oxygen atoms, the charge is -2. On 1 oxygen atom, the charge is -1. And the charge present on 1 oxygen atom is what I call as oxidation state of oxygen. The charge present on 1 atom of an element is what we call as oxidation state. What are the examples of the peroxides? My dear students, you must have heard about KO2, for example. Sorry. You must have heard about H2O2, hydrogen peroxide. If you look at its structure, this is how it looks like. H2O2. Whenever you see a single bonded linkage between 2 oxygen atoms, understand which linkage this is. You call this linkage as the peroxide linkage. Whenever you see oxygen, single bond oxygen, whenever you see a single bonded linkage between 2 oxygen atoms, my dear students, you'll be calling this as the peroxide linkage, right? And any compound which has got peroxide linkage in it, that compound overall will be called as peroxide. Yeah? Now, if you look at hydrogen peroxide carefully, understand one thing. This is the single bond between oxygen and hydrogen. Now, between oxygen and hydrogen, which one is more electronegative? Oxygen. So this bond pair is shifted towards oxygen due to which? Delta negative, delta positive. Look at this particular bond. Again, due to this bond, delta negative, delta positive. Look at this particular bond between 2 oxygen atoms. On this side oxygen, on this side oxygen. So I would say the tendency with which this oxygen will be attracting this electron pair towards itself, I would say with the same tendency, this oxygen also will be attracting the electron pair towards itself. Due to which, this electron pair between 2 oxygen atoms will be exactly present at the center. It is not shifted towards either of the oxygen atoms. Because on both the sides you have got oxygen here. The tendency with which this oxygen will be attracting the electron pair towards itself. With the same tendency, this particular oxygen will be attracting the same electron pair towards itself. due to which the electron pair is exactly going to remain at the center. Yeah, perfect. So, is this particular bond making any contribution towards the oxidation state? No, it's not making any contribution towards the oxidation state. So, if I ask you, what is the charge on this oxygen? What is the oxidation state of this oxygen? You'll say it's -1. Oxidation state of this oxygen, it's -1, right? So, in general, I will say the oxidation state of oxygen here in H2O2 is nothing but -1. That means the charge present on one oxygen atom here is -1. So, this was the case of peroxides. Similarly, my dear students, oxygen, it forms superoxides as well. It forms one more special compounds, which is what you call as superoxides. And whenever you see oxygen in this format, O2 negative, whenever you see oxygen in this format, O2 negative, understand oxygen at that point of time would be forming what? A compound called as superoxide. And in case of superoxides, my dear people, the oxidation state of oxygen will be taken as -1/2. It is evident too. On 2 oxygen atoms, the charge is -1. Therefore, on 1 oxygen atom, the charge will be -1/2. On 2 oxygen atoms, the charge is -1. Therefore, on 1 oxygen atom, the charge will be -1/2. Simple and basic. And you can take its examples as well. Let's say you would have heard about KO2, potassium superoxide, rubidium superoxide. These are the compounds wherein oxygen shows -1/2 oxygen state. Okay. My dear students, there is again one more set of compounds which oxygen forms. What is that? We call them as oxyfluorides. We call them as oxyfluorides. This is one special set of compounds which oxygen forms. And let me tell you, in the oxyfluorides, what you'll observe? You'll observe oxidation state of oxygen to be positive. If the question is asked, can oxygen form positive oxidation state? The answer is a big yes. Oxygen can form positive oxidation state, as in case of what? Oxyfluorides. What are the examples here? Examples are your OF2 and O2F2. These are the two examples wherein oxygen shows positive oxidation state. Let's have a look exactly how. My dear students, if you talk about OF2, this is the structure of your OF2. If you talk about the structure of your O2F2, this is the structure of your O2F2. Understand properly what exactly I'm going to say. Look at this particular bond. It's between oxygen and fluorine. Now, between oxygen and fluorine, which one is more electronegative? I would say fluorine. So, this bond pair will be shifted towards fluorine, due to which it will have -1, this will have +1. Due to this bond pair, -1, +1. Now, I'm not writing minus delta plus delta. That's understood now, yeah? That's understood. I'm directly writing -1 + 1, -1 + 1. Otherwise, it's actually minus delta plus delta, etc. So, what is the charge present on this particular oxygen here? My dear students, the charge present on this particular oxygen, as I can see, is +2. So, oxidation state of oxygen in OF2, what? +2. Is +2. Look at this O2F2. Look at this O2F2, people. Look at this O2F2. And look at this particular bond between oxygen and fluorine. -1, +1. Due to this bond, -1, +1. Is anything going to happen due to this bond? No. Right? On one side oxygen, other side oxygen. So here, oxygen is having +1 oxidation state. Here also, oxygen is having +1 oxidation state. So in case of O2, the oxidation state of O is +2. In case of O2F2, the oxidation state of O is +1. Right? So these are the compounds wherein oxygen shows positive oxidation states. Now, are there any other set of compounds which oxygen forms? Yes. Oxygen can form ozonoid as well. Oxygen can form ozonoid as well. Whenever you see oxygen in this format, O3 negative. Whenever you see oxygen in this format, O3 negative, at that point of time, oxidation state of oxygen is taken as -1/3, which is evident. On 3 oxygen atoms, the charge is -1. Therefore, on 1 oxygen atom, the charge will be -1/3. Right? And my dear students, do you see properly? In case of O3 negative, the charge present on 1 oxygen atom will be -1/3. And the charge present on 1 oxygen atom is something which you call as oxidation state. I would say oxidation state of oxygen in ozonoid is what? -1/3. What are its examples? You must have seen this particular compound, KO3, potassium ozonide. In potassium ozonide, the oxidation state of oxygen will be -1/3. As simple as that. So these are the varieties of the oxidation states which oxygen shows. Variety of oxidation states which oxygen shows. I believe this is clear to everyone. Yes? Now, Let me have a look on one more rule, which is particularly for which atom? Which is for hydrogen atom. My dear students, if you talk about hydrogen, hydrogen again forms variety of oxidation states. Hydrogen also shows variety of oxidation states. The first one, let me tell you, whenever you see hydrogen present in the free state, whenever you see hydrogen present in the free state means in the form of H2 gas, in the form of H2 gas, I would say oxidation state of hydrogen will be taken as 0. Simple and basic. Yeah. Now, my dear students, whenever you see hydrogen attached to more electronegative element than itself, whenever you see hydrogen attached to more electronegative element than itself, right? At that point of time, let me tell you, oxidation state of hydrogen will be taken as +1. Oxidation state of hydrogen will be taken as +1, right? For example, there are a lot of compounds which you can take. Let's say you've got HCl, let's say you've got H2O, let's say you've got NH3. Everywhere in these compounds, hydrogen is attached with more electronegative element than itself. And you know, when hydrogen is attached with more electronegative element than itself, the oxidation state of hydrogen will be taken as +1, +1, +1 respectively. Right? Similarly, people, whenever you see hydrogen attached with less electronegative element than itself, whenever you see hydrogen attached with less electronegative element than itself, remember oxidation state of hydrogen will be taken as -1, as in case of metal hydrides. If you talk about metal hydrides, for example, I've got lithium hydride. For example, I've got magnesium hydride. For example, I've got calcium hydride, right? For example, I've got sodium hydride. Perfect. In all these hydrides, I must say hydrogen is attached with less electronegative element than itself. And you know, when hydrogen is attached with less electronegative element than itself, the oxidation state of hydrogen is taken as -1. I believe this is clear. These are some special things which you need to remember about hydrogen, right? Hydrogen can form only 3 oxidation states: 0, +1, -1. I believe this is clear. This was about hydrogen, people. Now, about halogens. Have you heard about halogens? Do you know what halogens are? Halogens are represented by X, right? Which include your fluorine, chlorine, bromine, iodine, and astatine, right? My dear students, when you talk about halogens, whenever you see halogen present in free state, whenever you see hydrogen present in free state, right? Whenever you see hydrogen present in free state, for example, fluorine present in the form of F2, chlorine present in the form of Cl2, bromine present in the form of Br2. Whenever you see halogen present in the free state, remember the oxidation state of halogen will be taken as 0. For example, you've got F2, you've got Cl2, everywhere their oxidation states are 0. Correct? One simple point. Similarly, my dear students, whenever you see halogen attached to less electronegative element than itself, whenever you see halogen attached to less electronegative element than itself, at that point of time, oxidation state of halogen will be taken as -1. For example, again I'm taking HCl as a reference, right? Again I'm taking HCl as a reference. For example, here I'm taking PCl5 as a reference. Perfect. Right? As simple as that. So, if you look carefully, halogen is attached to less electronegative element. Halogen attached to less electronegative element than itself. And whenever you see halogen attached to less electronegative element than itself, the oxidation state of halogen will be taken as -1. Right? My dear students, when you see halogen attached to more electronegative element than itself, remember, oxidation at that point of time, halogen shows positive oxidation states, right? Whenever you see halogen attached to more electronegative element than itself, halogen can show positive oxidation state as well, right? For example, you have got Cl2O. You have got Cl2O. Perfect. If you look at its structure, this is O, this is Cl, and this is Cl. Correct? This bond is between oxygen and chlorine. Which one is more electronegative, oxygen or chlorine? I would say oxygen. So this bond pair will be shifted towards oxygen, -1, +1. Due to this bond, -1, +1. So what is the charge present on one chlorine atom? It's +1. Chlorine here is showing +1. Or one more example. If you talk about interhalogens, interhalogens people. If you talk about interhalogens, right? Interhalogens are represented by X dash, and here also X. If you talk about interhalogens, in case of interhalogens, halogens will show positive oxidation state. Let me take the example here. For example, you must have heard about IF7. IF7, right? This is one of the compound which you would have heard. IF7. Perfect. You would have heard about ClF3. This is one more compound. Do you see over here in this particular compound? I would say two different halogens have combined to form a compound. Two different halogens have combined to form a compound. And whenever you see two different halogens combining to form a compound, right? You'll be calling them as interhalogen. So this is the interhalogen, this is interhalogen, right? And my dear students, in these interhalogens, talk about this iodine, talk about this chlorine, calculate their oxidation state. Here, iodine is attached with 7 fluorine atoms with the help of single bond. So iodine will directly have +7. Chlorine is attached with 3 single bonds with fluorine. So chlorine will have +3 oxidation state. So do you see oxidation state of halogens coming out to be positive as well? Yes. So oxidation state of halogens can be positive, right? As in case of the Cl2, as in case of your interhalogens, right? I believe this is clear. So this was about halogens. Now, my dear students, what about sorry, what about coordinate covalent bond? What about coordinate covalent bond? Okay, somebody was asking me in the beginning, sir, what about coordinate covalent bond? Have a look. See guys, for example, there's a coordinate bond between A and B in this way, right? In this way. Okay. How do we get the oxidation states? Due to coordinate covalent bond. Understand one simple thing which I'm going to tell you. My dear students, imagine there's a coordinate bond between A and B. This A I am calling as the donor atom. This B I'm calling here as the acceptor atom. Right? In case of the coordinate bond, both the electrons are given by one atom, but mutually shared by both. So this is my coordinate covalent bond here. Okay. Now, my dear students, understand there are few cases which arise here. Number one, the first case. If the electronegativity of donor, is less than that of electronegativity of acceptor. Let me write it as less or equal to. If electronegativity of donor is less or equal to the electronegativity of acceptor, at that point of time, the oxidation state on donor due to the coordinate bond is taken as +2. Here it is taken as -2. I hope this particular statement is clear. My dear students, whenever you see a coordinate bond between two atoms, if the electronegativity of donor is less or equal to that of acceptor, then donor gets +2, acceptor gets -2. Second case. If electronegativity of donor is greater than that of electronegativity of acceptor, if electronegativity of donor is greater than that of electronegativity of acceptor, at that point of time, the oxidation state due to the coordinate bond on both the atoms is taken as 0. This is a special rule which I would want you guys to remember. If clear, let me know once in the chats quickly. If clear, let me know once in the chats quickly. Yeah? Quickly, people. Quickly, everyone. All clear? Quickly in the chats, guys, everybody. With some fire emojis, quick. Quick, people. Yeah? You can take a lot of examples. NC, N triple bond C, C triple bond N, right? HCN, HNC. I believe you can easily calculate the oxidation state of different elements if you know the structure. That's all. Yeah? Correct? For example, you have got BF4 negative. Let me show you one example. Let's say you have got BF4 negative. I hope you know its structure. This is something which I've taught you in chemical bonding already. This is BFFF, right? This F negative here, right? Which is forming a coordinate bond with this boron. Perfect. So if you want to calculate the oxidation state of boron here, first of all, talk about this particular bond. This bond is between boron and fluorine. Which one is more electronegative? Fluorine. So -1, +1. Due to this bond, -1, +1. Due to this bond, -1, +1. Now, it's a coordinate bond. This is the donor. This is the acceptor. Now donor, you know, fluorine is more electronegative than acceptor. When donor is more electronegative than acceptor, no contribution of coordinate bond is taken. So, if I ask you what is the oxidation state of boron here, +1, +1, +1, so +3. I hope I'm clear. I hope I'm clear. Did you understand? Did you understand, people? Did you understand? For example, you have got one more case, HC, or let me take HNC. HN, double bond C, and coordinate bond 1. Perfect. This is your HNC. Now you should be in a position to calculate the oxidation state of this nitrogen and this carbon, and you are going to try this on your own. I'm not going to show you all the examples here. Right? So I hope this coordinate covalent bond is clear to everyone. Now, moving ahead, people. Moving ahead. I hope you know what are your P block elements. There are some special things which I'm going to tell you now. I hope you know what are your P block elements. Your group 13 to group 18 elements are your P block elements, right? Your group 13 to group 18 elements, they are your P block elements. Perfect. Now, my dear students, related to P block elements, I'm going to give you one point. That's going to give us a lot of questions afterwards. See, remember, in case of P block elements, since if I talk about the P block elements, they show variable oxidation states. P block elements, since they show variable oxidation states, they show range of oxidation states, your P block elements, right? Your P block elements, they show range of oxidation states. So remember, that range of oxidation states, in case of P block elements, it is from group number -18 to group number -10. Group number -18 to group number -10. My dear students, this group number -18 is what I call as lowest possible oxidation state of the P block element. Group number -10 is what I call as highest possible oxidation state of the P block element. For example, let's say I'm taking nitrogen into consideration. Let's say I'm taking oxygen into consideration. Let's say I'm taking fluorine into consideration. What is the group number of nitrogen? Nitrogen belongs to 15th group. Oxygen belongs to group 16. Fluorine belongs to group 17, right? So all of them are your P block elements. And your P block elements, they show range of oxidation states. Let's have a look on that range of oxidation states. So group number -18. So 15 - 18 is -3. So 15 - 10 is +5. Similarly, 16 - 18 is -2. So 16 - 10 is +6, right? 17 - 18 -1. 17 - 10 +7, right? So, my dear students, I can say when it comes to nitrogen, nitrogen's lowest possible oxidation state is -3. Nitrogen's highest possible oxidation state can be +5. Oxygen's lowest possible oxidation state is -2. Oxygen's highest possible oxidation state can be +6. Similarly, this is lowest possible, this is highest possible. This is one important thing which I would want all of you to remember. Yeah? Right? I believe this is also clear. I believe this is also clear. Now, my dear students, one more thing. Have you heard about D block elements? Have you heard about D block elements? For D block elements, I want you guys to remember one point, right, which I'll be using afterwards. My dear students, in case of your D block elements, remember only one thing. Highest possible oxidation state of a D block element. Highest possible oxidation state of a D block element is always equal to n-1 d electrons plus ns electrons. Highest possible oxidation state in case of your D block elements is equal to nothing but n-1 d electrons plus ns electrons. For example, you have got chromium. Do you remember the outermost configuration of chromium? You should be remembering. It is 3d5 4s1. This is the outermost configuration of chromium. So, this is your n. If this is n, that means this will be n-1. If this is n, this is going to be n-1. ns is containing 1 electron. ns is containing 1 electron. n-1 d is containing 5 electrons. So 5 plus 1 comes out to be 6. So highest possible oxidation state of chromium can be +6. For example, you have got manganese. What is the outermost configuration of manganese? You must be knowing. It is 3d5 4s2, right? If this is n, this is going to be n-1, right? So how many electrons are there in ns? 2. How many electrons are there in n-1d? 5. So 5 plus 2 comes out to be 7. So highest possible oxidation state of manganese is going to be +7, right? This is how you are going to check for D block elements, and these are the only 2 elements which you will remember about D block elements. That's all, right? Because I'll be taking their compounds a lot in this particular chapter. I believe I'm clear with this one. Now, there is one more rule which you need to know. What is that? That rule is basically for radicals. What are radicals? Before that, let me tell you. Radicals are considered a single unit. Radicals are considered a single unit. And the charge on them is considered as their oxidation state. My dear students, this rule is used a lot when it comes to coordination compounds. This rule is used a lot when it comes to your coordination compound. So first of all, what are radicals? What are radicals? Remember one thing. Any atom or group of atoms carrying any sort of charge on them, any atom or group of atoms carrying any sort of charge on them is what we call as radical. Any atom or group of atoms carrying any sort of charge on them is what we call as radical. And whatever is the charge on the radical, that is their oxidation state. What does that mean? Say, for example, you have got sodium carrying positive. You have got nitrogen carrying negative. You have got oxygen carrying di-negative. You have got SO4 carrying di-negative. You have got PO4 carrying tri-negative charge. You have got, for example, C2O4 carrying di-negative. You have got NO3 carrying negative, right? You have got S4O6 carrying di-negative. You have got S2O3 carrying di-negative. You have got Cn carrying negative. You have got Nc carrying negative. Look here carefully. Atom carrying charge, atom carrying charge, atom carrying charge, atom carrying charge, or group of atoms carrying charge is what I call as a radical. So this is a radical here, this is a radical, this is a radical. Group of atoms carrying charge, group of atoms carrying charge, group of atoms, everywhere you can see group of atoms carrying charge. Atom carrying charge or group of atom carrying charge is what we call as a radical. And let me tell you, radicals are considered as a single unit. Charge on them is taken as their oxidation state. So, what is the oxidation state of sodium here? +1. Oxidation state of nitrogen here -3. Oxygen here -2. SO4 -2. PO4 -3. Oxalate -2. NO3 -1. S4O6 -2. this minus 2, this minus 1, this minus 1. So radicals are considered as a single units. The charge present on them is directly taken as their oxidation state. I believe this particular statement is also clear to everyone. Yeah? Perfect, people. Now, if this particular statement is clear, let's have a look on one more statement, which is super important. What is that? Remember, my dear students, the sum of oxidation states, the sum of oxidation states of all the atoms, the sum of oxidation states of all the atoms present in a molecule, is equal to the net charge on the molecule, is equal to the net charge present on the molecule. For example, let's say you've got a molecule of this format, ABC. It's a compound, for example. Let's say you've got one more, ABC positive. Let's say you've got one more, ABC negative, right? First thing, if I ask you, what is the charge present on this compound? 0. The charge present on this compound, +1. The net charge present on this compound, -1, right? How many elements do you see here? How many elements do you see here? 3. Now, this rule tells you the sum of their oxidation states, oxidation state of A plus oxidation state of B plus oxidation state of C has to be equal to 0. Oxidation state of A plus B plus C has to be equal to +1. Oxidation state of A plus oxidation state of B plus oxidation state of C has to be -1, right? Or if you have got a compound like this, AXBYCZ, right? Net charge 0. Let's say you have got a compound like this, AXBYCZ, net charge, for example, -1. Let's say you have got a compound AXBYCZ, net charge +1, right? As this rule is concerned, the sum of oxidation states over here is equal to net charge. Sum of oxidation states means oxidation state of A multiplied by X plus oxidation state of B multiplied by Y plus oxidation state of C multiplied by Z is equal to net charge is 0. Oxidation state of A multiplied by X plus oxidation state of B multiplied by Y, oxidation state of C multiplied by Z is equal to -1. Oxidation state of A multiplied by X, B multiplied by Y, C multiplied by Z is equal to +1. So simple, in short, one thing I would want you all to remember. What is that? The sum of oxidation states of all the atoms present in a molecule is equal to what? Net charge present on the molecule. If I'm clear, let me know once in the chats quickly. Quick, people. All clear? All clear, all clear, all clear. Let me know once. Yeah? I hope every single thing is clear till here. I believe so. Okay? Now let's have the application. Let's have a look on the application of all these rules which I gave you till now. My dear students, these are certain compounds which I've taken over here. These are certain compounds which I've taken over here. You have to calculate the oxidation state of the underlined elements. Underlined means green colored elements. Okay? Someone is saying, sir, speed up. Okay, cool. Watch the session in the recorded mode at 1.5x. Okay? It'll be fine for you. Quick, people. Calculate all of them quickly. I'm waiting for your answers. I am waiting for your answers. Quick. Everyone, let me know in the chats quickly. I hope you're with your pen and paper. Welcome, welcome, Nandani. Done? Perfect, people. So let's have a look how to calculate the oxidation states of these green colored elements over here in these compounds. Have a look. Imagine that I need to calculate the oxidation state of this chromium here. Okay. So I'll be assuming the oxidation state of chromium as X. If the oxidation state of chromium is X, that means charge on one chromium atom is X. Do we have one chromium atom or two chromium atoms? We have two chromium atoms, right? So it's not going to be X, it's going to be 2 times X. Plus, oxygen shows -2. There are 7 oxygen atoms. Net charge on this particular compound is -2. So X value comes out to be +6. Okay, X value comes out to be +6. Now, this particular one. This is again going to be 2X. Oxygen is going to show -2. There are 3 oxygen atoms. Net charge is -2. The value of X will be +2, right? This nitrogen. Let the oxidation state of nitrogen be X. Hydrogen is attached to more electronegative, so +1. There are 4 hydrogen atoms. Net charge is +1. X after solving is -3. Chlorine. X. Oxygen is going to show -2. There are 4 oxygen atoms. Net charge -1. So it's +7. Let the oxidation state of chromium be X. Oxygen is going to show -2. There are 4 oxygen atoms. Net charge is -2. The value of X comes out to be +6. Right? The value of X comes out to be +6. I believe this is clear. Let's have a look on a few more compounds. Fe2O3. Oxidation state of iron. So these are 2 iron atoms, so make it 2X. Oxygen will be -2. There are 3 oxygen atoms. Net charge 0. The value of X is going to be how much? +2, right? Sorry, +3. 2X -6 is equal to 0. So 6 by 2 is 3. Oxidation state of this iron. Let it be X, but there are 3 iron atoms, so 3X. Oxygen will be showing -2. There are 4 oxygen atoms. Net charge 0. The value of X will come out to be +8 by 3. Right? Now, it's a complex here. It's a complex here. This Cn is a radical. This Cn is a radical. And radical is considered to be a single unit. The charge present on it is taken its oxidation state. Let the oxidation state of iron be X. Oxidation state of Cn, here will be -1. There are 6 Cn radicals here. Net charge is -3. The value of X after solving comes out to be +3. This is carbonyl. It is a carbonyl. CO, carbonyl. Carbonyl, I am pretty much sure you would have heard somewhere in coordination chemistry that carbonyl is a neutral ligand. If it is a neutral ligand, no charge on this, therefore no charge on this nickel as well. Sulfur. Oxidation state of hydrogen will be +1. There are 2 hydrogen atoms. Let the oxidation state of sulfur be X. Oxidation state of oxygen is -2. There are 4 oxygen atoms. Net charge 0. The value of X is going to be +6. So it's +6 here, right? My dear students, in case of NH4NO2, we have to calculate oxidation state of this nitrogen as well as this nitrogen. Let me tell you, it's a special case. NH4NO2 exists in the form of NH4 positive dot NO2 negative. This is how the compound exists. NH4 positive dot NO2 negative. Now, my dear students, I need to calculate oxidation state of this nitrogen as well as this nitrogen. Yeah? I need to calculate oxidation states of these 2 nitrogen atoms. Well, in order to calculate oxidation state of this nitrogen, I'll be considering this as the separate entity. I'll be considering this as well as the separate entity. Now, do the calculation. Let the oxidation state of this nitrogen is X. Hydrogen here is going to show +1. There are 4 hydrogen atoms. Net charge is +1. So X here will come out to be -3. The oxidation state of nitrogen here is -3. Talk about this nitrogen. This is X. Oxygen will be showing -2. There are 2 oxygen atoms. Net charge here is -1. The value of X will come out to be +3. So this nitrogen is right here present in +3 oxidation state. If you talk about Ki3, potassium is the group first element, which is going to show +1, right? Let the iodine show X, so this is 3X. Net charge is 0. The value of X after solving will come out to be how much? -1/3. So -1/3 is the oxidation state of iodine here, right? For example, tell me what is the oxidation state of carbon here? Quickly. Similarly, tell me the oxidation state of bromine here. Quickly. I'm underlining these two elements. Tell me their oxidation states quickly. You should be in a position to do that. Quickly, people. Everyone in the chats. Then only I can know whether you are getting the concepts or not. Quickly. Everybody in the chats, quick. C3O2 and Br308. C3O2, Br308, quick. Guys, just give me a second. There is the electricity cut. Let me turn the generator on. Quick, wait. All fine now? All fine? Okay. Talk about this particular carbon, guys. I believe you have already done it. Let's say the oxidation state of this carbon is X, so it's going to be 3X. Oxygen is going to show -2. There are 2 oxygen atoms. Net charge is 0. When you solve, the value of X comes out to be +4/3. So +4/3 is the oxidation state of carbon here. Similarly, this is 3X. Oxygen is going to show -2. There are 8 oxygen atoms. Net charge is 0. The value of X will come out to be +16/3. So oxidation state of bromine here is +16/3. Similarly, I'm giving you one more compound. Tell me the oxidation state of iron in this compound. Tell me the oxidation state of iron in this particular compound. How you guys are going to do it? How you guys are going to do it? Let the oxidation state of iron be X. How many iron atoms do you see? 0.93. Oxygen is going to show -2. Net charge is 0. When you calculate X, X will be 2 divided by 0.93. Or I can say X will be 200 by 93. X will be plus 200 divided by 93. Perfect. I believe I'm clear with this. Now, my dear students, understand one more thing. Understand one more thing. The oxidation state of iron over here came out to be fractional, right? Oxidation state of iodine here came out to be fractional, right? Perfect. But the point is, what is the oxidation state? Charge present on an atom. Can charge on an atom be fractional? Can charge on an atom be fractional? Can charge on an atom be fractional? No. Because you would have studied in physics, Q is equal to NE. It is the integral multiple. It is the integral multiple. Remember one simple thing over here. Whenever the oxidation state of an element by using the formula comes out to be fractional, do remember that is not the normal oxidation state at that point of time. That is basically the average oxidation state. What is average oxidation state? You'll get the idea in some time. But before that, before making you understand what that average oxidation state is all about, remember whenever with the help of formula, oxidation state of an element comes out to be fractional, Remember that oxidation state, that fractional oxidation state, that is basically the average oxidation state of an element. Similarly, if I ask you here, what is this -1/3? It is the average oxidation state of iodine here, right? What is this +4/3? It is the average oxidation state of carbon here. What is this +16/3? It is the average oxidation state of bromine over here. What is this +200/93? It is the average oxidation state of iron here, right? It is the average oxidation state of iron here. So whenever with the help of formula oxidation state of an element comes out to be fractional, remember that is not the normal oxidation state, that is the average oxidation. Yeah? Now people, try to understand few more things. I am going to write one very, very, very important statement. I am going to write one very, very, very important statement. What is that? Take a note of it. Take a note of it, my dear student. I'm writing the maximum oxidation state. The maximum oxidation state of an element. The maximum oxidation state of an element in a compound. The maximum oxidation state of an element in a compound can never be greater than +7, except osmium in osmium tetroxide, where it is +8. This is one important statement, my dear students, which I would want you guys to remember. The maximum oxidation state of an element, it can never be greater than +7. There is one exception you have to remember, that's osmium. When it forms osmium tetroxide, the oxidation state of osmium in osmium tetroxide is +8. And this is the question which is asked in your AIMS as well. It is an AIMS PYQ. What is the oxidation state of osmium in OSO4? Oxidation state of osmium in OSO4 is nothing but +8, right? Otherwise, oxidation state of an element can never be greater than +7. There is one exception. Osmium in OSO4 shows the oxidation state of +8. Now, why this particular statement is important? Because there is a logic. What is the logic, people? Understand. For example, I'm taking a compound CrO5. Let's say I'm taking a compound CrO5. And for example, I'm asking you to calculate oxidation state of chromium here. You should be in a position to do it. I'm asking you to calculate oxidation state of chromium here in this compound with the help of formula. What are you will be doing? You'll be calling the oxidation state of chromium as X. You'll be calling the oxidation state of oxygen here as -2. Since there are 5 oxygen atoms, you will say net charge is 0. And eventually you'll get the value of X as 10. But can X be equal to 10? X cannot be 10. X cannot be 10. For example, if I take the compound as CrO6, and I ask you, for example, to calculate the oxidation state of chromium here, what you'll be doing? You'll be saying, call this X, oxygen -2, 6 oxygen atoms, net charge 0, the value of X will come out to be +12. Is +12 possible? +12 is not possible because the maximum oxidation state of an element can never be greater than +7. There is only one exception, osmium in OSO4, where it shows +8. So how come it's +10 here? Not possible. How come it is +12 here? Not possible. So remember guys, one important statement I'm writing over here. Whenever oxidation state of an element comes out to be greater than +7, from the formula. At that time, we need to take the structure of the compound. At that point of time, we need to take the structure of the compound into consideration. In order to calculate the actual oxidation state. In order to calculate the actual oxidation state of an element. I hope this particular statement is clear. So whenever with the help of formula, oxidation state of an element comes out to be greater than +7, at that point of time, you need to take the structure of the compound into consideration, then only you can calculate the actual oxidation state of an element. So mark the heading here as some important compounds. Mark the heading here as some important compounds. Some important compounds. Some important compounds whose structure you need to know from now onwards. Okay? So people, I'm starting with the first structure as CrO5, chromium pentoxide, CrO5. Let me tell you one thing. This CrO5, we say it has got a butterfly-like structure, which is not true though. It has got a butterfly-like structure, number one. Number two, CrO5. Let me tell you, it is deep blue in color. CrO5 is deep blue in color. Now, how the CrO5 exactly looks like? This is chromium, double bond O, oxygen, oxygen, single bond. Similarly, oxygen, oxygen, single bond. This is the actual structure of your CrO5. If this is the actual structure of your CrO5, my dear students, look at this particular bond. It is between chromium and oxygen. Which one is more electronegative? Oxygen is more electronegative. So this bond pair will be shifted towards oxygen. So -1, +1. Due to this bond, -1, +1. Due to this bond, -1, +1. Due to this bond, -1, +1. Due to this double bond, I'll say -2 and +2. Now, if I ask you, what is the total charge present on chromium here? The total charge on chromium here will be +2, +3, +4, +5, +6. So +6 is the total charge on the chromium. So I would say the oxidation state of chromium in case of CrO5 is +6. Right? Right, people? At the same time, my dear students, with the help of formula, the oxidation state of chromium was coming out to be +10. Oxidation state of chromium with the help of formula was coming out to be +10. Why is that? Because I was considering all the oxygen atoms to be present. I was considering all the oxygen atoms to be present in -2 oxidation state. But look carefully. Are all the oxygen atoms present in -2 oxidation state? No. Why is that? Because, my dear students, here, in reality, there's a peroxide linkage here. In reality, there's a peroxide linkage here, which we were ignoring before. Right? Which we were ignoring before. So, there's a oxygen, single bond oxygen. You call this particular linkage as the peroxide linkage. So, this linkage we were ignoring in the formula, right? We were considering all the 5 oxygen atoms to be in -2 oxygen state. But in reality, when we got to know, when we checked the structure, we got to know out of 5 oxygen atoms, 4 oxygen atoms are there in -1 oxidation state. 1 oxygen atom is there in -2 oxidation state. So if I ask you, how many peroxide linkage do you see here? This can be the question asked. How many peroxide linkages are here in CrO5? 1, 2. There are 2 peroxide linkages. If they ask you, how many oxygen atoms do you see with -1 oxidation state? How many oxygen atoms do you see with -1 oxidation state? It is simply number of peroxide linkages multiplied by 2. How many peroxide linkages? 2. So 2 multiplied by 2 comes out to be 4. Perfect. So this was your CrO5. Second structure is going to be for CrO6. Well, this compound was asked in NEET, I think 2021 or 2022. So it's a PYQ. What is the oxidation state of chromium in CrO6? Right? If you look at its structure, it is like this. If you look at its structure, this is how your CrO6 looks like. This is how your CrO6 looks like. Now, my dear students, understand properly. Look at this particular bond between chromium and oxygen. Which one is more electronegative? I would say oxygen is more electronegative. So this bond pair is shifted towards oxygen. -1, +1. Due to this particular bond, -1, +1. Due to this particular bond, -1, +1. Due to this particular bond, minus 1, plus 1. This one, minus 1, plus 1. This particular bond, minus 1, plus 1. So check the total charge present on chromium. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. So I would say the total charge on chromium here is plus 6. Or you can say the total oxidation state of chromium here is plus 6. Yeah, I believe this is clear. Now, if I ask you one more thing, how many peroxide linkages are here? How many peroxide linkages are here? Oxygen, single oxygen, peroxide, peroxide, peroxide. So there are basically 3 peroxide linkages. If I ask you how many oxygen atoms are there with minus 1 oxidation state, so 3 2s comes out to be 6. So this was our second structure. Okay, this was our second structure. The third one. Have you heard about Carrow's acid? Carrow's acid, people, which is what you call as H2SO5. How this H2SO5 looks like? Sulfur, double bonded O, oxygen attached with hydrogen, oxygen, oxygen, hydrogen. This is the structure of your H2SO5. Now, my dear students, if you look at the structure of your H2SO5 and try to analyze the structure, this is S double bond O. Oxygen is more electronegative. So both the electron pairs will move towards oxygen. Minus 2, plus 2. Due to this double bond, minus 2, plus 2. Due to this single bond, minus 1, plus 1. Due to this single bond, minus 1, plus 1. So what is the total charge on this sulfur here? Plus 2, plus 4, plus 5, plus 6. Do you see any peroxide linkage here? I can see one peroxide linkage here, right? So how many oxygen atoms will be there with minus 1 oxidation state? 1 multiplied by 2 comes out to be 2. So this was my third structure. That was your Carrow's acid. Now, the fourth one. The fourth one. I hope you would have heard about something called as oleum. H2S2O7. My dear students, if you look at the structure of your oleum, this is SOS, double bond O, oxygen attached with hydrogen, double bond O, oxygen attached with hydrogen. Now, in this particular structure, how many sulfur atoms do you see? There are 2 sulfur atoms. If you see carefully, there are 2 sulfur atoms. Now we will analyze and understand things properly. Talk about this particular sulfur. It is S double bond O. Due to this double bond, oxygen will have minus 2, sulfur plus 2. Due to this double bond, oxygen minus 2, sulfur plus 2. Due to this single bond, minus 1, plus 1. Due to this single bond, minus 1 and plus 1. So what is the total charge on this sulfur here? If you see, plus 2, plus 4, plus 5, plus 6, right? So its oxidation state is plus 6. Similarly, when you calculate oxidation state of this sulfur, it will also come out to be plus 6. Because the surrounding of both the sulfurs is same here. Whatever is the surrounding of this sulfur, same is the surrounding of this sulfur. So plus 6, plus 6. Since there are more than 1 sulfur atoms, if there are more than 1 sulfur atoms, therefore I will be calculating average oxidation state of sulfur here. There are more than 1 sulfur atoms. I'll be calculating the average oxidation state of sulfur. The first sulfur is showing plus 6 oxidation state. Second sulfur is also showing plus 6 and in total there are 2 sulfur atoms. So when you calculate it, the average oxidation state of sulfur comes out to be plus 6 as well. I believe you got to know how to calculate the average oxidation state as well. Right? These are the normal oxidation states, which cannot be fractional. Average oxidation state can be fractional. Average oxidation state can be fractional. But here, in this particular case, average oxidation state did not come out to be fractional. The average oxidation state is not always fractional. It can be fractional. It can be fractional. So this was your oleum. Structure number 5. Marshall's acid. Marshall's acid. H2S2O8. How this Marshall's acid exactly looks like? This is SOOS, double bond O, oxygen attached with hydrogen, double bond O, oxygen attached with hydrogen. So this is your structure of your H2S2O8, right? Now, my dear students, by drawing the structure of H2S2O8, now we can calculate the oxidation state of each sulfur atom here, right? Look at this particular sulfur. Look at this particular sulfur. It is S double bond O. So minus 2 plus 2. Due to this double bond, minus 2 plus 2. Due to this single bond, minus 1 plus 1. Due to this single bond, minus 1 plus 1. So total charge on this sulfur is plus 2 plus 4 plus 5 plus 6. Similarly, surrounding of both the sulfur is same. So plus 6 here also. And average oxidation state of sulfur will be First one carrying +6, second one carrying +6, total 2 sulfur atoms. So average here is +6. How many peroxide linkage do you see here? This is the only peroxide linkage I saw. So one peroxide linkage. So how many oxygen atoms with -1 oxidation state? There'll be 2 oxygen atoms with -1 oxidation state, right? So this was our fifth structure, that is Marshall's acid. Now, the sixth one. Sixth one. My dear students, you would have heard about Na2S4O6. From this particular compound, many a times question has been asked in JEE Mains, right? So question can be asked in NEET as well. Na2S4O6. You need to understand the structure of Na2S4O6. This is how it looks like. Oxygen with sodium, and here oxygen with sodium, right? And here oxygen with sodium, right? Now people, understand and analyze this particular structure as well. First of all, talk about this double bond O, S double bond O. Oxygen more electronegative. So oxygen will have -2, sulfur will have +2. Due to this double bond, sulfur will have again +2. Due to this single bond, sulfur will have +1. Due to this bond, sulfur is not going to have any charge. This bond, nothing. This bond, nothing. Now talk about this double bond. Sulfur will have +2. This double bond, sulfur will have +2. This single bond, sulfur will have +1. So what is the charge on this particular sulfur? +2, +4, +5. What is the charge on this sulfur? 0. What is the charge on this sulfur? 0. What is the charge on this sulfur? It is +5. Right? You got the charge on each sulfur atom. So you got the oxidation state of each sulfur atom over here. Now, if I ask you, what is the average oxidation state of sulfur? You'll say the first one is carrying +1 charge. The second one is carrying 0 charge. Third one is carrying 0 charge. Fourth one is carrying +1 charge divided by. How many sulfur atoms do we have? 4. When you calculate it, it comes out to be +2.5. So this is basically the average oxidation state of sulfur, which is coming out to be fractional, right? This is the average oxidation state of sulfur, which is coming out to be fractional here in case of Na2S4O6. Now, the seventh one. You know, once a question was asked in JEE Mains about this particular compound. The question was like this. The question was like this. The correct set of oxidation state of sulfur in Na2S4O6 is. The options were given in this format. +5, 0, 0 +5, +5, +5, 0 and 0, 0, 0 +5, +5, none of them, right? So if you just remember the structure, you will be in a position to solve this. So it has to be option 1. It has to be sodium, right? It has to be option 1. This is sodium here, ONA, right? Perfect. Never these structures you have to remember by practicing more and more times. I believe this particular question is clear and the sixth structure is clear. Now, talking about the seventh structure. Seventh structure is your K3CrO8. You must have heard this particular somewhere, K3CrO8. How it looks like exactly? This is chromium, oxygen, oxygen, single bond. This is oxygen, oxygen, single bond, single bond, single bond. Now, this oxygen is attached with potassium. Even this is attached with potassium. Even this is attached with potassium, right? K3CrO8. Now, tell me by looking at the structure, people. This is a single bond between chromium and oxygen. Which one is more electronegative? Oxygen. So, due to this particular oxygen, -1 and this is +1. Due to this oxygen, -1 and +1. Due to this oxygen, +1. Due to this oxygen, +1. Due to this oxygen, +1. So, what is the total charge on this chromium? It is going to be +1, +2, +3, +4, +5. So, it's going to be +5. How many peroxide linkage do you see here in this particular case? 1 peroxide, second, third, fourth. There are 4 peroxide linkages. How many oxygen atoms with -1 oxidation state? 4 2s are 8. 8 oxygen atoms with -1 oxidation state. I believe this is clear. This was my 7th structure. 8th one. Br3O8. 9th one. C3O2. C3O2. You need to remember their structures as well. Okay. Br3O8 looks like this. Br308. Now, my dear students, look carefully. Bromine, oxygen, which one is more electronegative? Oxygen. So both these bond pair towards oxygen. So -2, +2. Due to this double bond, -2, +2. Due to this double bond, -2, +2. Due to this single bond, nothing will happen. Due to this single bond, nothing will happen. Due to this double bond, -2, +2. -2, +2. Similarly, -2, +2. -2, +2. Similarly, -2 and +2. Now calculate everything. What is the total oxidation state on this bromine? +2, +4, +6. +2, +4. +2, +4, +6. If I ask you what is the average oxidation state of bromine, it is going to be +6, +4, +6 divided by 3. So it comes out to be +16 divided by 3. +16 by 3. This is going to be the average oxidation state of bromine in case of Br308. Right? Perfect. If you look at C3O2, C3O2, the structure is simple. C double bond C double bond C. This is O. This is O. Now look at this particular compound. C double bond O. Which one is more electronegative? Oxygen. So -2 and +2. Between this particular double bond. So this is -2, this is +2. This is CC. This is CC. So nothing. This is 0. Now, if I ask you the average oxidation state of carbon in C3O2, the first carbon carries +2, second carbon carries 0, third carbon carries +2, divided by total 3 carbon atoms. So this comes out to be +4 by 3. So this is the average oxidation state of C3O2 over here. Sorry, this is the average oxidation state of carbon in C3O2, right? Which is coming out to be fractional. As I told you, average oxidation state can come out to be fractional, right? It can come out to be fractional like you're seeing all these particular compounds, C3O2. Now, the 10th structure. I hope you would have heard about bleaching powder, CaOCl2. Let me make a rough structure of bleaching powder. This is OCl, right? And this is calcium here. This is Cl. This is Cl, right? Let me make, just to make you understand, let me put the bonds here as well, just to make you understand. This is OCl here. Which one is more electronegative? Oxygen. So -1, +1. Which one is more electronegative? Oxygen. So -1, +1. Which one is more electronegative? Chlorine. -1, +1. Right? So what is the oxidation state of this chlorine? +1. What is the oxidation state of this chlorine? -1. If I ask you what is the average oxidation state of chlorine, you will say first chlorine carries +1, second chlorine carries -1. There are 2 chlorine atoms. So average will come out to be 0. The average oxidation state of chlorine in case of your bleaching powder is coming out to be 0. So this was my 10th structure, that is bleaching powder. 11. There is a compound BASCN whole twice. This is something which I'll be using afterwards. When I'll be teaching you the N factor calculation, I would need its structure there also, right? BASCN whole twice. This is BA. For example, this is SC triple bond N. Similarly, for example, this is SC triple bond N, right? So, if you want to calculate the oxidation states of each elements, carbon triple bond nitrogen, which one is more electronegative? Nitrogen. So, all the 3 bond pairs towards nitrogen, -3 and +3. Among carbon and sulfur, sulfur is more electronegative, so -1 and +1. Among barium and sulfur, sulfur is more electronegative, -1, +1. Air, -1, +1, right? This is a single bond. Sulfur more electronegative, -1, +1. Nitrogen more electronegative, -3, +3. So calculate the oxidation state of each element. Nitrogen is -3, -3. Talk about this carbon, +3 + 1 is +4. Talk about this sulfur, -1 is -2. This barium, +1 + 1 is +2. This sulfur, -1 is -2. This carbon, +3 + 1 is +4. This nitrogen, -3 over here. So this is the structure of your BASCN whole twice, right? Right, people? Similarly, one more, people. Let's say you have got HCN. HCN. This is something which I would need in the N factor calculation as well. This is something which I would need in the N factor calculation as well, right? So first of all, there's a triple bond between carbon nitrogen, so -3 and +3. Carbon hydrogen, carbon is more electronegative, -1, +1. So what is the oxidation state of this particular carbon here? It will come out to be +2. +3 -1 comes out to be +2. Oxidation state of this nitrogen here, -3. I'll be using this particular compound also in different n factor calculations. So this was my 12th structure. Now, our 13th structure is going to be for H3PO2. I believe you would have heard this. 14th structure is going to be your H3PO3. 15th structure is going to be your H3PO4. And 15th structure is going to be your H3PO5. Right? And how do we make these structures over here? Again, in the same way. Everywhere, first of all, I'll be drawing P double bond O. Everywhere, I'll be drawing P double bond O. Everywhere, I've drawn P double bond O. Now, this is oxygen attached with hydrogen. These are your two hydrogen atoms. So this H3PO2. Similarly, oxygen attached with hydrogen. Oxygen with hydrogen. One hydrogen directly. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen, hydrogen. Oxygen, oxygen, and hydrogen. These are the structures of these different compounds as well. Now, if you got the structures, calculate the oxidation states. When you calculate, oxidation state of this phosphorus will come out to be +1. Oxidation state of this phosphorus will come out to be +3. This phosphorus will be in +5 oxidation state. Even this phosphorus will be in +5 oxidation state. And here, you'll find one peroxide linkage, right? And there'll be two oxygen atoms in the last case, which will be in -1 oxidation state. So this is what these structures were all about. One more important thing. My dear students, we had Fe3O4. And when we use the formula, we got the oxidation state of iron as +8/3. As I told you, +8/3, it cannot be the normal charge on the atom, right? It is basically the average. It is basically the average, right? It is basically the average oxidation state. So this Fe3O4, let me tell you, it exists as, it forms a mixed oxide. It is basically a mixed oxide, Fe3O4. And this Fe3O4, it exists in the form of FeO.Fe2O3. This Fe3O4 exists in the form of FeO.Fe2O3. So, oxidation state of this iron is calculated separately. Oxidation state of this iron is also calculated separately. When you calculate oxidation state of this iron, let's call this as X -2 is equal to 0. So, this iron is in +2 oxidation state. 2x -6, 3 2s are 6, is equal to 0. So this iron is in +3 oxidation state. So one iron is in +2, remaining two irons are in +3. So when you calculate average oxidation state of iron here, the first iron is in +2 oxidation state, right? Over here, +3. And how many are in +3? 2. How many iron total we have? 1 + 2, 3. When you solve this, the value comes out to be +8/3, which is basically the average oxidation state of iron in case of your Fe3O4. I believe I'm clear to every one of you. Right? Perfect. Similarly, my dear students, one last structure. Let's say you have got something like this. CH3, COOH. Can you calculate the oxidation state of this carbon? Yes, you can do that if you just know its structure. If you just know its structure. This is CH3, this is C, double bond O, and this is OH. You can calculate the oxidation state of each and every element over here. Right? You can do that. You know it. This is OH bond, -1 + 1. This is OC bond, -1 + 1. This is double bond O, -2 + 2. Right? I mean, you should be in a position to calculate oxidation states of all these underlined elements over here. I believe this is super clear to everyone. So this was all about the structures of different compounds. Perfect? Right? So let's take a short break here. Well, this is not the dinner break. It's a short break we are taking. Let's have a tea or coffee. Right, people? And what is the time right now? It is 7:34. I would want every one of you to be back on time, number one. Okay? I would want every one of you to be back on time. So we have got a break till so be back at 8 p.m. Okay? Go get refreshed and be back. whatever things I was discussing till now, it was all basics. Whatever things I was discussing till now, it was all basics, people. Now, after the break, we are going to start something interesting, something amazing, right? Have a tea, but be back on time. Perfect. See you. Take care. See you in some time. So people, is everyone back? Yeah? Is everyone back here? Is everyone back? All right. All right, people, just give me a second. Perfect. So tell me, whatever things we discussed till now, are all the things clear to you? Yeah? Are all the things clear to you? Whatever things we discussed till now, is every single thing clear? Tell me quickly in the chats, everyone. Tell me quickly in the chats, everyone. Whatever things we discussed till now, are all the things absolutely clear? Perfect, guys, perfect. So we are done with the oxidation state and rules to calculate oxidation state. Similarly, we are done with the, different structures as well. Now we are going to get into one more topic, that is oxidation and reduction. What exactly oxidation is all about? What exactly reduction is all about? Right? Let's get to know about all that stuff one on one. Let's get to know about all that stuff one on one. My dear students, if you talk about oxidation, well, oxidation I'm going to define in number of ways over here. Similarly, reduction also I'm going to define in number of ways. Oxidation reduction I'm going to define in many ways over here. So let's try to understand what this oxidation reduction exactly is all about. My dear students, oxidation is first of all defined as the loss of electrons. Similarly, if I talk about reduction, reduction is defined as the gain of electrons. If I write an example over here, imagine I've got sodium, and for example, sodium is losing one electron, getting converted into Na positive. Sodium is losing one electron, getting converted into Na positive, right? So, since sodium is losing electron over here, I would say this sodium, it is undergoing oxidation. Since it's losing electron, loss of electron is something which we call as oxidation, right? Since sodium is losing electron, getting converted into Na positive, so I would say sodium is undergoing oxidation here. Similarly, for example, I've got Na positive. I'm giving it one electron, and for example, it is getting converted into sodium. So Na positive is gaining one electron, getting converted into sodium, right? Gain of electrons is what you call as the reduction. So I must say this Na positive is undergoing reduction here. I must say this Na positive is undergoing reduction because it's gaining electron here. This is the first definition in terms of electron exchange. Loss of electrons is what we call as oxidation. Gain of electrons is what we call as reduction. Number two, oxidation is also defined as addition of oxygen. And reduction is also defined as removal of oxygen. Addition of oxygen is termed as oxidation. Removal of oxygen is termed as reduction. For example, let's say I've got calcium. I'm giving it half of O2. It is getting converted into calcium oxide. If I reverse the reaction, calcium oxide gives calcium plus half of O2. My dear students, what is happening in these reactions which I wrote over here? See, can I say in this particular reaction, addition of oxygen is happening towards calcium? Addition of oxygen is what you call as oxidation. Similarly, removal of oxygen is what you call as reduction. This is one more definition of what? Oxidation reduction. Similarly, removal of hydrogen is what you call as oxidation. And let me tell you, addition of hydrogen is what you call as reduction. What is removal of hydrogen? For example, I'm writing this reaction. 2 times H2O gives 2 times H2 plus O2. If I reverse the reaction, 2 times H2 plus O2 gives 2 times H2O. Do you see in this particular reaction removal of hydrogen taking place? Yes, removal of hydrogen is taking place here. My dear students, removal of hydrogen is also what you call as oxidation. Similarly, in this reaction, addition of hydrogen is taking place. And addition of hydrogen is what you call as reduction. Next, addition of more electronegative element. Addition of more electronegative element is what you call as oxidation. For example, C plus 2 times Cl2 gives CCl4. Similarly, here I would say removal of more electronegative element is what you call as reduction. Just reverse the reaction. So this is CCl4 giving carbon plus 2 times Cl2. In this reaction, my dear students, if you see, a more electronegative element is being added. And addition of more electronegative element is what you call as oxidation. Similarly here, more electronegative element is removed. And removal of more electronegative element is what you call as reduction. So these are different ways by means of which you can define oxidation and reduction. So my dear students, if you look at oxidation, first of all, loss of electrons, addition of oxygen, removal of hydrogen, addition of more electronegative element. If you talk about reduction, gain of electrons, removal of oxygen, addition of hydrogen, removal of more electronegative element. Now, you're not supposed to remember all this stuff. There is one thing, my dear students, which I want you guys to understand here. And what is that one thing? I'll have a look. If I ask you, is there any charge on sodium here? You'll say no, 0. Is there any charge on sodium here? Yes, +1. Charge on calcium here? 0. Charge on calcium. Oxidation state of calcium here. Calcium is group second, right? And group second elements, they show +2, right? Oxygen here is in -2 oxidation state when you calculate. Oxygen here is in 0 oxidation state. Carbon here is in 0 oxidation state. Carbon here is in, when you calculate X, this is -1 into 4 is equal to 0. So this is +4. But dear students, just analyze one thing everywhere. 0 to +1 is the oxidation state of sodium increasing or decreasing. 0 to +1 means increase in the oxidation state. 0 to +2, again increase in the oxidation state. -2 to 0, again increase in the oxidation state. 0 to +4, again increase in the oxidation state. Do you see one thing common in every oxidation reaction? What is that common thing? Oxidation state of an element is increasing. My dear students, you are going to remember one thing about oxidation from now onwards. Just one thing. What is that one thing? Take a note of it. I would say during oxidation, oxidation state of an element increases. That's all. From now onwards, you are going to remember one thing. Increase in the oxidation state of an element is what we call as oxidation, right? Increase in the oxidation state of an element is what we call as oxidation. And during oxidation, loss of electrons takes place. That's all. Nothing apart from this. Nothing apart from this. Similarly, my dear students, if you talk about reduction, reduction involves what? decrease in the oxidation state of an element. Decrease in the oxidation state of an element is what you call as reduction. And reduction involves what? Gain of electrons. These are just the two statements which I want you guys to remember from now onward. Right? Just two statements which I got from these definitions. Right? If you check here, +1 to 0, decrease in the oxidation state. Right? +2 to 0, decrease in the oxidation state. 0 to -2, decrease in the oxidation state. +4 to 0, decrease in the oxidation state. So decrease in the oxidation state is what we call as reduction. Increase in the oxidation state is what we call as oxidation. Is this statement clear? Let me know once in the chats, quickly people, if this is clear. If this is clear, let me know quickly in the chats. Yeah? All clear? Now guys, if you got the essence of what is oxidation and what is reduction, now this is the time to understand few more important terminologies. This is the time to understand few more important terminologies. The first terminology which I'm writing is oxidizing agent, or you call it as oxidant as well. What is an oxidizing agent? What is the oxidant? How do we define it? Understand properly. See guys, I would say the substance that oxidizes others. The substance that oxidizes others, but itself undergoes reduction. But itself undergoes reduction. The substance that oxidizes others, but itself undergoes reduction is what you call as oxidizing agent. What that means, you'll get the idea in some time. Before that, let me write one more definition first. That is for the reducing agent. A reducing agent, or you call it as the reductant as well. Reducing agent or reductant. What is the reducing agent? What is the reductant? How do you define it? It's again simple. See guys, I'll write the substance that reduces others. The substance that reduces others, but itself undergoes oxidation. The substance that reduces others, but itself undergoes oxidation. Let's try to understand these two definitions in detail. First of all, what is oxidation? Increase in the oxidation state. During oxidation, what happens? Loss of electrons takes place. What is the reduction? Decrease in the oxidation state. During reduction, gain of electrons takes place. Right? Now tell me one thing. Oxidizing agent. Oxidizing agent oxidizes others. Oxidizing agent, be careful with the terminologies. Oxidizing agent oxidizes others, but itself undergoes reduction. Oxidizing agent oxidizes others, but itself undergoes reduction. If oxidizing agent oxidizes others, that means oxidizing agent is going to make others lose electrons. Right? And if others lose electrons, those electrons are gained by it. So it itself undergoes reduction. Again, I'm repeating the same thing. Oxidizing agent oxidizes others, but itself undergoes reduction. If oxidizing agent is oxidizing others, that means it's making others lose electrons. It's making others lose electrons. And those electrons which are lost by others is gained by it. So that's why I'm telling oxidizing agent oxidizes others, but itself gains electrons, itself undergoes reduction. Right? Similarly, reducing agent. Reducing agent reduces others. Your oxidizing agent oxidizes others, but reducing agent reduces others and itself undergoes oxidation. Reducing agent reduces others. So reducing agent makes others to gain electrons. From where those electron comes? Itself undergoes oxidation. So it loses electrons and those electrons are gained by others. Yeah? Did you understand this? Oxidizing agent oxidizes others. Itself undergoes reduction. Reducing agent reduces others. Itself undergoes oxidation. Can you let me know once in the chats quick? Can you let me know once in the chats quick, people? If you got this? Let me know once in the chats quick if you got this. Everybody. And be active in the chats now. Be active in the chats. Let me know once in the chats quick. Everyone means everyone. Yeah? Now, people, let me teach you exactly how to identify the oxidizing and reducing agent. Let me teach you exactly how to identify the oxidizing and reducing agent. Understand properly what I'm going to do. Let me take certain examples with the help of which you'll understand how to recognize oxidizing and reducing agent. Understand properly. For example, I'm writing a reaction. Zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus copper solid. Imagine this is the reaction which I'm writing. Okay. My dear students, in this reaction, if I ask you, what is the charge here on zinc? 0. What is the charge here on copper? +2. What is the charge here on zinc? +2. What is the charge here on copper? 0. Is the oxidation state of zinc increasing or decreasing? 0 to +2, increasing. Increase in the oxidation state is what you call as oxidation. So I would say the zinc is undergoing oxidation. If zinc is undergoing oxidation, it is going to lose electrons. It is going to lose electrons, number one. Number two, the one that undergoes oxidation would be called as the reducing agent. So this zinc here behaves like a reducing agent. Talk about copper. +2 to 0. +2 to 0. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as a reduction. So this copper dye positive here undergoes reduction. If it is undergoing reduction, it will be gaining electrons. This copper dye positive will be gaining electrons. And the one that undergoes reduction would be called as the oxidizing agent. Would be called as the oxidizing agent. Right? Number one. Let me take one more reaction. For example, people, you have got a reaction like this. H2 gas plus 2 times Ag positive aqueous. Let's say it gives 2 times H positive aqueous, and with that, for example, I'm writing 2 times Ag solid. With that, for example, I'm writing 2 times Ag solid. Now, in this reaction, for example, I have to check which one is my oxidizing agent and which one is my reducing agent. How do I check it? Understand. If I ask you what is the charge on this hydrogen here? 0. What is the charge on this silver here? +1. Charge on this hydrogen? +1. Charge on silver here? 0. So what is happening to the oxidation state of hydrogen? Is it increasing or decreasing? 0 to +1. 0 to +1. Increase. Increase in the oxidation state is what we call as oxidation. So H2 is undergoing oxidation. The one that undergoes oxidation, it is going to lose electrons. The one that's undergoing oxidation, I would be calling it as a reducing agent. H2 is the reducing agent here. H2 is the reductant here. Now similarly, +1 to 0, +1 to 0, +1 to 0, decrease in the oxidation state. Decrease in the oxidation state is what I call as reduction. So Ag positive is undergoing reduction. If it is undergoing reduction, it's going to gain electrons. If it is undergoing reduction, it's going to be called as the oxidizing agent. Simple. Right? It's going to be called as the oxidizing agent. Simple. Perfect. Perfect, people. Let me take a few more examples so that it becomes properly clear to you. For example, I've got the reaction like this. MnO4 negative plus Sn di positive. For example, it gives Mn di positive plus Sn plus 4. Let's say this is the reaction. I need to identify which one is my oxidizing agent and which one is my reducing agent. First of all, I'll be calculating the oxidation state of this manganese over here. When you calculate, it will come out to be plus 7. X minus 2, 4 minus 1. So plus 7. Oxidation state of tin here, plus 2. Oxidation state of manganese here, plus 2. Oxidation state of tin here, plus 4. Now understand. Plus 7 to plus 2. Plus 7 to plus 2. What is happening? Decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. But understand, I won't say manganese is undergoing reduction. I won't say manganese is undergoing reduction. I'll say the whole compound is undergoing reduction. MnO4 negative is undergoing reduction. The one that undergoes reduction, that's called as oxidizing agent, which will be gaining electrons. Similarly, plus 2 to plus 4, increase. Increase in the oxidation state is what you call as oxidation. So I would say this Sn di positive is undergoing oxidation. The one that undergoes oxidation will be called as the reducing agent. Simple and basic. For example, let's say we have got the reaction like this. Cr2O7 di negative plus C2O4 di negative. Let's say it gives chromium tripositive. With chromium tripositive, we have got carbon dioxide as well. Let's say this one reaction, which I wrote over here. Now, first thing, I will be calculating the oxidation state of chromium here, right? So it's going to be 2x minus 2 into 7 is equal to minus 2. So the value comes out to be plus 6. Oxidation state of carbon here, when you calculate 2x minus 8 is equal to minus 2, it will be plus 3. Oxidation state of chromium here, plus 3. Oxidation state of carbon here, plus 4, right? Now check what is happening. Plus 6 to plus 3. Plus 6 to plus 3. Decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. So this overall species here is undergoing reduction. The one that undergoes reduction is my oxidizing agent. Similarly, plus 3 to plus 4. Increase in the oxidation state. Increase in the oxidation state is what we call as oxidation. So this oxalate ion is undergoing oxidation. The one that undergoes oxidation would be called as a reducing agent. As simple as that. So this is how you are going to identify which one is the oxidizing agent, which one is the reducing agent, right? Now, my dear students, there is a concept here. What concept exactly? How do we identify the nature of the compound? How do we identify the nature of the compound? For example, I'm giving you a compound. I'm giving you just a compound like H3PO4. I'm telling you, check whether this is oxidizing agent, whether it's reducing agent, or it's both. For example, I'm giving you KMnO4. I'm asking you to check whether it is oxidizing agent, reducing agent, or can behave like both, oxidizing, reducing. Right? How do we exactly do that? How do we exactly do that? How do we exactly check the nature of the compound? Understand what I'm going to say. My dear students, first of all, you're supposed to calculate the oxidation state of central atom. This will be your first step. This will be your first step. To calculate the oxidation state of central atom. For example, I've got a compound H3PO4. I need to check whether it's oxidizing agent, reducing agent, or it can behave like both. So my first thing is, what is the oxidation state of carbon in CO2? Plus 4. Did I write anything else? It's plus 4, right? Okay. So, for example, I have got a compound H3PO4. I need to check its nature. I need to check whether it can behave like oxidizing agent only. It can behave like reducing agent only. It can behave like oxidizing as well as reducing agent. See, the steps which we need to do. The first step, we are supposed to calculate the oxidation state of the central atom, right? We are supposed to calculate the oxidation state of central atom. Okay. My dear students, first case which arises here. If the oxidation state of central atom, or let me write it like this. If the central atom is present, in its maximum oxidation state already, if the central atom is present in its maximum oxidation state, what does that mean? What does that mean? You have got a compound. You have calculated oxidation state of the central atom in that compound. If by chance the central atom is present already in its maximum oxidation state, that means Central atom is present in its maximum oxidation state. That means it cannot further increase its oxidation state. If it cannot further increase its oxidation state, it cannot undergo oxidation. If it cannot undergo oxidation, it cannot behave like the reducing agent. It cannot behave like the reducing agent. So it will be only behaving as the oxidizing agent. Case number 1. I hope you got this point. I hope you got this point. Right? Second, if the central atom is present, in its lowest possible oxidation state, if in the compound central atom is present in its lowest possible oxidation state, what does that mean? That means it cannot further decrease its oxidation state. It's already present in lowest possible oxidation state. It cannot further decrease its oxidation state. If it cannot decrease its oxidation state, it cannot undergo reduction. If it cannot undergo reduction, it cannot behave like the oxidizing agent. It cannot behave like the oxidizing agent. It will only behave as the reducing agent. Okay? It will only behave as the reducing agent. Perfect. Now the third case. If the central atom is neither present in lowest possible oxidation state nor present in highest possible oxidation state. Imagine the central atom is present in the intermediate oxidation state. If the central atom is present in the intermediate oxidation state, that means it's not present either in lowest possible nor in highest possible oxidation state. So what does that mean? If you have got a compound wherein the central atom is neither present in lowest possible oxidation state nor present in highest possible oxidation state, it is at the intermediate state. That means if it is at the intermediate state, that means it can increase its oxidation state as well. It can decrease its oxidation state as well. When it increases its oxidation state, it is going to undergo oxidation, so reducing agent. When it decreases its oxidation state, it is going to undergo reduction, so oxidizing agent. So in that particular case, I would say the compound can behave both as oxidizing as well as a reducing agent, right? And remember, that particular compound in which the central atom is present in the intermediate state, we can say that particular compound can undergo disproportionation. What is disproportionation? You'll understand that in some time. But before that, I would want you guys to remember this scenario over here. Okay? Let me know once the chats, if it is clear, then I'll show you its application part as well. I'll show you how exactly you are going to identify the nature of the compounds. Let me know once in the chats quickly if all of this is super clear to everyone. Quickly, people. Everybody. Everyone. Mariam, this is going to be enough. One DPP I'll be providing in the Telegram. Just solve that. Nothing else. Perfect. I hope this particular diagram is clear. Now, let's try to solve certain questions. And I believe you should be in a position to solve these questions on your own. The compound that can act both as oxidizing and reducing agent. So which of the following compound can act both as oxidizing as well as a reducing agent? Well, the first compound that is given to us is H3PO4. Okay. Is H3PO4 in which the central atom is phosphorus. Here the central atom is nitrogen. Here the central atom is sulfur. Here the central atom is oxygen. Right? Phosphorus is your group 15 element. You should know it. Nitrogen is group 15. Sulfur is group 16. And sulfur here is group 6. Oxygen here is group 16. Right? I identified their groups. We know it. Nitrogen family is group 15. Oxygen family is group 16. Right? So, if you remember, I already gave you one range of oxidation state for P block elements. Group number minus 18. Group number minus 18. So 15 minus 18 is minus 3. Till group number minus 10. Group number minus 10. So 15 minus 10 is plus 5. This is the range of oxidation state for all the group 15 elements. This is the range of oxidation state for all the group 15 elements. Now, what is the range of oxidation states for group 16 elements? What is the range of oxidation states for group 16 elements? So it's group number minus 18. So minus 2 to plus 6. Similarly, minus 2 to plus 6. I calculated the range of oxidation states for all these atoms over here. Now, my dear students, tell me one thing. Tell me one thing. This phosphorus, can you calculate its oxidation state here? When you calculate, it's plus 5. Nitrogen in plus 3. Sulfur in plus 4 when you calculate it. Oxygen in hydrogen peroxide minus 1. So phosphorus here is in plus 5 oxidation state. Phosphorus here is in plus 5 oxidation state. And plus 5 is the maximum oxidation state of phosphorus. So phosphorus is present in its maximum oxidation state. It cannot further increase it. It cannot undergo oxidation. It cannot behave like the reducing agent. So it is going to only behave as the oxidizing agent. Okay, number 1. Nitrogen in plus 3. Nitrogen in plus 3. The minimum for nitrogen is minus 3. The maximum for nitrogen is plus 5. And nitrogen here is in plus 3. So plus 3 is the intermediate oxidation state of nitrogen. Intermediate. Plus 3 is the intermediate oxidation state of nitrogen. So it can increase as well as decrease. So it can behave both oxidizing as well as a reducing agent. Sulfur here, plus 4. For sulfur, minimum possible is minus 2, maximum is plus 6. And sulfur here is in plus 4. Plus 4 is the intermediate oxidation state. It can decrease as well as increase. So it can behave oxidizing as well as reducing. Oxygen here is in minus 1. Minus 1. Minimum oxidation state of oxygen is minus 2, maximum is plus 6. And oxygen here is a minus 1. So it can decrease as well as increase. So it can also behave oxidizing agent as well as a reducing agent. The question was the compound that acts both oxidizing as well as a reducing agent. B, C, and D. These are the compounds which act both oxidizing as well as a reducing agent. I hope this is clear. Now, identify the nature of the following. I'm going to erase this part because I believe this is clear. Okay? Identify the nature of the following compounds. You have to identify the nature of the following. You have to check whether these compounds are oxidizing agents, reducing agents, or both. Oxidizing agents, reducing agents, or both. Let me show them. Okay, understand guys. First of all, identify your central atom, which you identified here. When you calculate the oxidation state of chlorine here, it will be plus 7. Oxidation state of manganese here, it will be plus 7, right? Oxidation state of nitrogen here, when you calculate, plus 3. Oxidation state of chromium here, when you calculate, plus 6. With the help of formula, we know it. How do we calculate, right? Now, chlorine. Chlorine. If you talk about chlorine, chlorine is group 17. If it is group 17, so what is the range here? Group number minus 18. So 17 minus 18 is minus 1. 17 minus 10 is plus 7. Correct? Similarly, if you talk about manganese, do you remember I gave you the highest possible oxidation state of manganese already? Manganese is a D block element, right? N minus 1 D plus NS. What was the highest possible oxidation state of manganese? It was plus 7. It was plus 7 if you remember. Nitrogen is group 15 element. If nitrogen is group 15, what is the range of oxidation state for nitrogen? It is going to be minus 3 to plus 5, right? Chromium. Chromium, again D block element. Highest possible oxidation state of chromium, we already checked. That is plus 6. Okay. Now here, chlorine is in plus 7 oxidation state. Maximum oxidation state of chlorine is already plus 7. So I would say chlorine is in maximum oxidation state already. It cannot further increase its oxidation state. It cannot undergo oxidation. It cannot behave like the reducing agent. So it is only going to behave like the oxidizing agent. Number 1. Manganese here is in plus 7. And plus 7 is the maximum oxidation state of manganese. So manganese here is in maximum oxidation state, right? So it cannot increase further. It cannot undergo oxidation. So it cannot behave like the reducing agent. So only it is going to behave like the oxidizing agent. I hope you are getting all this. Nitrogen, plus 3. Plus 3 is the intermediate state of nitrogen. It can increase also, it can decrease also. So oxidizing agent as well as reducing agent. Perfect. Chromium here is in plus 6. So chromium is already in maximum. It cannot increase. It cannot undergo oxidation. It cannot behave like the reducing agent. So only like the oxidizing agent. So this is how you identify the nature of the compounds. If this is clear, let me know once in the chats quickly. If this is clear, let me know once in the chats quickly, people. Everyone in the chats quickly. Yeah? Everyone in the chats quickly. Look at these questions. Now, these questions you should be in a position to solve on your own. Which of the following can act both as oxidizing and reducing? Oxidizing and reducing. Calculate the oxidation state of oxygen here, -2. Oxygen here in hydrogen peroxide, -1. Chlorine, -1. Sulfur, -2. Now, which of the following compound is there which can act both as oxidizing as well as reducing? If you see, someone is saying manganese +7. Wait, +6. What did I write? Wait. We did a mistake, guys, here. We did one mistake here. This is not KMnO4. This is K2MnO4. In K2MnO4, when you calculate its oxidation state of manganese will come out to be +6. Right? And +6. That is the intermediate oxidation state of manganese. So +6 to +7. So it can increase as well as decrease. So it can be oxidizing agent as well as a reducing agent. Right? Just modify this. I thought this was KMnO4. That's why I wrote +7. But it is K2MnO4, where the oxidation state of manganese is +6. Perfect. All right, look at this particular question now. Since I calculate the oxidation state of oxygen here, can I say oxygen is already present in its least possible oxidation state? So it cannot further decrease. It cannot undergo reduction. It cannot behave like oxidizing agent. So it can only behave like reducing agent. Here oxygen is a -1, intermediate. So it can decrease as well as increase. So it can behave both. Chlorine here is in lowest possible oxidation state. It cannot decrease. So it cannot be the answer. Sulfur here is in lowest possible oxidation state. So it cannot decrease. It cannot be the answer. So only compound which acts both oxidizing as well as reducing agent here is H2O2. Right? Perfect, guys. I hope I'm clear with this. Now, which of the following cannot undergo disproportionation? What is disproportionation, first of all? Let me give you the idea of the disproportionation, because in this particular chapter only, I'll teach you disproportionation in detail. But right now, let me give you a slight idea of disproportionation. See, let's say you got the reaction like this. A2 gives A positive plus A negative. Let's say this is the reaction. A2 gives A positive plus A negative. Now, if you see oxidation state of A is 0 here, here it is +1, here it is -1. Okay? If you see 0 to +1, increase, 0 to -1, decrease. Can I say oxidation state of same element is increasing as well as decreasing simultaneously? So my dear students, oxidation state of A is increasing as well as decreasing simultaneously. Whenever you see such kind of the compound, in which oxidation state of same element increases as well as decreases simultaneously, we say that species undergoes disproportionation. And here we have to check. Which of the following cannot undergo disproportionation? Can you give it a try on your own? राकिब, इस चैप्टर को मैं 10 घंटे देता हूं, ठीक है? बाकी टीचर्स में भी 3 घंटे में करते होंगे, मैं 3 घंटे में नहीं, मैं डिटेल में पढ़ाता हूं. बैठना है बैठो, नहीं बैठना है बाहर जाओ. Which of the following cannot undergo disproportionation? Quickly, people, everybody. You should be in a position to answer this question. Mariam, Cl shows minimum -1, not -2. So majority is saying option D. So exactly, you all are perfectly right here. So how exactly you calculated? You solved this particular question. I believe you would have calculated the oxidation states of these central atoms here, right? So oxidation state of chlorine here is +1. When you calculate, it's +3 here, it is +5 here, it is +7 here, right? These are the oxidation states of chlorine. Perfect. Now, my dear students, tell me one thing. Chlorine is group 17 element, you know it. And your group 17 elements, what is the range of oxidation states which they show? -1 to +7. -1 to +7. If you see chlorine here is in maximum oxidation state. If you see chlorine here is in maximum oxidation state. Chlorine here is in maximum oxidation state. So it cannot increase further. If it cannot increase further, it cannot undergo disproportionation. +1. +1 means intermediate. It can increase as well as decrease. +3. +3 again means intermediate. Increase as well as decrease. +5. +5 again means intermediate. It can increase as well as decrease. Right? So, for disproportionation to happen, element has to increase its oxidation state as well as decrease its oxidation state simultaneously. Right? So, I would say this one will undergo disproportionation. This one will also undergo. This one will undergo. This one will not undergo disproportionation here. I believe it's clear. Yeah? Is this question clear to everyone quickly? Yeah? Quickly in the chats with some fire emojis, people. Everybody. Everybody in the chats. Everybody in the chats. Everybody in the chats. We'll have the dinner break at 10. Okay? At 10, around that. Now, what kind of questions can be asked from oxidizing reducing agents? Further questions. There are a few things which I'm going to tell you over here. Sometimes you'll be asked a question. Which of the following is the better oxidizing agent? Which of the following is the better reducing agent? You might have seen those questions as well. How do you solve them? Let me tell you. You'll be sometimes asked to check which of the following is the better oxidizing agent. Right? Better oxidizing agent. Better oxidizing agent. Sometimes you'll be asked to calculate, you check. Sometimes you'll be asked to check which of the following is the better reducing agent. Perfect. Right, guys? How exactly do you identify them? So I'll just write strength of the oxidizing agent or strength of the reducing agent. Or let me write completely so that you won't get confused afterwards. I'll write strength of the oxidizing agent. Strength of the oxidizing agent is directly proportional to the oxidation state of the central atom. Number 1. Strength of the reducing agent. Strength of the reducing agent is inversely proportional to the oxidation state of the central atom. Number 2. Sometimes you'll be asked a question on strength of oxyacids. Strength of oxyacids. Strength of an oxyacid is also directly proportional to the oxidation state of the central atom. Right? Strength of oxyacid is also directly proportional to the oxidation state of the central atom. So these are few important points which you are going to remember directly. And if you remember them directly, we are done. We can easily solve different basic questions over here. Okay? So remember first of all these 3 points which I gave you. Remember these points which I gave you. Now people, let's have a look on the set of the questions which I have come up with. In the first question, you have to check which of the following is the better oxidizing agent. Which of the following is the better oxidizing agent? Can you check it now? Better oxidizing agent. What is the thing which you'll be doing? You'll be calculating the oxidation states of these central atoms. Right? I believe you can easily calculate oxidation states of these central atoms. Have a look. Nitrogen. Here will be in -2 oxidation state when you calculate. Here it's going to be 0. Right? What is the oxidation state of nitrogen here? It's going to be +1. Oxidation state of nitrogen here, +2. Oxidation state of nitrogen here, +3. Oxidation state of nitrogen here, +4. Oxidation state of nitrogen here, +5. You know, strength of oxidizing agent is directly proportional to oxidation state of central atom. More the oxidation state of the central atom, better the oxidizing agent. So this is the order. This is the order. Similar question second. On the basis of strength of oxidizing agent, right? Calculate the oxidation state of manganese here, +6. Sorry, this is +7 here. Calculate the oxidation state of manganese here. It is +6. Oxidation state of manganese here, +4. Oxidation state of manganese here, +3. Oxidation state of manganese here, when you calculate +2. With the help of formula, right? Now, you know, more the oxidation state of the central atom, better the oxidizing agent. So this is the order. Look here. Nitrogen is in +5 oxidation state when you calculate. Chromium here is in +6. Nitrogen is in +7. More the oxidation state on the central atom, better the oxidizing agent. Right? Strength of acid. Calculate oxidation states of the central atoms. This is +7. This is +5. This is +3. And this is +1. More the oxidation state on the central atom, more the strength of the oxy acid. More the strength of the oxy acid. Among these two, better reducing agent. Oxidation state of nitrogen here, -3. Oxidation state of sulfur here, -2. Right? Reducing agent and oxidation state, inversely. Lesser the oxidation state, better the reducing agent. Lesser the oxidation state, better the reducing agent. They're inversely. Right? Now, this particular question. Oxidizing agent. Oxidizing agent. +7, +5, +3, +1. Perfect. So, which should be the better oxidizing agent? This should be the better oxidizing agent. Remember it as the exception. This is not the better. This one is the better oxidizing agent. Remember this question as an exception, which will be discussed in P block elements in detail. Remember it for now as an exception. Remember it for now as an exception. Okay? All clear? All clear, people? Strength of acid. Strength of acid. Strength of acid. Which one will be stronger acid here? Again, oxidation state of the central atom. More the oxidation state of the central atom, stronger the acid. So which one is going to be the stronger acid here? I think this one. Right? Because nitrogen is in +5 oxidation state. Right? Now this particular question, this again you are going to remember as an exception only. Right? It's the reason I'll be giving you in resonance. See, normally what should be the order? Strength of acid is directly proportional to oxidation state of the central atom. Right? Strength of acid is directly proportional to what? Is directly proportional to oxidation state of the central atom. Here, +5. Right? This is +5. Perfect. This is +3. Right? Is it +3? Yes. This one is +1. So this one should be stronger acid here. But it is not the stronger acid. The order again here is reverse. You are again going to remember this as an exception for now. Its actual reason lies in resonance, which will be discussed in the P block elements. So these two exceptions here, I would want you guys to remember properly, people, from now on. Am I clear till here? Am I clear till here, people? Am I clear till here? Yes? Perfect. Remember it. Remember it. Let me know once the chats quickly, if all the things are clear till here. Okay, there are two exceptions which I would want you guys to remember. This is one. This is one more, which I have highlighted over here. So remember them. Remember them. Application slide, someone is asking. This is the application slide. Strength of oxidizing agent directly proportional to oxidation state of central atom. Strength of reducing agent inversely proportional. Strength of oxy acid directly proportional to oxidation state of the central atom. Similarly, strength of the base inversely proportional to. You can write one more here. You can write one more here. Strength of a base, here you can say, is inversely proportional to oxidation state of the central atom. You can modify this, right? Write one more like this. I hope I'm clear with this. I hope I'm clear with this. So this was your oxidizing agent, reducing agents, and its application part. Now we are going to come into one more topic, which is a very, very, very important topic, that is concept of equivalent mass. Okay, concept of equivalent mass. Let me know once in the chats whether you have discussed this particular concept or not. See, in oxidizing and reducing agents, all the types of the questions I've shown you. Structures, all the types of the structures I've shown you, right? Anything can be asked out of those. Rules, everything is discussed in detail, right? Now it is the time for the equivalent mass to be done and dusted in detail. But before that, let me know once in the chats, everybody, if we are done. How to find the central atom? Did you not watch the chemical bonding lecture of mine, which I took the last? Do you know Mohit sir from NIT? Which Mohit sir? Are you talking about Mohit Riyan? Perfect. Let's have a look on the concept of equivalent mass now. What this equivalent mass exactly is all about? How do we calculate equivalent mass? This is a big topic here. It might take some 2.5 hours, right? You should know it. You should know it, people. Perfect. Equivalent mass, one of the super important topics of this particular chapter. And we are going to have a detailed look on the equivalent mass concept now. See guys, if I first of all would want to define the equivalent mass, let me tell you, equivalent mass is defined as, it is defined as that mass of substance in grams which can combine or displace either 1 gram of hydrogen, or 8 grams of oxygen, or 35.5 grams of chlorine, or 108 grams of silver, or 80 grams of bromine. 80 grams of bromine. This is the simplest definition of what? This is the simplest definition of the term equivalent mass. That mass of the substance in grams which can combine or displace either 1 gram of hydrogen, 8 gram of oxygen, 35.5 grams of chlorine, 180 grams of silver, or 80 grams of bromine. Now what it means exactly? Let's have a look on its meaning. Then I'll show you different types of questions which can be asked from the definition part. Right? See people. For example, I'm writing a reaction here. A reaction is pretty much simple. Let's say I'm writing N2 gas plus 3 times H2 gas. Right? You know it gives 2 times NH3 gas. This is one balanced chemical equation that I wrote over here. One balanced chemical equation. Okay. Balanced chemical equation. Now, my dear students, imagine that I need to calculate equivalent mass of nitrogen here. For example, I need to calculate equivalent mass of nitrogen. First thing, in order to calculate equivalent mass of nitrogen, what do I need? In order to calculate equivalent mass of nitrogen, what do I need? Understand one thing. In this reaction, nitrogen is combining with what? Nitrogen is combining with hydrogen. Nitrogen in the reaction is combining with hydrogen. So I am going to calculate equivalent mass of nitrogen with respect to what? With respect to hydrogen. And when you calculate equivalent mass of a substance with respect to hydrogen, you calculate it with respect to 1 gram of hydrogen. So basically, as per the definition, I am going to check that mass of nitrogen which has combined with 1 gram of hydrogen. And that mass of nitrogen which would have combined with 1 gram of hydrogen, that's what I'll be calling as equivalent mass of nitrogen. Understand what exactly? See, first of all, if I ask you, what is the molar mass of H2? You know molar mass of H2 is 2 grams. That means mass of 1 mole of H2 is 2 grams. Therefore, mass of 3 moles of H2 is going to be 6 grams. So I'll write 6 grams of hydrogen. 6 grams of hydrogen. Tell me one thing. What is the molar mass of N2? Molar mass of N2 will be 28 grams. That means mass of 1 mole of N2 is 28 grams. That means mass of 1 mole of N2 is 28 grams. So I'll write 28 grams of nitrogen. So what is meant by this particular statement? I'm simply using stoichiometry. From stoichiometry, I got to know 6 grams of hydrogen are combining with 28 grams of nitrogen. Therefore, 1 gram of hydrogen. Therefore, 1 gram of hydrogen combines with 28 divided by 6 grams of nitrogen. 1 gram of hydrogen combines with 28 divided by 6 grams of nitrogen, which simply comes out to be 14 divided by 3 grams of nitrogen. Now, if you look carefully, what is this particular term? What does it mean? I would say this is the mass of nitrogen that has combined with. This is the mass of nitrogen that has combined with 1 gram of hydrogen. And as per the definition, that mass of substance in grams which can combine with 1 gram of hydrogen, that's what you call it the equivalent mass. So I would say this is nothing but it is the equivalent mass of nitrogen. It is that mass of nitrogen which has combined with 1 gram of hydrogen. And that mass of substance which combines with 1 gram of hydrogen, what do you call that as? Equivalent mass. So I calculated equivalent mass of nitrogen here as 14 by 3 grams. Am I clear with this? Am I clear with this? For example, let me take one more reaction so that it becomes properly clear to you. Let me take one more reaction. This is a reaction, guys, which I'm taking over here. For example, I need to calculate equivalent mass of magnesium here. Let's say I need to calculate equivalent mass of magnesium. First of all, look carefully. Magnesium is combining with what? Magnesium is combining with oxygen. So, in order to calculate equivalent mass of magnesium, I'll be taking oxygen in reference. And how many grams of oxygen? I'll be taking 8 grams of oxygen in reference. I'll be taking 8 grams of oxygen in reference. Have a look how. Have a look how. See, guys. First of all, let's use the stoichiometry. First of all, what is the molar mass of O2? Molar mass of O2 is 32 grams. That means mass of 1 mole of O2 is 32 grams. Do I have 1 mole of O2 or half mole of O2? I have half mole of O2. If the mass of 1 mole of O2 is 32 grams, therefore mass of half mole of O2 will be 16 grams. So I'll write just 16 grams of oxygen. Now tell me, what is the molar mass of magnesium? Molar mass of magnesium is 24 grams. Therefore, mass of 1 mole of magnesium is 24 grams. So I'm writing 24 grams of magnesium. My dear students, how do you read this statement as per stoichiometry? I can say 16 grams of oxygen have combined with 24 grams of magnesium. Now we use the unitary method. Therefore, 1 gram of oxygen, 1 gram of oxygen has combined with 24 divided by 16 grams of magnesium. As per the definition, I would say 8 grams of oxygen, 8 grams of oxygen would have combined with 24 divided by 16 multiplied by 8. Value comes out to be 12 grams of magnesium. So what does it mean exactly? What does it mean exactly? What does it mean exactly? I would say this is basically the mass of magnesium. This is the mass of magnesium that has combined with 8 grams of oxygen. And as per definition, that mass of substance which combines either with 1 gram of hydrogen or 8 grams of oxygen, what do we call that as? Equivalent mass. So this 12 grams is basically the equivalent mass of magnesium here. So it is the equivalent mass of magnesium here. Perfect. So this is the definition. This is the definition here. Right? Right, people? Simple and basic. Okay. Now see what kind of questions can be asked from the definition. I'm just teaching you the definition right now. Let's exactly see what kind of questions can be asked from the definition part. Look here. This is one of the asked questions. One of the asked questions. How do you solve these sort of questions? Sulfur forms two compounds, S2Cl2 and SCl2. Equivalent mass of sulfur in this compound is given. Equivalent mass of sulfur in SCl2 is to be calculated. See guys, what you need to do exactly. We are supposed to calculate equivalent mass of sulfur in SCl2. Okay. So let me write the reaction. SCl2. SCl2, right? Well, I do not know in which form sulfur was taken. I do not know. So I'll write the reaction directly in atomic form. I'll write the reaction directly in atomic form. 1 atom of sulfur plus 2 atoms of chlorine. I wrote the reaction in atomic form directly. Perfect. This is the easiest way of solving the question. Now, my dear students, as per the question, I need to calculate equivalent mass of sulfur in SCl2. I need to calculate equivalent mass of sulfur in SCl2. Perfect. So, if you look carefully, I will be calculating equivalent mass of sulfur with respect to what? Chlorine. And when you make chlorine as the reference, you have to make 35.5 grams of chlorine as per the reference. You have to make 35.5 grams of chlorine as per the reference, as per the definition. Okay, now have a look what it means. First of all, what is the molar mass of Cl? Molar mass of Cl is 35.5 grams. Therefore, mass of 1 mole Cl is 35.5 grams. How many moles of Cl we have? 2 moles. So 35.5 multiplied by 2, 71 grams. So I would say 71 grams of chlorine combines with. What is the molar mass of this sulfur? Molar mass of sulfur is 32 grams. So mass of 1 mole of sulfur is basically 32 grams. So I'll just write 32 grams of sulfur. Correct? So I can say 71 grams of chlorine combines with 32 grams of sulfur. Therefore, using unitary method, 1 gram of chlorine combines with 32 divided by 71 grams of sulfur. As per the definition, 35.5 grams of chlorine combines with 32 divided by 71 multiplied by 35.5 grams of sulfur. When you solve this one, this is 2, the value comes out to be 16 grams of sulfur. Now check what did we calculate. My dear students, we calculated that mass of sulfur which combines with 35.5 grams of chlorine. As per definition, that mass of sulfur which combines with 35.5 grams of chlorine, what do I call that as? We call that as equivalent mass. So this is the equivalent mass of sulfur. I believe I'm clear. Yes? Perfect. Perfect, people. Let's have a look on one more question. Can you solve this? Look carefully. As per the question, SO3 contains 32% oxygen by mass. SO3 contains 32% oxygen by mass. What does that mean? What does that mean? Can you let me know its meaning? SO3 contains 32% oxygen by mass. What does that mean? That means, as per the definition, I can say 100 grams of SO3. It means that 100 grams of SO3 contains 32 grams of oxygen. This is what it means. 100 grams of SO3 contains 32 grams of oxygen. Right? 100 grams of SO3 contains 32 grams of oxygen. So, I would say the mass of the entire compound is 100 grams. And 100 grams of SO3 contains how many grams of oxygen? It contains 32 grams of oxygen. If it contains 32 grams of oxygen, so what is the mass of sulfur then? 100 minus 32 is 68 grams. Correct? So what we got to know exactly from this data? What we got to know? Why was S2Cl2 given in the last question? Just to confuse you, nothing else. Okay? See, my dear students, from this particular data, I'm getting to know one thing. That 32 grams of oxygen have combined with 68 grams of sulfur. Therefore, 1 gram of oxygen has combined with 68 divided by 32 grams of sulfur. As per the definition of equivalent mass, I would say 8 grams of oxygen would have combined with 68 divided by 32 multiplied by 8. 8, 1, 8, 4. So 68 divided by 4 comes out to be 17 grams of sulfur. So what does it mean? Have a look properly. I would say this is the mass of sulfur. This is the mass of sulfur which has combined with 8 grams of oxygen, and that mass of substance which combines either with 1 gram of hydrogen or 8 grams of oxygen. What do you call that as? Equivalent mass. So this is the equivalent mass of sulfur here, which I was supposed to calculate. Right? This is the equivalent mass of sulfur. Have a look on one more question. Have a look on one more question, people. Have a look on one more question. 0.84 grams of metal hydride. So we have got metal hydride. Let the formula of metal hydride be MxHy. Now, as per the question, they are mentioning one thing. 0.84 grams of metal hydride. So this is the mass of entire metal hydride. Contains 0.04 grams of hydrogen. 0.84 grams of metal hydride contains 0.04 grams of hydrogen. So what will be the mass of metal then? This minus this. So I would say it's going to be 0.80 grams. Okay. Now people understand. Now understand. From this particular data, what can we conclude? We can say one thing. From this data, we got to know one thing. 0.04 grams of hydrogen. 0.04 grams of hydrogen. How combined with 0.80 grams of metal. 0.04 grams of hydrogen have combined with 0.80 grams of metal. Now people, use the unitary method. If 0.04 grams of hydrogen have combined with 0.80 grams of metal, therefore 1 gram of hydrogen would have combined with 0.8 divided by 0.04 grams of metal. When you calculate it, I think this value comes out to be 20 grams of metal. So what is the meaning of this 20 grams of metal? I would say this is the mass of metal. This is the mass of metal which has combined with 1 gram of hydrogen, and that mass of substance which combines with 1 gram of hydrogen. What do you call that as? Equivalent mass. So this is the equivalent mass, people. Right? Yes? Right, people? Yeah? Is it clear? Absolutely. 20 grams is the answer of the question. Perfect. Let me slightly change the question. Can you solve this one on your own? Slightly, people. Slight change. As far as this particular question is concerned, 74.5 grams of metallic chloride. You are given with metallic chloride. How many grams of metallic chloride you are given with? You are given with 74.5 grams of metallic chloride. 74.5 grams of metallic chloride contains 35.5 grams of chlorine as per the question. This is the mass of entire metallic chloride. This mass of entire metallic chloride contains 35.5 grams of chlorine. So how many grams of metal will be there? This minus this. So it will be, I believe, 39 grams. The question is done here only. You are not supposed to do anything here. We got to know one simple thing. We got to know 35.5 grams of chlorine as combined with 39 grams of metal. What is the definition of equivalent mass? Equivalent mass. This is the mass of metal. We got to know this is the mass of metal that is combined with 35.5 grams of chlorine. And that mass of substance which combines either with 1 gram hydrogen or 8 grams oxygen or 35.5 grams of chlorine. What do we call this as? Equivalent mass. So this is the equivalent mass of metal directly, 39 grams. Done and dusted. Nothing else. Nothing else. Right? Look at this particular question. Look at this particular question. X grams of metal. X grams of metal gives what? Gives Y grams of metal oxide. Gives Y grams of its oxide. This is given in the question, people. Understand. X grams of metal gives Y grams of metal oxide. We have to calculate equivalent mass of metal. How? Simple, guys. It's very simple. Just think over them. Think over this stuff. And these are simple questions which are asked in your NEET JEE mains examinations, right? Yeah. Check. So as per the question, X grams of the metal gives Y grams of metal oxide. So we are given with Y grams of metal oxide, right? We are given with Y grams of metal oxide. So mass of this entire metal oxide is Y grams. Now, mass of the metal oxide, no doubt, is Y gram. And mass of the metal is how much? X gram. Mass of the metal is X gram. Mass of the metal is X gram, as per the question. Therefore, mass of oxygen will be Y minus X grams. Y minus X grams. This is the mass of oxygen. Correct? This is the mass of oxygen. Now we are almost done. Can I say Y minus X grams of oxygen? We got to know Y minus X grams of oxygen. How combined with X grams of metal? How combined with X grams of metal? Therefore, 1 gram of oxygen. Therefore, 1 gram of oxygen has combined with X divided by Y minus X grams of metal. As per the definition, 8 grams of oxygen would have combined with X divided by Y minus X multiplied by 8 grams of metal. Now understand what it means. What did we calculate? Check it out. What did we calculate? Check it out. I would say this particular term, 8x divided by y minus x. This is the mass of metal which is combined with 8 grams of oxygen. As per the definition, that mass of substance which combines with 8 grams of oxygen, what do I call that as? Equivalent mass. So this 8x divided by y minus x is basically the equivalent mass of metal, which is 8x divided by y minus x grams. These can be different questions which can be asked from the definition of the equivalent mass. I believe this is super clear to everyone. Yes? Is it, people? Is it clear to everyone? Tell me. This was the definition. Now we are going to go into the details. This was the definition. Now we are going to go into the details. So before that, before going into the details, tell me once in the chats if all the things are super clear to you or not. Quickly. Yeah? Sir, NH3 is better reducing the agent than H2S. See, in NH3, oxidation state of nitrogen is -3. In H2S, it is -2. Lesser the oxidation state on the central atom, better the oxidizing agent. So NH3 is more oxidizing, better oxidizing agent than H2S. Yes, you're right. I hope this particular stuff is clear. Okay, let's move on now and let's get into the details of this equivalent mass. My dear students, till now, I was just showing you how do we calculate equivalent mass of certain substances with the help of definition. Now, all the time, you are not supposed to use the definition. All the time, you are not supposed to use the definition. You can use a simple formula to calculate equivalent mass. What is that formula exactly? Let's have a look. I'm writing the formula. See, I can say equivalent mass. Equivalent mass of the substance is always equal to molar mass of the substance divided by molar mass of the substance divided by n factor of the substance. Or you can call the n factor as valency factor of the substance as well. This is one general formula which you are going to remember from now onwards, and it is a super important formula, guys. Okay? Equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the substance. Now the point is, this is something which you already know. Molar mass of certain substances you can already calculate, right? How do we calculate n factors of the substances? That is the discussion now. And that is something important. See, guys. So here, I'm going to write the first thing. What is that? I'm writing n factor n factor of an element. N factor of an element. Remember, n factor of an element is nothing but valency of the element. N factor of the element is nothing but valency of an element. For example, I'm taking certain elements. Let's say we have got nitrogen. Okay. Let's say we have got nitrogen. Let's say we have got oxygen. Let's say we have got sodium. Let's say we have got magnesium. These are different elements which I've taken over here. Now, people, if I ask you, what is the valency of nitrogen? You will say valency of nitrogen is 3. What is the valency of oxygen? It is 2. Valency of sodium, 1. Valency of magnesium, 2. Whatever is the valency of the element, that's what you call as the n factor of the element. And if you got the n factor of the element, you can easily calculate its equivalent mass. So, if I ask you what is the equivalent mass of nitrogen, you will say as per formula, it is molar mass of nitrogen divided by n factor. Molar mass of nitrogen is 14 grams, n factor is 3. So, this is the equivalent mass of nitrogen. What is the equivalent mass of oxygen? Simple. Molar mass of oxygen divided by n factor. What is the equivalent mass of sodium? It is going to be molar mass of sodium divided by n factor. Similarly, what is the equivalent mass of magnesium? You will say it is molar mass of magnesium divided by n factor. Right? So, the first n factor, I believe it's clear. Right? N factor of an element is nothing but valency of an element. Okay? Valency of an element. This is the first point. Second point. That is n factor of an ion. N factor of an ion is nothing but magnitude of charge present on an ion. N factor of an ion is nothing but it is magnitude of charge present on an ion. Okay? N factor of an ion is nothing but magnitude of charge present on an ion. Let's say I'm taking certain ions here, Na positive. Let's say we have got Cl negative. Let's say we have got SO4 dinegative. Let's say we have got PO4 trinegative. These are different ions which I've taken over here. Right? Now tell me one thing. The charge on sodium here is +1. The charge on chlorine here is -1. The charge on sulfate here is -2. The charge on phosphate here is -3. What exactly you need to do? You need to take the magnitude of charge here, my dear students. What is the magnitude of charge here? It is +1. What is the magnitude of charge here? Again +1. Magnitude of charge here, 2. Magnitude of charge here, 3. And you know, magnitude of charge on ion is what we call as n factor of an ion. Magnitude of charge on an ion is what you call as n factor of an ion. So this is n factor of Na positive. This is n factor of Cl negative. This is n factor of SO4 dinegative. This is n factor of phosphate. Well, if you got the n factor of these ions, you can easily calculate their equivalent masses. So equivalent mass of sodium here, equivalent mass of Cl negative, equivalent mass of SO4 dinegative, equivalent mass of phosphate ion will be equal to molar mass divided by n factor, right? Molar mass divided by n factor. My dear students, remember one thing. By the presence of charge, nothing happens to molar mass. By the presence of charge, nothing happens to molar mass. Whatever is going to be the molar mass of sodium, same is going to be the molar mass of Na positive. Whatever is going to be the molar mass of chlorine, same is the molar mass of Cl negative. Whatever is the molar mass of SO4, same is going to be the molar mass of SO4 dinegative. So, by the presence of charge, nothing happens to molar mass. Remember this. So, equivalent mass of Na positive is equal to molar mass of sodium divided by its n factor, Cl negative. Molar mass of chlorine divided by its n factor. Molar mass of SO4 will be 96 divided by n factor, right? This will be molar mass 95 divided by n factor. So this is how you calculate equivalent mass of the ions. I believe it's clear to everyone. Yeah? Is it clear, people? So this was the n factor calculation for an ion. Now, the third one. Third one is going to be n factor of a salt. If you have got the salt, how do you calculate its n factor? Let me tell you, n factor of salt is calculated by taking the LCM of charge on cation and the charge on anion. Charge on cation and the charge on anion. Or you can say one thing. N factor of a salt is basically the total cationic charge or total anionic charge. For example, understand. Let's say I'm taking certain salts here. Let's say you've got NaCl, right? One common salt this is. Perfect. Let's say you've got KCl. One more. Perfect. Let's say you've got MgCl2. Right? Let's say you've got AlCl3. Right? Let's say you've got Al2SO4 whole thrice. Perfect. Now, this is basically Na1Cl1. What is the charge on sodium? Just crisscross. Take this one here. Take this one here. Similarly, take this one here and take this one here. Take this 2 here. Take this one here. Take this 3 here. Take this one here. Take this 3 here. Take this 2 here. So you got the charges on cations and anions. You got the charges on cations and anions. Now, do one thing. Take the LCM of charge on cation and anion. It is 1. LCM of 1 and 1 is 1. LCM of 2 and 1 is 2. LCM of 3 and 1 is 3. LCM of 3 and 2 is 6. And you know, LCM of charge on cation and charge on anion gives you the N factor of the salt. Gives you the N factor of the salt, right? So, if I ask you, what is the equivalent mass of NaCl? You will say molar mass of NaCl, which is 58.5 grams, divided by its N factor. That's one, right? Perfect. Similarly, equivalent mass of KCl, you will say it is molar mass of KCl divided by its N factor. Similarly, equivalent mass of AlCl3 is going to be molar mass of AlCl3 divided by its N factor. Equivalent mass of Al2SO4 whole thrice is going to be what? Molar mass of Al2SO4 whole thrice divided by N factor. So this is how you calculate N factors of salts and eventually equivalent mass of salts. I believe this is clear. Yeah? I believe this point is also clear to everyone. Perfect view? Perfect. Quick. Quickly in the chats. So this is how you calculate N factor of what? N factor of salts. Now, moving on to N factor of acids. How do we calculate the N factor of acids? N factor of acids. People, let me tell you, N factor of acid is nothing but basicity of the acid. It is nothing but basicity of the acid. How do we exactly define basicity? Number 1. Number of H positives an acid donates. Number of H positives an acid donates. Number of OH negatives an acid accepts. Or number of lone pairs an acid accepts. These are the 3 ways by means of which we can define basicity of the acid. Okay? For example, let me take some simple acids, which you already know. HCl, H2SO4, HNO3, H3PO4. These are some simple acids, guys, right? For example, the question is asked, simple like this. What is the equivalent mass of HCl? No reaction given. No reaction is given, only the question is what is the equivalent mass of HCl? What is the equivalent mass of H2SO4? What is the equivalent mass of HNO3? What is the equivalent mass of H3PO4? No reaction is, for example, given in the question. At that point of time, there should be one thing in your mind. That means you are putting this HCl in water, right? So if no reaction is mentioned, that means you are putting all these acids into water. And when you put this acid into water, how many H positives it's going to donate? 1. How many H positives this is going to donate? 2. How many H positives this HNO3 is going to donate? 1. How many H positives this H3PO4 is going to donate? 3. And the number of H positives an acid donates, it defines the basicity of the acid. And whatever is the basicity of the acid, that's what you call its N factor. So N factor of HCl is 1. N factor of H2SO4 is 2. N factor of HNO3 is 1. N factor of H3PO4 is 3. Right? So these are the N factors of these acids. If you got these N factors of the acids, you can easily calculate their equivalent masses. Equivalent mass of HCl will be molar mass of HCl divided by its N factor. Right? Similarly, equivalent mass of H2SO4, molar mass of H2SO4 divided by its N factor. Right? Equivalent mass of HNO3, will be molar mass of HNO3 divided by its n factor. N factor is 1. Perfect. Similarly, equivalent mass of H3PO4, it will be molar mass of H3PO4 divided by its n factor, that's 3. So simply, whenever you're supposed to calculate n factor of an acid, right, you just need to calculate the basis T. And how do we define basis T? 3 ways are there to check basis T, right? 3 ways are there to check basis T. Perfect. And basis T gives you the n factor of the acid. Perfect. Now, there are few things which I want you guys to know about acids. Take a note of this. Take a note of this. Remember, my dear students, an acid donates only that H positive. An acid donates only that H positive which is connected, or I would say which is attached to more electronegative element. An acid donates only that H positive which is attached to more electronegative element like chlorine, oxygen, nitrogen. Why am I telling you this particular statement? Why am I telling you this particular statement? For example, I'm taking certain acids. Let's say I'm taking H3PO2. Let's say I'm taking H3PO3. Let's say I'm taking H3PO4. Let's say I'm taking H3PO5. Right? Now I'm asking you what is the n factor of H3PO2? Right? Normally, what should you say? You should say when you introduce this in water, it should give 3 H positives. This should also give 3 H positives. This should give 3. This should give 3. So n factor of all these species should be 3. But that's not the case here. That's the reason why I made you write that particular statement. An acid donates only that H positive which is attached to more electronegative element like chlorine, oxygen, hydrogen, or nitrogen. So, if you remember the structure of your H3PO2, already I gave you the structure of H3PO2. I hope you remember. In H3PO2, how many hydrogens do you see? 3 hydrogens, right? But out of these 3 hydrogens, how many hydrogens are attached to more electronegative element like oxygen? Only 1 hydrogen is attached. The more electronegative element, oxygen. And we know acid donates only that hydrogen in the form of H positive, which is attached to more electronegative element. So this acid in water is going to donate only 1 H positive, right? Similarly, H3PO3. H3PO3. If you remember its structure, I have already given this. Similarly, H3PO4. And H3PO5. H3PO5. People just try to understand one thing over here. In H3PO3, there are in total 3 hydrogen atoms. Out of 3 hydrogen atoms, 2 are attached to more electronegative. Over here, all the 3 hydrogen atoms are attached to more electronegative. Over here, again, all the 3 hydrogen atoms are attached to more electronegative element, like oxygen. Perfect. So people, just remember one thing. An acid donates only that hydrogen in the form of H positive, which is attached to more electronegative element, like oxygen. So this acid is going to donate 2 H positives. This acid is going to donate 3 H positives. This acid is going to donate again 3 H positives. And you know, number of H positives an acid donates, that defines its basis T. Number of H positives that an acid donates defines its basis T. And whatever is the basis T of the acid, that is something which you call as the N factor. So I would say N factor of H3PO2, it is 1. N factor of H3PO3, it is 2. N factor of H3PO4 is 3. Right? And N factor of this is also 3. Perfect. If you got their N factors, you can easily calculate their equivalent masses. How exactly? Molar mass divided by N factor. That's all. Is it clear, people? Is it clear? That it is butterfly structure. Which has butterfly structure? That is CrO5. I did not mention CrO5 anywhere. All clear, guys? All clear, all clear? All clear, quickly. I hope this is clear. Perfect. Now, related to acids, I'm giving you one more thing, one more important thing related to acid only. Have you heard about boric acid? H3BO3, boric acid, or you can represent it like this as well. BOH whole thrice. This is only H3BO3. Boric acid, one special case. One special case you have, boric acid. Right? Now guys, if you talk about boric acid, let me first of all tell you this boric acid, it is a weak Lewis acid. It's a weak Lewis acid. Now, what this boric acid, when we put this boric acid into water, what happens? Try to understand very carefully what I'm going to say. If you talk about boric acid, this is BOH, this is your OH, and this is your OH. This is H3BO3. When you introduce this boric acid into water, what happens? When you introduce this boric acid into water, what happens? Oxygen here has got 2 lone pairs. When you introduce boric acid into water, you know, this boron center, it is electron deficient. It has got 2, 4, 6, only 6 electrons in its valence shell. This boron here has only got 6 electrons in its valence shell. How many it wants? It wants 8. So this boron over here is electron deficient. If it is electron deficient, if it gets electrons from somewhere, it's going to accept them. So when boric acid is introduced in water, oxygen of water has got a lone pair, and oxygen is going to donate one of its lone pair towards boron. So oxygen is the donor atom here, boron is the acceptor atom here. Perfect. So what happened? You had boric acid, BOH whole thrice. You are just introducing this boric acid into water. What is going to happen? What is going to be made at the end? My dear students, earlier there was no charge on oxygen. It was water, neutral. There was no charge on oxygen. Now oxygen got positive charge. And you must be knowing, positive charge on an electronegative element. Positive charge on an electronegative element makes it more electronegative, right? So, oxygen carrying positive now is more electronegative. Or I would say, positive charge on an electronegative element makes it unstable. So now this oxygen carrying positive is unstable. It would want to get back its stability. How it would get back its stability? When this positive charge is neutralized. How this positive charge is neutralized? What is going to happen? I would say one of the OH bonds here is going to break towards oxygen, due to which the final structure is going to like this. OH, this is OH, one more OH, and this is oxygen attached with hydrogen. Since this bond has been broken down towards oxygen, so that positive charge will be nullified, cancelled, right, neutralized. Perfect. And there is negative on this boron. And this hydrogen leaves as H positive. So what did we get? If you look at this particular structure properly, it is BOH4 negative plus H positive. Perfect. Any substance that accepts pair of electrons, what do you call that as? Lewis acid. So boric acid has accepted a pair of electrons. So it works as a Lewis acid. It's a weak Lewis acid here. People. Okay? It's a weak Lewis acid here. Yeah? It's a weak Lewis acid here. I believe it's clear. Now, people, one thing which I'm going to tell you over here. Should I be calling the boric acid as protic acid? Is it giving H positive? Is boric acid giving H positive? Boric acid is not giving its H positive. No, you can see clearly. It is the hydrogen of water which is leaving here. So boric acid is not the protic acid. It is the Lewis acid. It is accepting a pair of electrons. Okay. Now, people, if I ask you what is the N factor of boric acid? If I ask you what is the N factor of boric acid here, you can check it out. See, I would say initially there were 3 OHs. Now when you introduced in water, now there are 4 OHs. Initially there were 3 OHs. In water now there are 4 OHs. That means boric acid has accepted one OH negative. And the number of OH negatives accepted by the acid the number of OH negatives accepted by the acid, that defines the basicity of the acid. And basicity of the acid is what you call as its N factor. So normally, I used to think that its N factor is 3 because it has got three hydrogens attached with 3 oxygens. So its N factor should have been 3. But when we analyze things, its N factor is not coming out to be 3. Its N factor is coming out to be 1. Right? Suama Roy. Tomorrow morning at 9 a.m. I'm posting one video on that. Do watch that. Okay, you'll get all your answers cleared. Tomorrow at 9 a.m. on this channel itself, one video will be posted related to proper strategy for upcoming 7 months. Okay, I believe this particular thing is clear to everyone. Now, acid part is not over yet. Acid part is not over yet. Let me tell you one more statement about acids. My dear students, N factor of an acid, N factor of an acid changes. N factor of an acid changes on changing the type of the reaction. N factor of the acid changes on changing the type of the reaction in which it participates. What is meant by this? See, I'm writing 2 reactions here. The first reaction is H2SO4 plus NaOH gives NaHSO4 plus water. This is one of the reactions which I've written. Similarly, I'm writing one more reaction. H2SO4 plus 2 times NaOH gives Na2SO4 plus 2 times water. For example, in both the reactions, I want you guys to calculate the N factor of H2SO4. Why the N factor of H2SO4? Because I want to calculate equivalent mass of H2SO4 in both the reactions. In order to calculate equivalent mass, what do I need? N factor. So I want N factor of H2SO4 in the first reaction as well as second reaction. How exactly are you going to do it? Understand properly. See guys, you must be knowing about one thing. You know, one H positive, when reacts with one OH negative, it forms one water molecule. This is something which all of you must be knowing. One H positive when reacts with one OH negative, it forms one water molecule. So 2 H positives when react with 2 OH negatives, they are going to form 2 water molecules. Okay? Correct? Now people, understand. In this reaction, people, in this particular reaction, how many water molecules are being formed? I would say 1 water molecule is being formed. If 1 water molecule is being formed, that means from this acid, 1 H positive would have come. From this NaOH, 1 OH negative would have come. And they would have interacted and formed 1 water molecule. Right? So can I say this acid is donating 1 H positive? And the number of H positives donated by the acid, that defines its basicity. And basicity here is called as N factor. N factor of H2SO4 in the first reaction is 1. In the second reaction, check it out. How many water molecules are being formed? 2 water molecules. Well, in order to form 2 water molecules, can I say this acid would have given 2 H positives, this base would have given 2 OH negatives, and 2 H positives, 2 OH negatives would have interacted and formed 2 water molecules. Right? Right, people? So can I say this H2SO4 is donating 2 H positives? And number of H positives donated by the acid defines its N factor, defines its basicity. So basicity of H2SO4 here is 2. So in the first reaction, Vikram, what are you asking? What is the N factor of NO2? You cannot say it. What is the N factor of NO2? Until you give me the reaction. Right? The reaction in which you want to calculate N factor of NO2. Then I can say it. You are giving the wrong question. Check and modify the question first. Okay. In the first reaction, people, the N factor of H2SO4 is 1. In the second reaction, N factor of H2SO4 is 2. Right? Perfect. N factor of H2SO4 in the first reaction is 1. N factor of H2SO4 in the second reaction is 2. So if I ask you, what is the equivalent mass of H2SO4 in the first reaction? Molar mass divided by N factor. It is going to be 98 grams. What is the equivalent mass of H2SO4 in the second reaction? Molar mass 98 divided by 2, which comes out to be 48 grams. Right? So equivalent mass of H2SO4 in both the reactions, is it coming out to be same or different? Equivalent mass of H2SO4 in both the reactions is coming out to be different. That's what I told you. Equivalent N factor of an acid It changes on changing the type of the reaction, right? If n factor of H2O here was 1, here it was 2. So equivalent mass of H2O in the first reaction is 98. Equivalent mass of H2O in the second reaction is 48. So if you see, equivalent mass of the same substance is coming out to be different in both the reactions. What can we conclude from here? I can conclude equivalent mass is a variable quantity. Equivalent mass is a variable quantity. Unlike what? Unlike molar mass, which is always fixed. Unlike molar mass, which is always fixed. I believe this particular statement is clear to everyone. Yeah? Okay, is it coming out to be 49? All right. Make it as 49 grams. I believe this particular point is clear. Yeah? All clear, people? All clear, quickly. Quickly, all clear? So this was all about the n factor of acids. Now, let's move on. Let's move on to the fifth point. That is your n factor of bases. N factor of bases. And after this particular topic, we are going to take the dinner break. Okay, after this particular topic. N factor of bases. My dear students, how can we define the n factor of bases? N factor of base is nothing but it is defined as acidity of the base. It is defined as the acidity of the base. How do we define acidity of the base? Number one, number of OH negatives a base donates. Number of OH negatives a base donates. Number two, number of H positives a base accepts. Base accepts, or I can say number of lone pairs a base donates. Three ways by means of which you can define the acidity of the base. And why am I defining the acidity of the base? Because acidity of the base is something which you call as n factor of the base. For example, take some common bases, like you have got NaOH, like you have got KOH, like you have got MgOH whole twice, right? Let's say you have got AlOH whole thrice. Perfect. When you introduce them in water, it is going to give one OH negative. This is also going to give one OH negative. This is going to give two OH negatives. This is going to give three OH negatives. And the number of OH negatives a base donates, that defines its base acidity. And whatever is the acidity of the base, that's something which you call as n factor of the base, right? So once you got the n factor of the base, once you got the n factor of the base, people, once you got n factor of the base, you can easily calculate equivalent mass of the base. So what is the equivalent mass of NaOH here? Equivalent mass of the NaOH will be molar mass of NaOH, 40 grams, divided by n factor of NaOH. N factor of NaOH is just 1. Perfect. Similarly, KOH, molar mass divided by its n factor, that's 1. Molar mass divided by its n factor 2. Molar mass divided by its n factor 3. Right? Am I clear? Right, people? In simple words, n factor of the base is nothing but acidity of the base. And how do we define acidity? Number of OH negatives a base donates, or number of H positives acid accepts, or number of lone pairs a base donates. Here, I took a base. Imagine I introduced this base into water. It gave away one OH negative. In water, this is giving one OH negative, two OH negatives, three OH negatives, and number of OH negatives given by a base. Number of OH negatives a base donates. That defines its acidity, and acidity of the base is what you call its n factor. And if you got n factor of these bases, you can easily calculate their equivalent masses. How? Their molar masses divided by their n factors. Simple. This was point number 1. Point number 2. For example, you have got NH3. Imagine you are introducing it into water. Let's say it's forming NH4 positive plus OH negative. Plus OH negative, right? If I ask you, What should be the N factor of this ammonia? N factor of base here. What should be the N factor of this base here? What should be the N factor of this base here? Well, you are not going to say this ammonia is losing one OH negative. That's not the right explanation. See basically what is happening. If you talk about NH3, nitrogen here as the lone pair, you are introducing it into water. Water has got H positives and OH negatives. Well, H positives are electron deficient. So, nitrogen is going to donate its lone pair towards hydrogen in the form of what? In the form of coordinate bond. Okay? And what does it form at the end? At the end, it forms NH4 positive. So, NH3 is going to donate one of its lone pair to H positive. Right? Perfect. And it's going to form NH4 positive at the end. Perfect. And this is the OH negative, which is not the OH negative coming from NH3. This is basically the OH negative which belongs to water. Perfect. So can I say it like this? NH3 in water is accepting H positive basically. Right? Can I say NH3 in water is accepting one H positive and forming NH4 positive at the end? Number of H positives a base accepts. That defines its N factor. So I would say N factor of NH3 here in this reaction is 1. I believe this is clear. Yeah? NH3 in water accepts one H positive. Perfect. Don't say it is going to donate one OH negative. This is the OH negative which is coming from water. This has got nothing to do with this NH3. I believe it's clear. Now, one more statement I'm giving you. I would say N factor of a base chains. N factor of a base chains on changing the type of the reaction in which it participates. For example, let's say I'm writing the reaction like this. Zinc hydroxide plus HCl. For example, it gives ZnOHCl plus water. This, for example, one reaction. Second one. Zinc hydroxide plus 2HCl gives ZnCl2 plus 2 times water. For example, I need to calculate N factor of zinc hydroxide in the first reaction as well as second reaction. If you look properly, in the first reaction, one water molecule is being formed. If one water molecule is being formed in the first reaction, can I say in order to form one water molecule, this acid would have given one H positive, this base would have given one OH negative, and they would have interacted and formed one water molecule. Similarly, here if you see two water molecules are formed, if two water molecules are being formed, I would say this acid would have given two H positives, this would have given two OH negatives, right? They would have interacted and formed what? They would have interacted and formed two water molecules. If you see properly, this base is donating one OH negative. Here the base is donating two OH negatives. Number of OH negatives donated by a base, that defines its N factor. So N factor of zinc hydroxide here is 1, N factor of zinc hydroxide here is 2. If you got the N factor of zinc hydroxide in both the reactions, you can calculate equivalent mass of zinc hydroxide in both the reactions. In the first reaction, it's going to be molar mass divided by 1. In the second reaction, it's going to be molar mass divided by 2. Right? In the first reaction, it's going to be molar mass by 1. In the second reaction, it's going to be molar mass divided by 2. Correct, people? Is it clear? And if this particular concept is clear to you, you should be in a position to answer these questions. Equivalent mass of acid and base in the following reaction. Equivalent mass of acid and base in the following reaction. Can you give them a try? Can you give them a try, people, quickly? Everybody. Simple question this is. Let me know in the chats. I'm looking at your chats only. You should be in a position to solve this. Quick, quick, quick. Hmm. Quickly solve them. Slightly move, sir. Okay. Moved. Give it a try quick. It is again the simple question, guys. It's again the simple question. Quickly. Guys, you should be in a position to solve this easily. Okay, you're going to use the same logic. Here, one water molecule is formed, two water molecules, one water molecule. And in order to form one water molecule, I would say from here, one H positive would have come. From here, one OH negative would have come. Right? And they would have interacted and formed one water molecule at the end. So this acid is donating one H positive, hence its N factor is 1. And this acid is donating one OH negative, hence its N factor is 1 also. Right? So their N factors are 1 and 1. You can easily calculate their equivalent masses. Molar mass divided by N factor. Here also molar mass divided by N factor. Same approach you'll be using here. Same approach you'll be using here. These two are going to be your homework questions. Okay. So with this, your equivalent masses of acids, bases is done. I think let's take a break, dinner break. So I would say dinner break till what time? It is 9:53 right now. So 9:55, 35. So let's get back at what time? At what time? At what time? Quick. Break of 45 minutes, huh? But be back on time, huh? Perfect. Be back on time, guys. Let's get back at 10:40 sharp. Okay? I'd be expecting every one of you to be here. I would be expecting every one of you to be here after the dinner. I'll also have dinner and get back. See you in some time. Is everyone back or not? Is everyone back or not? Done with the dinner? Are you guys done? Welcome back, people, welcome back. Welcome back. Yes, I'm done with the dinner. Yes, I'm done. What about you guys? Back with the same energy? Back with the same energy? That's great. So tell me quickly, whatever things we discussed till now, is every single thing clear? Whatever things we discussed till now, every single thing clear or not? Let me know honestly in the chats quickly. Then we'll be starting the session. Let me know quickly in the chats. Yes, everyone. Perfect, that's great. So let me ask you one question and then we'll be starting. What is the N factor of boric acid? What is the N factor of boric acid in water? Quickly, in the chats. What is the N factor of boric acid in water? Let me see how much you guys remember. Nice, great. Okay, it's 1. All right, tell me the N factor of H3PO2 in water. H3PO2. H3PO2. That's also 1. All right, that's great. So, perfect. Perfect then, perfect. Nice, good. So, let's continue now. So, people, till now we are done with the N factor of elements, N factor of ions, N factor of salts, N factor of acids, N factor of bases, right? Now, we are going to move into we are going to move into the N factor of oxidizing agents and reducing agents. Okay, N factor of oxidizing agents and reducing agents. What is, first of all, the N factor of oxidizing or reducing agent? Let's get to know about this. My dear students, N factor of oxidizing or reducing agent is always equal to the number of moles of electrons lost, gained, or exchanged lost, gained, or exchanged by 1 mole of substance. N factor of oxidizing or reducing agent is equal to N factor of oxidizing or reducing agent is equal to the number of electrons, number of moles of electrons lost, gained, or exchanged by 1 mole of substance. Let's get to know exactly what it means and how do we calculate this. Understand properly what I'm going to say now. My dear students, for example, you have got the reaction like this. A plus B. For example, it gives A positive plus B negative. Let's say this is one general reaction that I've taken. Okay. If I ask you, what is the oxidation state of A here? It's 0. Oxidation state of B is 0. Oxidation state of A here is +1 and here it is -1. I would say oxidation state of A is changing from 0 to +1. Oxidation state of B is changing from 0 to -1. Now, first of all, 0 to +1 means increase in the oxidation state. 0 to -1 means decrease in the oxidation state. You know, increase in the oxidation state is something which we call as oxidation. So I would say this A is undergoing oxidation over here. Now, if A is undergoing oxidation, I would call this A as the reducing agent, right? I would call this A as the reducing agent. Similarly, if I talk about B, 0 to -1, decrease in the oxidation state. Decrease in the oxidation state is termed as reduction. And the one that undergoes reduction, that is going to be your oxidizing agent, right? Now the point is, how do we calculate N factors of these oxidizing and reducing agents? See guys, it's simple. If I write N factor of this A over here, N factor of A, how do I get it? First of all, I'll take modulus. I'll take modulus. Modulus of what? Have a look. What is the initial oxidation state of A? It is 0. What is the final oxidation state of A? It is +1. If I ask you to calculate change in the oxidation state of A, you'll write final oxidation state of A minus initial. Final is +1. Initial is 0. The value comes out to be 1. This one is the change in the oxidation state for one atom of A. And over here, we have got only 1. So at the end, I'm multiplying this with 1. The value comes out to be 1. So I would say N factor of A in this particular reaction is nothing but 1. Okay? As simple as that. Similarly, my dear students, if I ask you what is the N factor of B, how do you get the N factor of B? Calculate the change in the oxidation state of B. Calculate the change in the oxidation state of B. This is the initial, this is the final. So final oxidation state of B minus initial, the value comes out to be 1. This one is the change in the oxidation state for one atom of B, and over here I have only 1. So the value comes out to be 1 only. So this one I'll be calling as N factor of B in this particular reaction. I hope you got to know how do we calculate exactly the N factors of oxidizing and reducing agents. Simple. Change in the oxidation state multiplied by number of atoms. Let me give you one more direct example, a general example, so that you'll understand this in better way. For example, you have got the reaction A2 plus B2. Let's say it gives A positive plus B negative. Let's call this as 2 times A positive, 2 times B negative. This is the reaction now. Understand. Let's assume that oxidation state of A here is 0. Here it is 0. Here it is +1 and here it is -1. So I would say oxidation state of A is changing from 0 to +1. That means increase. Increase in the oxidation state is what you call as oxidation. And what is oxidation actually? Oxidation means loss of electrons. Perfect. And the one that undergoes oxidation is something which I call as a reducing agent. Similarly, 0 to -1 means decrease in the oxidation state. Decrease in the oxidation state is what we call as a reduction. The one that undergoes reduction is going to gain the electrons, right? And the one that undergoes reduction is what we call as oxidizing agent. So if I want to calculate the N factor of this A2 here, how do I calculate? 0 to +1. Calculate the change in the oxidation state, which is final oxidation state of A minus initial oxidation state, modulus, the value comes out to be 1. 1 is the change for one atom of A, but I have 2, So multiplying it with 2, the value comes out to be 2. So this 2 is the n factor of A2 in the reaction. Similarly, if I ask you what is the n factor of B2 here? What is the n factor of B2 here? Calculate the change in the oxidation state of B2. Initial is 0, final is -1. So final minus initial modulus, the value comes out to be 1. This one is the change in the oxidation state for one atom of B, but over here, I've got 2 atoms, so multiplying it with 2, the value comes out to be 2. So n factor of A2 as well as B2 came out to be 2. Okay? Now, my dear students, what is the significance, what is the meaning of this n factor of A2 and B2? See, n factor of A2 came out to be 2, right? This A2, its n factor came out to be 2. First of all, A2 is the reducing agent, which undergoes the loss in electrons. So I would say one simple thing. I would say 1 mole A2. 1 mole A2. I'm just making you understand the meaning of this n factor. See, if you look at the definition, it is the number of moles of electrons lost, gained, or exchanged by 1 mole of substance. So I can say, since A2 is losing electrons and its n factor is 2, so that means 1 mole of A2 loses 2 moles of electrons. That means 1 mole of A2 lost 2 moles of electrons in this reaction. Similarly, n factor of B2 is also coming out of B2. This B2 is undergoing reduction, gain of electrons, right? So B2 is gaining electrons and its n factor is 2. What does it mean? It means that 1 mole of B2 gained 2 moles of electrons, right? It means that 1 mole of B2 gains 2 moles of electrons. I believe it is clear to everyone. Yes? And guys, one more thing. One more thing which I want to tell you. I told you in order to calculate n factor of A2, calculate the change in oxidation state, which is final minus initial. The value comes out to be 1. 1 is the change in the oxidation state for one atom, but I have 2. Remember, the one whose n factor is to be calculated, just multiply with the subscript of that particular substance. That's why I multiplied with 2. In order to calculate n factor of B2, the one whose n factor is to be calculated, at the end you have to multiply with its subscript. You have got nothing to do with what it's getting converted into. You have got nothing to do with the subscript of that. Okay? For example, one more thing. If I ask you, what is the n factor of A positive in this reaction? What is the n factor of A positive in this reaction? If I ask you to calculate n factor of A positive, what do you need to do? Just reverse the things. When you reverse the things, you'll be calling this as initial, this as final. So now it's going to be final minus initial. Final here is 0 minus initial is +1. The value comes out to be 1. 1 is the change in the oxidation state for one atom of A, and over here the subscript is 1. So multiplying with the subscript, nothing to do with the stoichiometric coefficient. So its n factor simply is 1. Right? Similarly, guys, if I ask you to calculate n factor of B negative, again you'll be reversing the things. You'll be calling this as initial, you'll be calling this as final minus initial. So final is 0, initial is -1, modulus, the value comes out to be 1. 1 is the change for one atom and its subscript here is 1. So 1 multiplied by 1 directly comes out to be 1 only. Am I clear with this? Tell me once in the chats. Tell me once in the chats, people, quickly, if this is super clear to everyone. Tell me once in the chats quickly, if this is clear. Yeah? Got it? The one whose n factor is to be calculated, you have to consider its subscript only. Right? Here I was supposed to calculate n factor of this reactant. So I looked at its subscript. Here I was supposed to calculate n factor of this A positive. Therefore, I looked at its subscript and multiplied at the end with the subscript. Nothing else. Simple and basic. Okay. For example, you have got the direct reaction like this. You are going to tell me the answer in the chats. Let's say A4 plus B4, it gives 4 times A positive plus 4 times B negative. Can you let me know the n factor of this A4? Can you let me know the n factor of all these species? So first of all, calculate their oxidation state. 0, 0. Here it is plus 1. Here it is minus 1. Right? Now, n factor of A4 will be equal to A4. This is initial and this is final. So final minus initial mod, the value is 1. 1 is the change in the oxidation state for one atom of A. I have 4 here. So I'm multiplying with 4. The value comes out to be 4. Simple. And what does this 4 mean exactly? See, this is increase in the oxidation state. So this A4 is losing electrons. It is undergoing oxidation. It's losing electrons. This 4 means that 1 mole A4 lost 4 moles of electrons. This is the meaning of its n factor. This is the meaning of its n factor. Similarly, if I ask you what is the n factor of B4, n factor of B4, see, 0, 0 to minus 1. Calculate the change. Final minus initial. The value is 1. 1 is the change for one atom. I've got 4 over here. So the value is 4. See, this is decrease in oxidation state. Decrease in the oxidation state means reduction. So B4 is gaining electrons. And since its n factor is 4, so I got to know 1 mole B4 gained 4 moles of electrons. I hope this is clear. Now, for example, I want to calculate n factor of A positive. If I want to calculate n factor of A positive, I'll go in the reverse manner. Now, I'll be calling this as initial, this as final. So, it will be final minus initial is plus 1, modulus. So, the value comes out to be 1. 1 is the change for one atom of A. Look at the subscript, it's 1 only. So, 1 multiplied by 1 is 1, right? Similarly, if I ask you the n factor of B negative, you should be in a position to calculate it. B negative n factor. Call this as initial, call this as final. So, final minus initial, the value is 1. 1 is the change in the oxidation state for one atom of this B. And over here, the subscript is 1. So, the value comes out to be 1 only. So, again, I'm repeating the same thing. The one whose n factor is to be calculated, you have to look at its subscript, right? Not to the subscript of what it is getting converted into. Simple. Am I clear with this? Let me know quickly in the chats. Am I clear with this? Am I clear with this, people? Quickly. Everyone. Everyone. Now, guys, let's try to understand a few more things. There is one very important compound which is what you call as KMnO4. You must have heard about it. KMnO4. It is a strong oxidizing agent. It is a strong oxidizing agent. Okay. Now this KMnO4 in different mediums, it shows different reactions. What does that mean? My dear students, in acidic medium, KMnO4 gets converted into Mn di positive. This is something which happens in which medium? In acidic medium. Remember, in acidic medium, KMnO4 gets converted into Mn di positive. This is something to be remembered. Okay, number 1. Number 2, my dear students, in neutral or slightly alkaline medium, in neutral or slightly alkaline medium, let me tell you, this KMnO4, it gets converted into MnO2. Similarly, in a strongly alkaline medium, the same KMnO4, it gets converted into MnO4 dinegative. Okay. Now, I want to calculate n factor of KMnO4 in all the mediums. I want to calculate n factor of KMnO4 in all the mediums. How exactly? Have a look. I'll be first of all calculating the oxidation state of manganese here. It's plus 7. Oxidation state of manganese here is plus 2. Oxidation state of manganese here is plus 4. Oxidation state of manganese here is plus 6. When you calculate it, right? Now, my dear students, plus 7 to plus 2. Plus 7 to plus 2. I need to calculate n factor of KMnO4 in acidic medium. In acidic medium, it's going from plus 7 to plus 2. What is the change? final minus initial का mod. The value comes out to be 5. 5 is the change in the oxidation state for one atom of manganese. And over here, I have only one. So N factor of KMnO4 in acidic medium is nothing but 5. Correct? Similarly, people, N factor of KMnO4 in neutral medium. Plus 7 to plus 4. Plus 7 to plus 4. What is the change? Final minus initial. The value comes out to be 3. 3 is the change for one atom, and over here I have only one. So its N factor over here is nothing but 3. Perfect. Similarly, plus 7 to plus 6. So its N factor will be 1. So remember, if I talk about KMnO4, in acidic medium, N factor of KMnO4 is 5. Right? In neutral medium or slightly basic medium, N factor of KMnO4 is 3. And in strongly basic medium, N factor of the same KMnO4 is 1. Okay? These are certain things which you need to remember. Now, my dear students, a question was asked long back on the same. The question was like this. What is the ratio of equivalent mass of KMnO4 in acidic, neutral, and strongly basic medium? Acidic, neutral, and strongly basic medium. So first of all, I want to calculate the ratio of equivalent mass of KMnO4 in which all mediums? Acidic medium, neutral medium, and strongly basic medium. So first of all, if I ask you what is the N factor of KMnO4 in acidic medium, it's 5. In neutral medium, it is 3. In strongly basic medium, it's 1. So if I ask you to calculate equivalent mass of KMnO4 in acidic medium, it's going to be molar mass divided by N factor. Here it's going to be molar mass divided by N factor. Here it's going to be molar mass divided by N factor. This ratio I was supposed to calculate, right? So first of all, M got cancelled. If M got cancelled, this comes out to be 1 by 5. This comes out to be 1 by 3. This comes out to be 1 by 1, right? Now people, do one thing. Take the LCM of the denominators over here. The LCM of 5 and 3 is 15. So I'm multiplying this with 15. I'm multiplying this with 15. I'm multiplying this with 15. So 5, 1, 5, 3. The value here comes out to be 3. 3, 1, 3, 5. The value comes out to be 5. And here, the value directly comes out to be 15. So the ratio of equivalent mass of KMnO4 in all the mediums, acidic, neutral, and strongly basic, came out to be 3 is to 5 is to 15. This is the ratio of the equivalent masses of KMnO4 in acidic, neutral, and strongly basic medium. I believe this is clear to everyone. Yeah? Similarly, let me talk about few things about one more oxidizing agent, one more strong oxidizing agent, that is K2Cr2O7. This is again a strong oxidizing agent. In which medium? It is a strong oxidizing agent in acidic medium. And remember, in acidic medium, it gets converted into Cr tripositive. Now people, if I ask you, what is the N factor of K2Cr2O7 here in this reaction? What is the N factor of K2Cr2O7 in this particular reaction? First thing, calculate the oxidation state of chromium here. It is plus 6. Here it is plus 3. So plus 6 to plus 3. Decrease in the oxidation state. Reduction. Reduction means oxidizing agent. Right? Now people, calculate the N factor of K2Cr2O7. So plus 6 to plus 3. Calculate the change. Final minus initial, and this is mod. The value comes out to be 3. This 3 is the change in the oxidation state for one atom of chromium. But here I've got 2. So 3 multiplied by 2 comes out to be 6. This is the N factor of K2Cr2O7 in which medium? In acidic medium. Similarly, people, if I ask you, what is the N factor of Cr tripositive in the same reaction? If you want to calculate N factor of Cr tripositive, that means you'll go in the reverse manner. You'll be calling this as initial. You'll be calling this as final. So it's going to be final minus initial, and this is mod. The value comes out to be 3. 3 is the change for one chromium, and here we have got 1 only. So 3 multiplied by 1 comes out to be 3 only. Right? I believe I'm clear with all of this stuff. right? So people, if you got to know how to calculate n factors of different, oxidizing reducing agents, then I believe you are fit enough to solve these questions. I believe you are fit enough to solve these questions on your own. See, calculate the n factor of following. So this is something which we discussed few minutes back only. N factor of K2Cr2O7 here is, it will be 6, and n factor of Cr tri positive will be 3. We solved this like a few seconds back. Now, iodine here is in 0 oxidation state. Here the iodine is in +5 oxidation state. 0 to +5. Change is 5 minus 0. 5. 5 is the change for one atom. I have 2. So 5 2s are 10. So n factor of I2 here is 10. What is the n factor of IO3 negative? +5 to 0. Change. Final minus initial. The value is 5. 5 is the change for one iodine, and I have 5 on. And I have 1 only. So its n factor is how much? Its n factor will be nothing but, its n factor will be 5 only. Perfect. Talk about this particular reaction. Calculate the oxidation state of this carbon by using the formula. When you solve, this is +3 and this is +4. So first of all, +3 to +4, change 1. 1 is the change for one atom, I have 2. So its n factor is 2. Calculate its n factor of carbon dioxide. +4 to +3, calculate the change. Final minus initial, the value is 1. 1 is the change for one atom of carbon. Here I've got 1 only. So its n factor is 1. Simple. Oxidation state of oxygen here is -1, here it is 0. So -1 to 0. -1 to 0, change 1. 1 is the change for one atom, I have 2. So its n factor is 2. Right? Similarly, O2, 0 to -1. 0 to -1, calculate change. Final minus initial, the value is 1. 1 is the change for one atom, I have 2. So its n factor is 2. Vanadium here is in +2 oxidation state. Here vanadium is in +5 oxidation state. +2 to +5. +2 to +5. Change. Final minus initial, 3. 3 is the change for one atom. I have 3 only. I have 1 only. So it's 3. +5 to +2. 3. 3 multiplied by 2 is nothing but 6. I hope you are getting all this stuff. I hope you are getting all this stuff, people. Now, Fe 0.930 gives FeU. So first of all, if you see, when I was discussing the oxidation state in the beginning, I took this example and showed you its oxidation state is nothing but +200 by 93. And its oxidation state is nothing but, when you solve it, it's +2. It's simple. X minus 2 is equal to 0. So, +200 by 93 to +2. Calculate the change. So, n factor of Fe 0.930 is equal to final, that is +2, minus initial is 200 by 93. This is the change for one atom, right? And at the end, you'll be multiplying this with 0.93. Whatever value you get, that's going to give you the n factor of this particular substance, right? Simple. Similarly, guys, oxidation state of iodine, when you calculate here, it's +5, here it is +7. So +5 to +7, change is 2. 2 is the change for one atom, right? And I've got one atom only, so its n factor is nothing but 2. Similarly, its n factor will be also 2. Let me know once in the chats if you got how to calculate the n factors of oxidizing and reducing agents. Quickly, let me know this in the chats, because this is something which I feel is very important, which you need to know. Clear? Clear, people? Yes or no in the chats? Everybody. Yes or no in the chats? Everyone. Yes or no in the chats? Everyone. This is the same stuff which we did, right? Now, people, there is one more case in the n factors, that is, I would say, n factor of substances which can behave as oxidizing agents as well as reducing agents. Which can behave as oxidizing agents as well as reducing agents. There are some substances which show dual nature. Dual nature means sometimes these substances are going to behave like oxidizing agents, and sometimes the same substance is going to behave like the reducing agent. And the common examples of these are your first one is H2O2, second one is HNO2, and third one is FeSO4. Let me tell you, H2O2, sometimes you'll see this H2O2 getting converted into O2, and sometimes you'll see the same H2O2 getting converted into water. In some of the reactions, you will see this HNO2 getting converted into NO. In some other reaction, the same HNO2 you will see getting converted into NO3 negative. NO3 negative. FeSO4, sometimes you will see getting converted into iron, and in some other reaction, it gets converted into iron tripositive. It gets converted into iron tripositive. Okay? Now guys, understand. Properly understand what exactly I'm going to say. Oxidation state of oxygen and hydrogen peroxide is -1. Here it is 0. Here it is -2. First of all, when H2O2 gets converted into O2, what happens? -1 to 0. Increase. Increase means oxidation. Oxidation means reducing agent. So, when H2O2 gets converted into O2, it behaves like the reducing agent. Similarly, -1 to -2. -1 to -2. Decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. The one that undergoes reduction behaves like the oxidizing agent. So, I would say when H2O2 gets converted into water, it behaves like the oxidizing agent. Now, in both the cases, what is the N factor of H2O2? So, N factor of H2O2 when it behaves like the reducing agent, and N factor of H2O2 when it behaves like the oxidizing agent. How much? It's going to come. -1 to 0. Calculate the change. Final minus initial. The value is 1. 1 is the change for one atom, but I have 2. So its N factor is simply 2. Similarly, -1 to -2. The change is 1. 1 is the change for one atom, but I have 2. So its N factor 2. So basically, if H2O2 behaves like oxidizing agent or reducing agent, in both the cases, the N factor of H2O2 is coming out to be how much? It's coming out to be 2 only. Right? It is coming out to be 2 only. Yeah? Right, people? In both the cases, it's going to get converted into what? It's going to be, its N factor is going to be 2 only. Now, similarly, talk about HNO2. Talk about HNO2. My dear students, if you talk about the oxidation state of this nitrogen here, it will come out to be +3. Here, it will come out to be +2. Here, it will come out to be +5. Right? Now, +3 to +2. Change is 1. 1 is the change for one nitrogen. I've got only 1. So, N factor of HNO2, right, in this first reaction is nothing but 1. And in the first reaction, if you look carefully, +3 to +2, decrease. Decrease means reduction. So, oxidizing agent. So, here HNO2 is behaving like the oxidizing agent. Similarly, +3 to +5, increase. Increase means oxidation. So, it's the reducing agent. So, +3 to +5, calculate the change. Final minus initial. The value comes out to be 2. 2 is the change for one atom. I've got one atom only. So, its N factor is 2. N factor of HNO2 in this reaction is nothing but 2. I hope this is clear to everyone. Similarly, the next one. This is sulfate, SO4 dinegative. If it is SO4 dinegative, that means iron has to be in +2 oxidation state, di positive. Here iron is in 0 oxidation state. Here iron is in +3. So +2 to 0, decrease, reduction, oxidizing agent. +2 to +3, increase, oxidation, reducing agent. So let's calculate N factor of FeSO4 in both the cases. Understand. +2 to 0, calculate the change. Final minus initial. The value comes out to be 2. 2 is the change for one atom of iron, and I've got one atom only. So its N factor here is 2. So +2 to +3, change. 1. 1 is the change for one atom. I have one atom only. So its N factor is 1. So if you got their N factors, you can easily calculate their equivalent weights. How? Molar masses divided by their respective N factors. I believe I'm clear to everyone. I believe I'm clear to everyone. Quickly in the chats, people. Is all the stuff clear? Is all the stuff clear, people? Yeah? This was one more case of N factors wherein a particular substance can show dual nature. In some of the reactions, it's going to behave like the oxidizing agent. In some other reaction, the same substance is going to behave like the reducing agent. I hope this is super clear to everyone. Yeah. Now, guys, there are few more cases when it comes to N factor calculation. What is that? N factor of the substances. N factor of the substances in which oxidation state of more than one element changes. See, guys, till now I was talking about I was giving you only those oxidizing and reducing agents wherein. Till now I was giving you only those oxidizing and reducing agents wherein the oxidation state of only one element was changing. Just a second, guys. Few people insist me to block them. And they are gone. They are over. Done and dusted, yeah? Now they won't be able to spam. Look here now. It's done. See, guys, N factor of substances in which oxidation state of more than one element changes. So till now, I was taking those oxidizing and reducing agents. I was giving you those oxidizing and reducing agents till now in which the oxidation state of only one element was changing. What if in a compound oxidation state of more than one element changes? How do we calculate N factor of those substances in which oxidation state of more than one element changes? For example, imagine that you've got a compound ABC, right? During the reaction, let's assume that oxidation state of A as well as oxidation state of B is changing. Let's say during the reaction, let's assume oxidation state of A as well as oxidation state of B is changing. Let's say during the reaction, let's assume oxidation state of A as well as oxidation state of B is changing. Now, how they can change? There are few permutations, combinations which you can use here. One of the possibilities is during the reaction, oxidation state of A as well as B is increasing. One more possibility is during the reaction, oxidation state of A as well as B decreases. One more possibility is oxidation state of A increases, B decreases. Right? These are the possibilities which we have over here. We have got some compounds in which oxidation states of more than one element increases. Now, first possibility is oxidation state of both the elements will be increasing. Second possibility, oxidation state of both the elements will be decreasing. Third possibility, oxidation state of one element increases, another element decreases. How do we calculate their N factors? How do we calculate their N factors? My dear students, remember, whenever you see a species in which oxidation state of more than one element either simultaneously increases or simultaneously decreases, how do you calculate their N factors? Simple. N1 plus N2. This is how you calculate their N factor. But if oxidation state of one element increases, another one decreases, how do you calculate its N factor? Its N factor is nothing but mod of N1 minus N2. This is the formula which you can remember directly. This is the formula which you can remember directly. Okay? Perfect. Right, people? For example, you have got a case like this. You have got a compound ABC. Let's say during the reaction, oxidation state of A, B as well as C is increasing. How do I calculate its N factor? It is simply going to be N1 plus N2 plus N3. Perfect. Let's say you have got a reaction in which oxidation state of A as well as B as well as C decreases. How do you calculate its N factor? It's going to be N1 plus N2 plus N3. Let's say you have got a case like this. You have got a compound ABC. Oxidation state of A increases, B increases, C decreases. How do you calculate its N factor? It's going to be N1 plus N2 minus N3. N1 plus N2 minus N3. Right? Right, people? Perfect. I hope this is clear to everyone. Let me take certain examples so that you'll understand all of this in a better way. Let's take certain examples one by one. See, guys. Look at this particular example. For example, I want to calculate N factor of this substance. First of all, if you look carefully, this is oxalate ion, C2O4 di-negative. If this is oxalate di-negative, then iron has to be in di-positive. Similarly, when you calculate oxidation state of carbon here, this is going to be +2 plus 2x minus 8 is equal to 0. It comes out to be +3. Oxidation state of iron here is +3. Oxidation state of carbon here is +4. Now check it out. +2 to +3, increase. +3 to +4, increase. Can I say this is the compound wherein oxidation state of two elements is increasing simultaneously? Right? How do we calculate its n factor? Its n factor is simply going to be n1 plus n2. Now what is n1, what is n2 here? Understand. See guys, +2 to +3, change, final minus initial. The value is 1. 1 is the change for one iron. I have only one iron, right? So n1 value is 1. +3 to +4, what is the change? 1. 1 is the change for one atom, but I have 2 carbon. So n2 is 2. So its overall n factor is going to be 2 plus 1. That comes out to be 3. That comes out to be 3. Did you understand? Did you understand, people? Is it clear? If you want to have its actual significance, +2 to +3, increase means oxidation, loss of electrons. So when Fe di-positive is getting converted into Fe tri-positive, it is losing electrons. How many? 1. +3 to +4, increase, oxidation, again loss of electrons. So carbon is also losing electrons. How many? 2. Iron is losing 1 electron. Carbon is losing 2 electrons. So in total, this overall molecule is losing how many electrons? 1 iron is losing, 2 carbon is losing. So 2 plus 1, 3. So I would say its n factor 3 means over here I can say 1 mole ferrous oxalate is losing 3 moles of electrons. Did you understand why I do the addition here n1 plus n2? I hope this is clear. I hope this is clear. I hope you got to know why I'm doing the addition. Iron lost 1, carbon lost 2. So overall molecule is losing how many? 2 plus 1, 3 electrons. Or I can say 1 mole of this compound is losing 3 moles of electrons. As simple as that. Let me take one more example so that it becomes properly clear. Let me quickly give you their oxidation state. This is +1, this is -2, this is +2, and this is +4. Now check it out. +1 to +2, increase. -2 to +4, increase. Oxidation state of both the elements is increasing simultaneously. Its n factor has to be again equal to n1 plus n2. Now get the value of n1 and get the value of n2. Yeah? See, +1 to +2. What is the change? Final minus initial. The value is 1. 1 is the change for one atom, but I have 2. So n1 is 2. -2 to +4. -2 to +4. Final minus initial. The value comes out to be 6. 6 is the change for one atom. I have only 1. So n2 is 6. So I would say 6 plus 2 comes out to be 8. Right? 6 plus 2 comes out to be 8. 6 plus 2 comes out to be 8. Right? If you think logically, +1 to +2, increase means oxidation. Oxidation means loss of electrons. So copper is losing some electrons. How many? 2. Sulfur is also losing some electrons. How many? 6. So this overall species is losing 6 plus 2, 8 electrons in total. Or I can say 1 mole of this compound is losing 8 moles of electrons. 1 mole Cu2s lost 8 moles of electrons. I hope I'm clear with this. Achha, one more thing. In the same reaction, if I ask you what is the n factor of this Cu di-positive, what you'll be doing? You'll be going in the reverse manner. This is final, this is initial. So final minus initial mod is 1. 1 is the change for 1. I've got only 1. So its n factor is directly 1, nothing else. What is the n factor of this SO2? Go in the reverse manner. This is +4 and this is -2. This is initial, this is final. So final minus initial mod comes out to be 6. 6 is a change for 1. I've got only 1, so its n factor is 6. Yeah? I hope I'm clear with all of this stuff. Right, people? I hope I'm clear with this. All right. For example, one more I'm giving you. Let's check it out what is happening here. Oxidation state of bismuth, when you calculate, it's +3 and sulfur will be -2. This will be +5. This will be 0. Now, +3 to +5, increase. -2 to 0, increase. So what about its n factor? Its n factor is again going to be n1 plus n2 only. Check it out. +3 to +5. Changes, final minus initial. The value is 2. 2 is the change for one atom. I have 2. So 2 2s are 4. -2 to 0. Changes 2. 2 is the change for one atom. I have 3. So 2 3s are 6. So 6 plus 4 comes out to be 10. Simple. Right? Look at this one, guys. Calculate the oxidation states of all the elements first of all. Iron here will be, do the crisscross thing. This 3 will be here. 2 will be here. Right? Iron here will be x minus 2 is equal to 0. So plus 2. Sulfur x minus 4 is equal to 0. So x plus 4. Perfect. So +3 to +2. +3 to +2. Decrease. Right? Perfect. Decrease. -2 to +4. -2 to +4. Increase. +3 to +2. Decrease. -2 to +4. Increase. So oxidation state of one element is increasing, another one is decreasing. Oxidation state of one element is increasing, another one is decreasing. So how do I calculate n factor of that species in which oxidation state of one element increases, another one decreases? So it is simply mod of n1 minus n2. So +3 to +2. What is the change? Final minus initial. The value is 1. 1 is the change for 1. I have 2. So n1 value is 2. Similarly, -2 to +4. What is the change? Final minus initial. So 4 minus -2 comes out to be 6. 6 is the change for 1. I have 3. So 6 3s are 18. So overall is going to be 18 minus 2. That comes out to be 16. This is the overall n factor of Fe2S3. Right? I hope you can easily solve this sort of a question as well. Perfect. Now, look at this particular example. Look at this particular example, people. If you remember, I already gave you the structure of BaSCN whole twice in the beginning of the session. In the beginning of the session, right? I already gave you its structure. This was like this. SC triple bond N and it was SC triple bond N, right? And then it is getting converted into BSO4, which is pretty much normal. This used to be HCN and its structure also we discussed. Now, tell me the oxidation state of all these elements. If you remember, nitrogen used to be in -3 oxidation state, right? Carbon here used to be in how much? +3 due to nitrogen and +1 due to sulfur. It used to be in +4 oxidation state. Sulfur used to be in -2, right? And barium used to be in +2 oxidation state. We have discussed the structure of it, from where we calculated their oxidation state. Barium here is in +2 oxidation state, is a group second element. Sulfur will be in +6 when you solve it. Now, nitrogen here will be in -3 oxidation state. Here carbon will be in +3 due to nitrogen, -1 due to hydrogen, so it will be in +2 oxidation state. Now let's get to know the n factor of the substance. The oxidation state of barium here is 2, here is 2. So it is not changing, so I've got nothing to do with barium. I've got nothing to do with barium. Nitrogen here is in -3, nitrogen here is in also -3, so nothing to do with nitrogen as well. Now check. Oxidation state of sulfur is changing from -2 to +6, increase. Oxidation state of carbon is changing from +4 to +2, decrease. So this is the species wherein oxidation state of one element increases, another one decreases. So its n factor has to be mod of n1 minus n2. So what is n1 and what is n2? Check it out. -2 to +6, change. Final minus initial. So 6 minus -2 is equal to 8. 8 is the change for one sulfur, but I have 2. So 8 2s are 16. So n1 value is 16. +4 to +2. What is the change? 2. Final minus initial, 2. 2 is a change for one atom. And I have 2 atoms. So 2 2s are 4. So 16 minus 4 comes out to be 12. So this is the n factor of the species over here. Am I clear with this, people? Let me know once in the chats if all this stuff is clear. So This was how you calculate n factor of those substances in which oxidation state of more than one element either increases or decreases, or one increasing, one decreasing, etc. etc. Okay? Tell me in the chats quickly if this particular stuff is clear to everyone. Quickly in the chats. Yeah? Formula page we'll see at the end. Perfect. Now guys, there is one last case left in the n factor calculation. What is that? One last case, that is n factor of the substance, or let me write n factor in disproportionation reactions. N factor in disproportionation reactions. How do you calculate n factor of those substances which undergo disproportionation? N factor in case of disproportionation reaction. How to remember this? You do not have to write, you do not have to remember the reactions. Reactions will be given to you only. And then you have to calculate n factors. What is there to remember? If both the elements, their oxidation state is increasing, N1 plus N2. If both are decreasing, again N1 plus N2. If one is increasing, one is decreasing, N1 minus N2. What is there? Nothing. See guys, for example, I've got the reaction like this. A2 gives A positive plus A negative. Let's say this is the reaction. Okay, let's say this is the reaction. I'm assuming oxidation state of A here is 0. Here it is plus 1. Here it is minus 1. First of all, 0 to plus 1 means increase. 0 to minus 1 means decrease. So I would say oxidation state of same element. Oxidation state of same element is simultaneously increasing as well as decreasing. Whenever oxidation state of same element simultaneously increases as well as decreases, we say that particular species undergoes disproportionation. And how do we calculate n factor of the species which undergoes disproportionation? It is nothing but n1, n2 divided by n1 plus n2. This is how you calculate the n factor. n1, n2 divided by n1 plus n2. Okay, understand. 0 to plus 1. Change is 1. 1 is the change for one atom. I have 2. So n1 value is 2. 0 to minus 1. Change is 1. 1 is the change for 1. I have 2. So n2 is 2. So overall n factor is going to be 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. So this is the n factor of A2 in this reaction. Okay. This is the n factor of A2 in this particular reaction. This is one quick formula which you can remember to calculate n factor of that species which undergoes disproportionation. I hope I'm clear with this. I hope I'm clear with this. For example, let's say I'm giving you a question here. The question is, you have got Br2. It gives Br negative plus BrO3 negative. Okay. You need to calculate n factor of this Br2 here in this reaction. Can you try it out? What is the n factor of Br2 in this reaction? So first of all, its oxidation state here is 0. Here the oxidation state is minus 1. Here when you calculate, it's going to be plus 5. So 0 to minus 1, decrease. 0 to plus 1, increase. So you saw oxidation state of same element is increasing as well as decreasing simultaneously. So I would say this Br2 is undergoing disproportionation. How do you calculate n factor of that particular species which undergoes disproportionation? You know, the result, that is directly n1, n2 divided by n1 plus n2, right? Now, 0 to minus 1, change is 1. 1 is a change for one atom, but I have 2. n1 is 2. 0 to plus 5, change is 5. 5 is the change for one atom, but I have 2. So 5 2s are 10, right? So it's going to be 2 multiplied by 10 divided by 2 plus 10. The value comes out to be 20 divided by 12. Hence, 4 5, 4 3. So 5 by 3 is the n factor of Br2. If I ask you what is the equivalent mass of Br2 in this reaction, you will say molar mass of Br2 divided by n factor, that is 5 by 3. So the answer is going to be 3m divided by 5 grams. This is the equivalent mass of Br2 in this particular reaction. Yeah? right? Perfect, guys. Similarly, if I ask you one more question, this is the question asked in AIMS. Calculate the equivalent mass of H2O2 in this reaction. You are supposed to calculate the equivalent mass of H2O2 in this particular reaction. Can you give it a try? Let me know the answer in the chats. I want to see whether you'll be able to solve this question or not. What is the equivalent mass of H2O2 in this particular reaction? Well, in order to calculate equivalent mass, what do we need? We need n factor. Equivalent mass of H2O2 in the reaction. Equivalent mass of H2O2 in the reaction. So first of all, in order to calculate equivalent mass of H2O2 in the reaction, what do I need? I need its n factor. Now, how do I calculate its n factor? Understand. This is hydrogen peroxide. Oxidation state of oxygen in hydrogen peroxide is -1. In water, it's -2. In oxygen, it is 0. So -1 to -2 means decrease. -1 to 0 means increase. So oxidation state of same element is decreasing as well as increasing simultaneously. So I would say the species is undergoing disproportionation. Now, -1 to -2, calculate the change. That is 1. 1 is the change for one atom, but I have 2. So N1 is 2. Similarly, -1 to 0, change is 1. 1 is the change for one atom, but I have 2. So N2 is also 2. So it is going to be N1, N2 divided by N1 plus N2. The overall value comes out to be 1. N factor of H2O2 in this reaction is 1. If N factor of H2O2 in the reaction is 1, I would say equivalent mass of H2O2 in the reaction will be equal to molar mass of H2O2, which is 34 grams divided by N factor. So the final value comes out to be 34 grams only. So 34 grams is the equivalent mass of H2O2 in this particular reaction. I hope I'm clear to everyone. I hope I'm clear to everyone. All clear? All clear, people? Yes? Perfect. So this was all about the N factor calculation. This was all about the N factor calculation. Now, there is one thing which I want to tell you over here. What is that? That is some important reactions which you should know. Some important reactions of KMnO4 in acidic medium. Some important reactions of KMnO4 in acidic medium. My dear students, the first thing which I already told you, if you talk about KMnO4 in acidic medium gets converted into Mn di positive, right? Or I would say N factor of KMnO4 in acidic medium is how much? You should remember it directly from now onwards. It's 5. Because +7 to +2 changes 5, right? Its N factor is 5. Now see guys. First of all, the KMnO4, +7 to +2. +7 to +2 means decrease in the oxidation state. Decrease means reduction. Reduction means oxidizing agent. So, you know, KMnO4 is a strong oxidizing agent. Since KMnO4 is a strong oxidizing agent, what kind of reactions this KMnO4 shows, that is important. Few important things, that's all. My dear students, remember, KMnO4 converts Fe di positive into Fe tri positive. In which medium? Acidic medium. You need to remember this. KMnO4 is a strong oxidizing agent. It oxidizes others. So it oxidizes Fe di positive into Fe tri positive in which medium? In acidic medium. This is the first thing which you need to remember about our KMnO4. Second, KMnO4 converts I negative into I2 in the same acidic medium. KMnO4 converts H2O2 into O2 in again acidic medium. KMnO4 converts oxalate ion. into carbon dioxide in the same acidic medium. KMnO4 converts H2S into sulfur, again in acidic medium. KMnO4 converts SN di positive into SN plus 4 in the same acidic medium. KMnO4 converts SO2 into SO4 di negative in the same acidic medium. These are some typical points which you need to remember about KMnO4. KMnO4 is a very strong oxidizing agent. So in acidic medium, KMnO4 converts Fe di positive into tri positive, I negative into I2, oxalate into carbon dioxide, H2O2 into O2, H2S into sulfur, SN di positive into SN plus 4, SO2 into SO4 di negative. Right? Now, people, if you want to write the reactions, you should be in a position to write the reactions as well. How exactly? See, I'll write, let's say I'm writing the first reaction. KMnO4 converts what? KMnO4 converts Fe di positive. In which medium? Acidic medium. Into what? Into Fe tri positive. Itself gets converted into Mn di positive. And with that, you'll be just writing water. This is a complete reaction. It's a complete reaction. No need to remember it. You should be in a position to make the reaction. Let's say I want to make the second reaction. See, KMnO4 converts I negative. In which medium? Acidic medium. Into what? Into I2. And itself gets converted into Mn di positive. And with this, you'll be writing water. This is the second reaction. Similarly, you can write all these reactions on your own. Right? Yeah? Sir, I asked Shimon sir whether you both are friends in the live chat. He said you both used to work together long back. Shimon and me, we started the teaching career together. Okay? He used to teach maths, I used to teach chemistry in the same offline center in Chennai. Yeah? And after that, we joined one common platform wherein he is working right now. I was a part of that platform too for 3 years. Then I shifted to Unacademy. He's still there. Yeah? He's one of the very close friends of mine. Mon Joseph, yeah. So guys, can you write all these reactions? Can you write all these reactions on your own now? For example, I need to write the third reaction. The third reaction says KMnO4 converts H2O2 in acidic medium into O2. Itself gets converted into Mn di positive. And with this, you'll be writing water as well. Done and dusted. Okay. For example, KMnO4 converts oxalate into carbon dioxide. I believe all the reactions you should be in a position to write. Okay, someone is telling me, sir, calculate the N factor of I negative in the chats, right? You should be in a position to do it on your own. I negative here is -1. Here it is 0. -1 to 0. Change. Final minus initial. The value is 1. 1 is the change for 1. So its N factor is 1. N factor of I negative here is 1. Similarly, N factor of I2 will be 2. N factor of I2 will be 2. Then you calculate it. Yeah? Got it? So these are some important reactions of KMnO4 in acidic medium. Rest of the reactions, I believe you can easily complete. Okay? So these are some of the common reactions of KMnO4 in acidic medium, and this is something which is important, which you need to remember. Converts what into what. Perfect. Now similarly, guys, let me write some common reactions. Some common reactions of K2Cr2O7 in acidic medium. Some common reactions of K2Cr2O7 in which medium? In acidic medium. Again, simple. See, first of all, when you talk about your K2Cr2O7, K2Cr2O7, as I told you already, in acidic medium gets converted into Cr tri positive. It is again a strong oxidizing agent. It's again a strong oxidizing agent. Calculate its N factor first. Oxidation state of chromium here is +6. Here it is +3. So +6 to +3, change. Final minus initial, the value is 3. 3 is the change for one atom. I have 2. So 3 2s are 6. So N factor of K2Cr2O7 in acidic medium is 6. Now, what are the reactions? What are the reactions, okay, which this K2Cr2O7 shows? My dear students, K2Cr2O7 is going to show the same reactions as were shown by KMnO4. As were shown by KMnO4. For example, the first one, K2Cr2O7 converts Fe di positive to what? To Fe tri positive. Second one, K2Cr2O7 converts I negative into I2. Third one, K2Cr2O7 converts Sn di positive into Sn plus 4. Fourth one, K2Cr2O7 converts H2O2 into O2. Right? Next one, K2Cr2O7 converts oxalate ion into carbon dioxide. Right? Next one, it converts H2S into sulfur in acidic medium. I think one is pending here. What is that? That is SO2 into SO4 dinegative. And all this happens in which medium? All this happens in acidic medium, right? Now, you should be in a position to write all these reactions on your own. So, I'm going to write K2Cr2O7 converts what? Fe di positive. In which medium? Acidic medium. Into what? Into Fe tri positive. Itself, K2Cr2O7 gets converted into Cr tri positive. And with this, you'll be writing water as well. This is one complete reaction. Done. Similarly, K2Cr2O7 converts I negative. In which medium? Acidic medium. Into what? I2. Itself gets converted into Cr tri positive. With that, you'll be writing water as well. K2Cr2O7 converts Sn di positive. In which medium? Acidic medium. Into what? Sn plus 4. Itself gets converted into Cr tri positive. With that, water. Same. K2Cr2O7 converts H2O2 in acidic medium. Into what? Into O2. Itself gets converted into Cr tri positive. With that, you'll be writing water as well. And similarly, you can continue all these reactions of K2Cr2O7. Am I clear? Right? Someone is saying calculate the N factor of H2O2 here. Let's calculate the N factor of H2O2. So oxidation state of oxygen here in hydrogen peroxide is -1, here it is 0. So -1 to 0, calculate change. Final minus initial, the value is 1. 1 is the change for one atom. I have 2 oxygen here. So 1 into 2 is 2, so its N factor is 2. Similarly, if you want to calculate the N factor of this O2 as well, so it is 0 to -1. Calculate the change. Final minus initial, the value is 1. 1 is the change for 1, I have 2. So its N factor is 2. Got it? Got it, people? All clear? Are these reactions clear? And I would highly recommend you guys, to remember these reactions because they are super important when it comes to the titration part. Okay? Next chapter will be electrochemistry. Now let's move on to one more topic, that is balancing of redox reactions. Okay? Balancing of redox reactions. Balancing of redox reactions is the next topic. So my dear students, in balancing, in order to balance a redox reaction, we have got two methods. Okay? We have got two methods. One is ion electron method. One is oxidation number method. These are the two methods by means of which we can balance a redox reaction. Ion electron, oxidation number. So first, we shall be discussing ion electron method in acidic medium. Then we'll be discussing ion electron method in basic medium. Then we'll be discussing oxidation number method in acidic medium. Then oxidation number method in basic medium. So one on one, we shall be discussing these things. Right? So first of all, I would want you guys to mark the heading as oxidation number method in acidic medium. Oxidation number method in acidic medium. Oxidation number method in acidic medium. How do we balance a redox reaction with the help of oxidation number method in acidic medium? Someone is asking about the duration. We shall be ending by 12 to 1, 1 to 2. I think 2:30 will end the chapter. 2:30 or maximum by 3. 2:30 or maximum by 3 we shall be ending this chapter. Yeah? Are you going to be with me till the end? Or you guys are sleepy? Are you sleepy? How many of you are going to stay till the end? Are you going to stay till the end? Is that a promise? Is that a promise? Yes, 3 to 3.5 more hours. That's all. Perfect. Great. Let's complete the balancing part. Then we'll be taking a break for 10-15 minutes. Okay? Let's complete the balancing part first. Let's complete the balancing part first. So, oxidation number method in acidic medium. How do we balance? How do we balance a redox reaction with the help of oxidation number method in acidic medium? So, let me take the example directly so that it becomes clear to you. For example, I'm taking the reaction as MnO4 negative plus Fe di positive. In acidic medium, it gets converted into Mn di positive. With this, I'm writing Fe tri positive. This is the reaction which is, for example, happening in acidic medium. Okay. So how do I balance this reaction with oxidation number method? See guys, my first step is to calculate the N factors of reactants. That is my first step. Calculate the N factors of reactants. Now, what is the N factor of Fe di positive? Plus 2 to plus 3. Change is 1. 1 is the change for one atom. It's 1 only. So N factor is 1. What is the N factor of MnO4 negative? The oxidation state of manganese here is plus 7. Plus 7 to plus 2. Change is 5. Its N factor is 5. So I got the N factors. My dear students, since I got the N factors, now my second step is to crisscross these N factors. Crisscross these N factors. So take this one as the stoichiometric coefficient here. Take this 5 as the stoichiometric coefficient here. Crisscrossed. After crisscrossing, balance all the atoms except hydrogen oxygen. Balance all the atoms except oxygen and hydrogen. So here we have got 1 manganese. So keep it 1 here. We have got 5 iron. Keep it 5 here. Right? So we have balanced all the atoms except hydrogen oxygen. Now after doing this, balance oxygen atoms with the help of water molecules. So how many oxygen atoms do we have here? 4. There are 4 oxygen atoms on left side. There is no oxygen atom on right side. So which side is oxygen deficient? Right side is oxygen deficient. How many oxygen deficiencies are there on the right side? 4 oxygen deficiencies. If there are 4 oxygen deficiencies, add 4 water molecules on that side, which is oxygen deficient. Done. Now, after doing this, balance hydrogen atoms by adding H positives to that side, which is hydrogen deficient. How many hydrogens on this side? No hydrogen. How many hydrogens on this side? 4 2s are 8. So, left side is hydrogen deficient. How many hydrogen deficiencies? 8. So, add 8 H positives. It's a balanced chemical equation now. It's balanced. Did you understand all this stuff? Let me take one more example. Let's say you got the reaction like this. Cr2O7 di-negative plus Sn di-positive gives Cr tri-positive plus Sn plus 4. Let's say this is the reaction which I have to balance in the acidic medium, right? So what is my first step? Calculate the n factors of reactants. Plus 2 to plus 4 changes to n factor 2. Oxidation state here is plus 6 for chromium. Plus 6 to plus 3. Plus 6 to plus 3. What is the change? 3. 3 is the change for 1 atom of chromium. I have 2. So 3 2s are 6. I got the n factors. Crisscross them. So make this 2 here. Make this 6 here. Now balance all the atoms except hydrogen oxygen. So 4 chromium, 4 chromium. 16, 16. Now balance oxygen with the help of water. How many oxygen on this side? 7 2s are 14. How many oxygen on this side? No oxygen. So right side is oxygen deficient. How many oxygen deficiencies? 14 oxygen deficiencies. So I'll be adding 14 water molecules to that side which is oxygen deficient. Now 14 to 28. 28 hydrogens on this side. No hydrogen on this side. So left side is hydrogen deficient. There are 28 hydrogen deficiencies. So add 28 H positives on this side. Now it's a balanced chemical equation. Are you getting it? Yeah? Yes, today a lot of people visited the block list. I don't know what makes them think that I do not have the access to block, and I think they are in that zone wherein teachers have to, call someone to block, etc. That is their mistake, I think. Perfect. Let's have a look on the next reaction. For example, I've got the reaction like this. Cr2O7 dinegative plus C2O4 dinegative gives Cr tri-positive plus carbon dioxide. This is the reaction. Can you balance it? Can you balance it, people? Can you balance it on your own? You should be in a position to balance it. You should be in a position to balance it. What is the first thing? Get the n factors of reactants. N factor of this is 6. N factor of this will be C. Plus 3 to plus 4. Plus 3 to plus 4 change is 1. 1 is the change for 1. I have 2. So its n factor is 2. So make this 2 here. Make this 6 here. Now balance all the atoms except hydrogen oxygen. So 4 chromium, 4 chromium. 6 to the 12 carbon, 12 carbon. Right? Now it is the time for oxygen. How many oxygen atoms on the left side? 7 2s are 14 plus 6 4s are 24. 14 plus 24 is 38. How many on right side? 12 2s are 24. So right side is oxygen deficient. How many oxygen deficiencies? 14 oxygen deficiencies on right side. So add 14 water molecules on this side. Add 14 water molecules on this side. Now time for hydrogen. How many hydrogens here? 14 2s are 28. How many hydrogens on left side? No hydrogen. So left side is hydrogen deficient. How many hydrogen deficiencies? 28 hydrogen deficiencies. So add 28 H positives on this side. So this reaction is balanced. I believe it's clear. So this was oxidation number method in acidic medium. Now let's have a look on the oxidation number method in basic medium. Let's have a look on the oxidation number method in oxidation number method in which medium? In basic medium. Yeah? Oxidation number method in basic medium. Understand? See guys, again I'm taking a reaction. Let's try to balance it so that you understand how do we use it. Let's say this is the reaction taking place in a basic medium, right? This is the reaction which we need to balance in the basic medium. With the help of which method? Oxidation number method. Let me write the sequence of the things first. First of all, what do we need to do? Calculate the n factors of reactants. N factors of reactants. Okay. After that, crisscross the n factors. After that, after crisscrossing the n factors, balance all the atoms except hydrogen oxygen. After that, in acidic medium, we were supposed to balance oxygen. Now here we are not going to balance oxygen first. Here we'll balance negative charge first with the help of water molecules. After that, we'll be balancing oxygen with the help of water molecules. Over here, no need to balance hydrogens. Hydrogens automatically get balanced here. For example, have a look. This is the sequence. These are the steps which we need to follow. First of all, calculate the oxidation states. Calculate the n factors. 0 to -1. 0 to -1 means 0 to -1. Change is 1. 1 is the change for 1 atom out 2. So its n factor is 2. Iodine here is in +5 oxidation state. So +5, here iodine is in +7. +5 to +7. Change is 2. 2 is the change for 1 atom out 1 only, so 2. Crisscross these n factors. So this is 2. This is 2. Balance all the atoms except hydrogen oxygen. So 4 chlorine, 4 chlorine. 2 iodine, 2 iodine. So we have completed the process till here. Now it is the time to balance negative charge. Now is the time to balance negative charge. Is there any charge here? No. I'll say 1 IO3 molecule carries charge -1. So 2 IO3 molecules carry charge -2. 1 chlorine carries charge here -1. So 4 will carry -4. 1 IO4 carries charge -1. 2 carries -2. So on left side, the charge is -2. On right side, the charge is -6. So which side is negative charge deficient? I would say left side is the negative charge deficient. How many negative charge deficiencies on left side? -2, -6. I'll say 4 negative charge deficiencies on left side. So if there are 4 negative charge deficiencies on left side, add 4 OH negatives to that side which is negative charge deficient. So I did 4 OH negatives to that side which is negative charge deficient. Now balance oxygen with the help of water. How many oxygen here? 3 2s are 6, 6 4s are 10. So 10 oxygen atoms on left side. How many here? 4 2s are 8. 8 oxygen atoms on this side. 10, 8. So this side is oxygen deficient. How many? 2. So add 2 water molecules. Oxygen deficiency is removed with the help of water molecules. Now the reaction is balanced. The reaction is balanced, right? You need not to check it. Hydrogen automatically would have got balanced, by the way. You can check it. 4 hydrogen here. And here also there are 4 hydrogens. It's already balanced. Let's take one more example here so that it becomes like very much clear to you. For example, you have got the reaction in this format. MnO4 negative plus Br negative gives MnO2 plus BrO3 negative. Let's say this reaction you need to balance in the acidic medium. Sorry, in the basic medium. In the basic medium. No, I did not write water for negative charge. I wrote OH negatives for, it's not water, it's 4 times OH negative. That's what I wrote, right? 4 OH negatives. Then for oxygen, I wrote water. First negative charge. Okay, here you are telling. Oh, okay. Here you are telling. So here negative charge will be balancing with the help of OH negatives and oxygen with the help of water. In the question, I did it correctly. Okay. Now, see. First of all, get the n factor of MnO4 negative. +7 to +2. +7 to +4. +7 to +4. Manganese here is in +7. Here it is in +4. +7 to +4. N factor 3. -1 to +5. -1 to +5. Calculate change. Final minus initial. The value is 6. 6 is the change for one atom. I have only 1. So 6. Crisscross. 6 here, 3 here. After crisscrossing things, balance all the atoms except hydrogen oxygen. 6 manganese, 6 manganese. 3 bromine, 3 bromine. Now, after balancing, it is time for the negative charge to be balanced. 1 MnO4 molecule carries -1, so 6 will carry -6. 1 Br carries -1, 3 will carry -3. So -6 -3 comes out to be -9 on left side. On right side, 1 BrO3 -1, 3 BrO3 -3. That's all. So -9 on left hand side, -3 on right hand side. Which side is negative charge deficient? Right side is negative charge deficient. How many negative charge deficiencies on right side? 6 negative charge deficiencies. So add 6 OH negatives on this side. Add 6 OH negatives on the side which is negative charge deficient. Now after that, balance oxygen. So how many oxygen on left side? 6 4s are 24. How many oxygen on right side? 6 to 12, 3 3 9 plus 6. So 9 6 15 plus 12 is 15 plus 12 is 27. So 24 oxygen on left side, 27 oxygen on right side. Which side is oxygen deficient? LHS side. How many oxygen deficiencies? 3 oxygen deficiencies, right? So add 3 water molecules on that side which is oxygen deficient. Hydrogen you need not to check. That will be automatically balanced. 3 2s are 6 and 6 hydrogen this side also. Am I clear? Am I clear, people? So this was your oxidation number method balancing, right? How do we balance the reactions? With the help of oxidation number method in first acidic medium, then in the basic medium. If it is clear, let me know once in the chats quickly. If it is clear, let me know once in the chats quickly. Everyone. Everyone in the chats. I want everyone to write it in the chats if it is clear. If not, write it. Perfect, people. Got it. Koshal Sharma, this is the English channel. ये English channel है जहाँ पे अंग्रेजी में पढ़ाते हैं. हिंदी होती तो हिंदी में पढ़ा लेता. अपने नाम नहीं पढ़ा शायद चैनल का. It is Unacademy NEET English. Deepika, you can just drag the video a little back. It will be a replay for you, right? Why do you want me to explain this again? It will take a lot of time. Just drag the video back. It will be a replay for you. Yeah? We'll complete first of all ion electron method and then we'll take a break for 15 to 20 minutes. Okay? Telegram channel is Wassim Bhat Chemistry Official. Telegram channel is Wassim Bhat Chemistry Official. Okay? Chalo, let's have a look on one more method of balancing the redox reactions. Let's have one more method of balancing the redox reactions. That is ion electron method. I'll just give one example here. Ion electron method in which medium? In acidic medium. Ion electron method in which medium? Acidic medium. See guys, let me take one reaction. Let me take one reaction and let's try to balance the reaction with the help of ion electron method now. This is again very important method of balancing the reaction. For example, let me take the reaction like this. One simple reaction I'm taking. MnO4 negative plus Fe di positive gives Mn di positive plus Fe tri positive. Plus Fe tri positive. Okay. Let's say we need to balance this reaction with the help of ion electron method. In which medium? Acidic medium. My dear students, in case of ion electron method, what we need to do? The first step is write the oxidation states of all the elements. Write the oxidation states of all the elements. Number one. Okay. After that, break this reaction into two parts. Break the reaction into two parts. One would be called as oxidation half reaction and other would be called as the reduction half reaction. Let's first of all do till here. First thing, let's calculate the oxidation state of all the elements over here. Oxidation state of manganese here is +7. Here it is +2. Here it is +2. And here it is +3. Okay. So I have mentioned the oxidation states of all. Now, check which of the following species is undergoing oxidation and which is undergoing reduction. +7 to +2. +7 to +2. Decrease in the oxidation state means reduction. Means reduction. Okay. So MnO4 negative is undergoing reduction. Reduction means gain of electrons. Fe di positive +2 to +3. +2 to +3. Increase. Increase means oxidation. So Fe di positive is undergoing oxidation. So I got to know which species is undergoing reduction and which species is undergoing oxidation. Yeah? Right? Now people, I am going to break this reaction into two parts. One is your oxidation half reaction. One is your reduction half reaction. In oxidation half reaction, I can say Fe di positive is getting converted into Fe tri positive. Fe di positive is getting converted into Fe tri positive. Right? Fe di positive is getting converted into Fe tri positive. So Fe di positive is undergoing oxidation. Oxidation means loss of electrons. So I would say Fe di positive would be losing some electrons and getting converted into Fe tri positive. How many electrons it will be losing? Final minus initial. The value is 1. I would say Fe di positive is losing 1 electron, getting converted into Fe tri positive. Right? Now, in case of reduction half reaction, which one is undergoing reduction? MnO4 negative is undergoing reduction. And finally, after reduction, MnO4 negative is getting converted into Mn di positive. Perfect. Reduction means gain of electrons. So I would say MnO4 negative would be gaining some electrons, then getting converted into Mn di positive. Now, how many electrons it will be gaining? +7 to +2. Change is 5. So I would say it will be gaining 5 electrons. MnO4 negative would be gaining 5 electrons and getting converted into Mn di positive. Now, after breaking the main reaction into two parts, oxidation half reaction, reduction half reaction. Now, try to balance all the atoms except hydrogen oxygen. Balance except hydrogen oxygen. Balance all the atoms except hydrogen oxygen. So, here iron, iron balanced, manganese, manganese balanced. Okay, leave it. Balance the electrons. Balance the electrons. 1 electron here, 5 electrons here. So how do I balance the electrons? I'm multiplying first reaction by 5, second reaction by 1. When I multiply first reaction by 5, this becomes 5, this becomes 5, now this becomes 5 electrons. Multiplying with 1, no change. So I've balanced the electrons. After balancing the electrons, add the reactions. Add the reactions. After balancing the electrons, add the reactions. When we add the reactions, left hand side add, right hand side separately add. So I would say 5 electrons would get cancelled when we add them. So net reaction is going to be 5 times Fe di positive plus MnO4 negative. It gives 5 times Fe tri positive plus Mn di positive. Right? How many electrons got cancelled out? 5. So I would say N value here is 5. What does N mean here? N means number of moles of electrons exchanged in the net reaction. Number of moles of electrons exchanged in the net reaction, that is basically your N here. There are 5 moles of electrons exchanged in the net reaction. So we have reached till here. Now in acidic medium, what do? In acidic medium, we balance first oxygen with the help of water and then we balance hydrogen. First we balance oxygen with the help of water and then we balance hydrogen with the help of H positive. So balance oxygen. 4 oxygen on this side, so add 4 water molecules on this side. 8 hydrogen on this side, so add 8 H positives on this side. The reaction is balanced. Now it's a balanced chemical equation. Yeah? Is it clear? Is it clear, people? Now it's a balanced chemical equation. Now guys, let me tell you one more important thing over here. What is the value of N? How many moles of electrons are exchanged? 5. Let me show you one more way of calculating the N factor. Let me show you one more way. N factor is always equal to N divided by stoichiometric coefficient. This is the actual way of calculating N factor. Whatever way I was teaching you till now to calculate N factor, that was basically the trick, the shortcut. The actual way of calculating N factor is get the number of moles of electrons exchanged and divide that with stoichiometric coefficient. For example, N factor of Fe di positive. N is 5, divided by stoichiometric coefficient is 5. So 5 by 5 comes out to be 1. 5 divided by 1 comes out to be 5. 5 divided by 5 will be 1. And 5 divided by 1 will be 5. So these are the N factors of your reactants products. This is the N factor of Fe di positive, N factor of MnO4 negative, N factor of Fe tri positive, N factor of Mn di positive. Same things we can get by our method. Plus 2 to plus 3. Change is 1. 1 is the change for one atom. I have 1 only. So its N factor is 1. Plus 7 to plus 2. Plus 7 of manganese to plus 2. So change is 5. 5 is the change for one atom. I have got one atom of manganese only. So 5. Got it? Do you want one more example here in this? Or it's clear? Do you want one more example here in this? Quickly. Do you want one more example here in this? How will they ask question in balancing? They'll give a reaction like this. They'll tell you what are the stoichiometric coefficients of all these. Nothing else. You can use any method. The choice is all yours. Let's have one more example on this so that it becomes like properly clear. For example, I'm taking the reaction as Cr2O7 dinegative plus C2O4 dinegative. It gives chromium tri positive plus carbon dioxide. Let's say this reaction I need to balance in which medium? In acidic medium. Let's say this reaction I need to balance in acidic medium with the help of which method? Ion electron method. Ion electron method. So what is my first step? Tell me the first step. Write the oxidation state of each element. Here it is plus 6. Here it is plus 3. Here it is plus 3. And here it is plus 4. I hope you know how to calculate the oxidation states now, right? By using the formula stuff, you know it. Now, Plus 6 to plus 3. Decrease means reduction. So this is undergoing reduction. If this is undergoing reduction, it will be gaining electrons. Plus 3 to plus 4. Oxidation. It will be losing electrons. Now break the main reaction into two parts. Oxidation half reaction, reduction half reaction. In the oxidation half reaction, oxalate is getting converted into carbon dioxide. Oxalate ion is getting converted into carbon dioxide. Now, first of all, we have to balance all the atoms except hydrogen, oxygen here only. So 2 carbon, so make it 2 carbon. Okay. Now, oxalate is undergoing oxidation. So it will be losing electrons, then will be getting converted into carbon dioxide. So how many electrons this oxalate will be losing? Plus 3 to plus 4. Change is 1. 1 is the change for 1. I have 2. So I would say it will be losing 2 electrons. Now, reduction half. Plus 6 to plus 3. Plus 6 to plus 3. Decrease means reduction, gain of electrons. So I would say when Cr2O7 di-negative will be getting converted into Cr tri-positive, I would say it will be gaining electrons. But before that, balance all the atoms except hydrogen, oxygen. So 2 chromium, 2 chromium. Now, I would say Cr2O7 di-negative will be gaining some electrons, then getting converted into Cr tri-positive. Now, how many electrons it will be gaining? Plus 6 to plus 3. What is the change? 3. 3 is the change for 1 atom. I have 2. So 3 2s are 6. Cr2O7 di-negative is gaining 6 electrons, then getting converted. Yeah? Now, people, what is the next thing? The next thing is balance the electrons. So 2 here, 6 here. So multiply this reaction with 3. So when you multiply with 3, this becomes 3, this becomes 3 2s are 6, and this becomes 3 2s are 6. Now add these two reactions. When you add these two reactions, 6 and 6 got cancelled. So N value is 6 here. My net reaction is going to be 3 times C2O4 di-negative plus Cr2O7 di-negative gives 6 times carbon dioxide plus 2 times chromium tri-positive. This is my net reaction. This is my net reaction. If this is my net reaction, now reaction is to be balanced in acidic medium. In acidic medium, we balance oxygen first. So 4 3s are 12 oxygen, 12 plus 7. So 19 oxygen on left side. How many on right side? 6 2s are 12. 12 oxygen on right side. Which side is oxygen deficient? Right side. How many oxygen deficiencies? 7. So add 7 water molecules. So that side which is oxygen deficient. Now, balance hydrogen. 14 hydrogen on this side. So add 14 H positives on this side. Now the reaction is balanced. So if I ask you to calculate the N factor, you will say 6 divided by 3 is 2. For this one, 6 divided by 1 is 6. For this one, 6 by 6 is 1. For this one, 6 divided by 2 is 3. So these are the respective N factors of reactants products as well through balancing over here. Should balance charge. Charge you have to balance in basic medium. I am showing in acidic medium. In acidic medium, we balance oxygen first, then hydrogen. Charge is automatically balanced there. In basic medium, we balance charge first, then oxygen. Hydrogen is automatically balanced there. Okay. So this was balancing of the redox reaction in acidic medium through ion electron method. Yeah. Perfect. Now let me show you the same method in the basic medium. Let me show you the ion electron method. Ion electron method in which? In basic medium. Ion electron method in basic medium. Let me show one example of this as well. For example, let's take the reaction as Cl2 plus IO3 negative gives Cl negative plus IO4 negative. So in basic medium, everything is same. It is just one thing is different. First of all, write the oxidation states of all elements. Of all elements. Right? After that, break the main reaction into oxidation half and reduction half. Balance all except hydrogen, oxygen. Then balance electrons. Since now the reaction is in basic medium, now balance the negative charge first with the help of water. Okay, just a second. After balancing electrons, add the reactions. After adding reactions, balance negative charge with the help of OH negatives. Then balance oxygen with the help of water molecules. No need to balance hydrogen here. They would be already balanced. Okay, have a look now. First of all, calculate the oxidation state of each element. Chlorine here is 0, iodine here is +5, chlorine here is -1, iodine is +7, right? Calculate the oxidation states of all. After calculating oxidation states of all, 0 to -1 means reduction, +5 to +7 means oxidation. So this is undergoing reduction, it will be gaining electrons. This will be undergoing oxidation, it will be losing electrons. So write oxidation of reaction as well as reduction of reaction. Write oxidation of as well as reduction of. Well, in oxidation of reaction, I must say IO3 negative is finally getting converted into what? IO4 negative. This is the reaction. Now, since IO3 negative is undergoing oxidation, so I must say this IO3 negative will be losing some electrons. How many? +5 to +7. So change is 2. I would say IO3 negative will be losing 2 electrons, getting converted into IO4 negative. Yeah? Now, reduction of Cl2 is undergoing reduction. Cl2 is undergoing reduction and finally getting converted into Cl. So first here only I'll be balancing chlorine, 2 chlorine, 2 chlorine. Now 0 to -1, decrease means reduction, gain of electrons. So this Cl2 will be gaining some electrons, then getting converted into Cl negative. How many electrons it will be gaining? 0 to -1, change is 1. 1 is the change for 1, but out 2. But out 2 here. So 2 electrons it will be gaining. Now electrons are already balanced, so add them up. So 2 gets cancelled. N value comes out be 2 here. If N comes out be 2, add the 2 reactions. I must say IO3 negative plus Cl2 gives what? IO4 negative plus 2 times Cl negative. Now since the reaction is taking place in basic medium, so balance the negative charge. 1 IO3 carries charge -1, 1 IO4 carries charge -1, 1 Cl carries charge -1, 2 will carry -2, so -3. So -1 on left side, -3 on right side. Which side is negative charge deficient? Left side. How many negative charge deficiency? 2. So add 2 OH negatives. Right? And after balancing negative charge, balance oxygen. How many oxygen on left side? 3 plus 2, 5. How many oxygen on right side? 4. Which side is oxygen deficient? Right side. How many oxygen deficiency is there? 1. So add 1 water molecule. No need to check hydrogen. Hydrogen would be automatically balanced. Check 2 hydrogen here, 2 hydrogen here. The balance reaction. Now N is 2. So what should be the N factor of IO3 negative? 2 divided by 1 is 2. 2 divided by 1 is 2. 2 divided by 1 here is 2. 2 divided by 2 is 1. So these are the respective N factors of the reactants products as well. So this is how you use Yes, Janvi, you have to do that. Okay. So this is how you use ion electron method in basic medium. Okay. This is how you use ion electron method in basic medium. Now guys, one more thing in balancing which you would be remembering. What is that? That is how do we balance the disproportionation reaction? Balancing of disproportionation. Balancing of disproportionation. How do we balance the disproportionation? One thing I'm telling you, whenever you are supposed to balance a disproportionation reaction, always go through ion electron method. It will always give you accurate results. Whenever you are supposed to balance a disproportionation reaction, always go through ion electron method. For example, I've got the reaction like this. Let's say I've got the reaction like this. Br2 gives Br negative plus BrO3 negative. For example, I want to balance this particular reaction in basic medium. I want to balance this particular reaction through basic medium. What is my first step? Oxidation state of all. So 0, -1, here plus 5, right? Now, 0 to -1 means decrease. Decrease means reduction. Reduction means gain of electrons. 0 to plus 5 means increase. Increase means oxidation. Oxidation means loss of electrons. Right? Your oxidation of reaction and reduction of reaction. In the oxidation of reaction, Br2 is getting converted into Br2 is getting converted into BrO3 negative. So 2 bromine, 2 bromine. Now, Br2 is undergoing oxidation. It will be losing electrons. How many? 0 to plus 5. Change is 5. 5 is the change for 1. I have 2. So 5 2s are 10. 10 electrons it is losing. Br2 is losing 10 electrons, then getting converted into this. Now, reduction. 0 to minus 1. During reduction, Br2 will be gaining some electrons and finally getting converted into Br negative. So if this is 2Br, make this 2Br. Now 0 to minus 1, change is 1. 1 is a change for 1, I have 2. So Br2 will be gaining 2 electrons, then getting converted into 2 times Br negative. Right? Now balance the electrons. So I'm multiplying this reaction by 5. This becomes 5. This is 5 2s are 10. This is 5 2s are 10. Balanced. Now add the reactions. So 10 electron cancel. 5 Br2 plus Br2 makes it 6 Br2. Gives 2 times BrO3 negative plus 10 Br negative. Since the reaction is in basic medium we balance negative charge first. There is no negative charge here. 1 BrO3 carries minus 1, 2 carries minus 2. 1 Br minus 1, 10 carries minus 10. So the value here is minus 12. So on right side, the net charge is minus 12. So left side, there is no negative charge. So left side is negative charge deficient. How many? 12 negative charge deficiency. 12 negative charge deficiency means add 12 OH negatives. Now balance oxygen. How many oxygen on left side? 12. On right side, 6. So right side is oxygen deficient. How many? 6 oxygen deficiency means add 6 water molecules on this side. Now the reaction is already balanced. It is balanced. What is the N value? N value here is 10. Right? Get the N factor of Br2. 10 divided by 6 comes out to be 5 by 3. 10 divided by 2 is 5. 10 by 10 is 1. So these are the respective N factors of these reactants and products in this reaction as well. And if you remember, my dear students, if you remember, in the question, they'll mention whether the reaction is taking place in acidic or basic medium. And my dear students, if you remember, this Br2 here was undergoing disproportionation. And I have taken this example when I told you N factor of the substance that undergoes disproportionation. N1, N2 divided by N1 plus N2. If you remember, the answer came out to be same here also. There it was 5 by 3. Here also it is 5 by 3. Correct? So this was your balancing of redox reactions with the help of oxidation number method. In which medium? In basic medium as well as acidic medium. Perfect. Let's take a break. And after the break, we shall be moving on to the titration part. But I would want every one of you to be back. And I need a promise for that. Yeah? I need a promise for that. It's 12:33. So break till 1, huh? I would want every one of you to be back, guys, because I am now going to teach you something important. The redox titration maybe I would have taught before also, but acid-base titration I have never taught here in redox. This is the first time I'm going to teach you acid-base titration as well in redox. Okay? This is the first time I'm going to teach you volume strength in redox on YouTube. So be back on time. 1 sharp. Everyone means everyone. Perfecto? Chalo guys, I'll see you exactly at 1. Take care till then. Have some tea or coffee till then. Chalo, see you. Is everybody back? Is everybody back? Yeah. Is everyone back, people? Quick. Perfect, perfect. So tell me all the concepts, whatever we discussed till now, is every single thing clear? Tell me in the chats, quickly. Whatever things we discussed till now, are all the single things clear? All right, so let's get going then. Let's get started. How much time more? 2 more hours. 2 more hours, that's it. Done? Two more hours, that's it. All ready then? All ready, all ready. All ready, people? So let's have a look on the concept of equivalence. Okay, concept of equivalence. Dear students, the way we calculate number of moles of any substance, the way we calculate number of moles of any substance, in the similar way we calculate number of gram equivalents of any substance. The way we calculate moles of a particular substance, in the similar way we calculate gram equivalents of the substance as well. And how do we calculate gram equivalence of a substance? It is always equal to given mass of the substance in grams divided by equivalent mass of the substance. Given mass of the substance in grams divided by equivalent mass of the substance. How do we calculate moles? Given mass of substance divided by molar mass of substance. But here, in order to calculate the number of gram equivalents of the substance, what is the result? Given mass of the substance divided by equivalent mass of the substance. Number one. The second result with the help of which we can calculate the number of gram equivalents of substance, it is always equal to number of moles of the substance multiplied by n factor of the substance. Number of moles of the substance multiplied by n factor of the substance. So right now we have got two results, two formulas by means of which we can calculate the number of gram equivalents of a particular substance. It is always equal to given mass of the substance in grams divided by equivalent mass of the substance, or number of moles of the substance multiplied by n factor of the substance. Okay. Now people, similarly, there is one more term. Number of milli equivalents of the substance. Number of milli equivalents of the substance is equal to given mass of the substance in grams divided by equivalent mass of the substance multiplied by 1000. Or one more result, number of millimoles of the substance multiplied by n factor of the substance. These are the two results which we have for now to calculate the number of milli equivalents of a particular substance. And my dear students, let me tell you, number of milli equivalents of the substance is always equal to number of gram equivalents of the substance multiplied by 1000. Number of milli equivalents of the substance is always equal to number of gram equivalents of the substance multiplied by 1000. Okay? These are certain results which I would want you guys to remember from now on. Number of gram equivalents given mass by equivalent mass, or number of moles multiplied by n factor. Number of milli equivalents given mass of substance by equivalent mass of substance multiplied by 1000, or number of millimoles of the substance multiplied by n factor. Number of milli equivalents of the substance is always equal to number of gram equivalents of the substance multiplied by 1000. Simple. As simple as that. Yeah? For example, let's say I'm writing one simple and basic question. Let's say I'm asking you to calculate the number of milli equivalents and gram equivalents present in 31.6 grams of KMnO4 in acidic medium. In acidic medium. So basically, as per the question is concerned, we are given with 31.6 grams of KMnO4. In which medium? In acidic medium. In acidic medium. You know, n factor of KMnO4 in acidic medium is how much? It is 5. Because you know, in acidic medium, KMnO4 gets converted into what? KMnO4 gets converted into Mn di positive. Right? So, plus 7 to plus 2 changes 5. So, its n factor is 5 basically. Right? So, what is the mass of KMnO4 we are given with? 31.6 grams. So, let me calculate the number of gram equivalents of KMnO4. I'll be directly using the result. And you know the result. What is the result? Number of gram equivalents of KMnO4 is equal to the mass of KMnO4 in grams divided by what? Divided by equivalent mass of KMnO4. Now, what is the given mass of KMnO4? That is 31.6 grams. Equivalent mass of KMnO4 means molar mass of KMnO4 divided by n factor. When you solve this, the value comes out to be 1. When you solve this, the value comes out to be 1. What does it mean? It means that 31.6 grams of KMnO4 in acidic medium. It means that we have got 1 gram equivalent of KMnO4 in acidic medium. Whether you want to say that we have got 31.6 grams of KMnO4, or you can say we have got 1 gram equivalent of KMnO4 in acidic medium. Correct? Similarly, if you got the gram equivalents of KMnO4, you can calculate the number of milli equivalents of KMnO4 as well. So I would say number of milli equivalents of KMnO4 will be equal to gram equivalents of KMnO4 multiplied with 1000, right? So you can say that we have got 1000 milli equivalents of KMnO4 as well. Perfect. You can say we have got 1 gram equivalent of KMnO4, or you can say we have got 1000 milli equivalents of KMnO4, or you can directly say we have got 31.6 grams of KMnO4 in acidic medium. All the three things have got the same meaning over here. Yeah? Sir, how have you written the n factor of KMnO4 as 5? Sir, I have taught this 100 times, right? KMnO4 in acidic medium gives Mn di positive. This is something which I told you when I started the n factor. So plus 7 to plus 2, how is the change? Final minus initial, that's 5. So its n factor is 5, right? Its n factor is 5. We have discussed this hundreds of times till now. KMnO4 n factor 5, K2Cr2O7 n factor 6 in acidic medium. Okay? Anyways, let's have a look on a term called as normality. Normality, which is represented by capital N. Now, people, how do we exactly define the term normality? Let me write its definition first. Normality is defined as number of gram equivalents of solute present in 1 liter of solution. How do we define molarity of the solution? Number of moles of solute present in 1 liter of solution. And here, instead of moles of solute, I'm using gram equivalents of solute, nothing else. Number of gram equivalents of solute present in 1 liter of solution, that defines normality of the solution. For example, imagine that in 1 liter solution, there are 5 gram equivalents of solute. You'll directly say normality of the solution is 5. In 1 liter of solution, imagine there are 10 gram equivalents of solute. You'll directly say normality of the solution is 10. In 1 liter of solution, there are X gram equivalents of solute. You'll directly say normality of the solution is X. Simple. So the number of gram equivalents of solute which are present in 1 liter of solution, that defines normality of the solution. Now we will normality. The first result to calculate normality is going to be number of gram equivalents of solute divided by volume of solution in liters. Now gram equivalents of solute I can write as mass of solute in grams divided by equivalent mass of solute, and instead of volume of solution in liters, for example, I'm writing volume of solution in ml and here I'm multiplying with 1000. This is the second result to calculate normality. Or there is one more direct result. You can say normality of the solution is equal to molarity of the solution multiplied by n factor of solute. These are the 3 results with the help of which we can calculate normality of a solution. These are the 3 results with the help of which we can calculate normality of the solution. Okay. Now, my dear students, if I ask you, what are going to be the units of normality? Units of normality, it's going to be gram equivalents per liter. Gram equivalents per liter. If I ask you whether normality is temperature dependent or independent, you'll directly say it is a temperature dependent concentration term. Because in the formula of normality, there is volume. And any concentration term whose formula contains volume, that becomes the temperature dependent one. Okay. For example, sometimes if I write 2 normal NaCl aqueous solution, what does it mean? How can we decode this statement? It simply means that 2 gram equivalents of solute is your NaCl. 2 gram equivalents of solute are present in 1 liter of solution. It means that 2 gram equivalents of solute are present in 1 liter of solution. Simple. For example, sometimes I write 10 normal NaCl aqueous solution. It means 10 gram equivalents of NaCl are present in 1 liter of solution. Right? I believe this is clear. I believe this is clear. For example, if I write a question like this, calculate the normality of a solution in which 63 grams of oxalic acid dihydrate in which 63 grams of oxalic acid dihydrate are present in 500 ml of solution. Can't we solve this? We are just supposed to calculate normality of the solution. And you know, normality of the solution is equal to mass of solute in grams multiplied by 1000 divided by equivalent mass of the solute in grams multiplied by volume of solution in ml. Simple. What is the mass of solute in grams? 63 grams multiplied by 1000. Equivalent mass of solute, equivalent mass of this oxalic acid dihydrate will be molar mass of oxalic acid dihydrate, which is 126, divided by its n factor. Since it's acid, it's going to give 2 H positive, so its n factor is 2. And volume of solution in ml is given to me as 500, right? So this 63 cancel. The value comes out to be 2. So I would directly say normality of the solution is 2. Now, if normality of the solution is 2, you know normality is equal to molarity multiplied by n factor of solute. So from this particular result, you can calculate molarity of the solution as well. Normality divided by n factor of solute. Normality we got to know as 2. N factor of solute, n factor of oxalic acid is 2. So I would say molarity of the solution is nothing but 1. Simple, basic. For example, if I make some more questions. 0.1 normal HCl aqueous solution. Can you let me know what will be its molarity? Number 1. Number 2, 0.2 molar H2SO4 aqueous solution. Just tell me its normality. For example, 0.3 molar Al2SO4 whole thrice, right? Aqueous solution. Just tell me its normality. 0.5 normal BOH whole thrice aqueous solution. Just tell me its molarity. Can you solve these sort of basic questions over here? Yeah? You should be in a position to solve all this stuff. See guys, you know, normality is equal to molarity multiplied by n factor of solute. Correct? Or you can say molarity is equal to normality divided by n factor of solute. Now, in the first question, normality is given. Molarity is to be calculated. So, molarity is just going to be equal to normality of the solution multiplied by n factor of solute. What is the normality of the solution? 0.1 divided by. What is the n factor of HCl? N factor of HCl is 1. It gives 1 H positive only. So, normality of the solution is 0.1. In this case, molarity is given. Normality is to be calculated. So, normality is nothing but molarity multiplied by n factor of solute. What is molarity here? 0.2. What is n factor of this solute? N factor of H2SO4? That is 2. The value comes out to be 0.4 normal. Similarly, this is the salt. What will be the n factor of this salt? LCM of charge present on cation and anion. I hope you remember. So, its n factor is going to be 6. So, 0.3 multiplied by 6 is going to be 1.8. So, its normality is 1.8. Similarly, boric acid, its n factor is 1. Since its normality is 0.5, so its molarity will be also 0.5. Correct? Because its n factor is 1. We have discussed it. Clear? Very simple. Now guys, here if you understand, if you look at one more thing, you know, normality is equal to gram equivalence divided by volume of solution in liters. Can I say gram equivalence will be equal to normality multiplied by volume? So, here I got one more result to calculate gram equivalence. Remember, the number of gram equivalence is also equal to normality of the solution multiplied by volume of solution in liters. This is one more way of calculating gram equivalence. Normality of the solution multiplied by volume of solution in liters. Similarly, to calculate milli equivalence, I can use one more result. Normality of the solution multiplied by volume of solution in milliliters. So, in short, I would say, we have got 3 results to calculate gram equivalence. We have got 3 results to calculate milli equivalence. One result is in terms of mass, another one is in terms of moles or millimoles, and the third one is in terms of normality. Normality multiplied by volume of the solution in liters gives me gram equivalence. Normality multiplied by volume of solution in ml gives me the milli equivalence. As simple as that. Okay? Perfect, people? Is it clear? Is it clear? Can you see this one simple and basic question? Calculate the gram equivalence in 50 ml of 0.5 normal NaOH, right? So normality is given, volume is given. Volume is given in ml. So normality is given, volume of the solution is given in ml. What do I get from here? Number of milli equivalents of solute. Solute here is NaOH. So normality is 0.5. Volume of the solution is 50 ml. So this is going to give me the number of milli equivalents of NaOH. So I got the milli equivalence. Similarly, you can convert milli equivalence into gram equivalence as well. You know, number of milli equivalents is always equal to number of gram equivalents multiplied by 1000. So I would say number of gram equivalents will be equal to number of gram equivalents will be equal to number of milli equivalents divided by 1000. Milli equivalents we have calculated from here. 0.5 multiplied by 50 divided with 1000. What do you get? You get number of gram equivalents. Done. Right? Perfect. Perfect, guys. Now we are going to come to the actual topic, that is your titration part. Okay? Redox titration. Redox titration we are going to start now. Before making you explain the redox titration, right? Before showing you the questions of redox titration, let me tell you the concept behind it, which is what we call as law of equivalence, of law, or you can say law of chemical equivalence. And this is the law which we are going to use in the titration questions. Law of equivalence, law of chemical equivalence. Let me write case 1 over here. My dear students, what this law of chemical equivalence states. See, for example, we have got the reaction N1A plus N2B. Imagine it gives N3C plus N4D. Imagine it gives N3C plus N4D. Law of equivalence says that, as per law of equivalence, I can say, gram equivalence, the number of gram equivalents of A reacted in the reaction is always equal to the gram equivalence of B reacted in the reaction, which is always equal to gram equivalence of C formed in the reaction, which is always equal to gram equivalence of D formed. One simple statement I wrote. As per law of equivalence, gram equivalence of reactants reacted is always equal to the gram equivalence of product formed. So whatever gram equivalence of A has reacted in the reaction, same gram equivalence of B would have reacted. Same gram equivalence of C would have formed. Same gram equivalence of D would have formed. Right? This is the first statement in terms of gram equivalence. Similarly, as per law of equivalence, you can also say milli equivalence of A reacted in the reaction will be always equal to milli equivalence of B reacted, will be always equal to milli equivalence of C formed, will be always equal to milli equivalence of D formed. Right? So in a chemical reaction, the number of equivalents of A reacted will be always equal to the number of equivalents of B reacted, always equal to number of equivalents of C formed, always equal to number of equivalents of D formed. This is case number 1. So just these two statements you have to write and you'll be done. You'll be sorted. Case number 1. Case number 2, people. Case number 2. Case number 2. Imagine that you have got a container here. In this container, imagine you have got 3 substances present, 1, 2, and 3. And in this container, we are adding the 4th substance. For example, there's a mixture here in the container. The mixture is containing 3 substances. Now you are adding 4th substance. Okay, you are adding 4th substance. If, for example, if 4 reacts with 1, 2 as well as 3. If the 4th substance will be reacting with A, 1, 2 as well as 3. At that point of time, your equivalent concept says that gram equivalence of 1 reacted plus gram equivalence of 2 reacted plus gram equivalence of 3 reacted will be equal to the gram equivalence of 4 reacted. Or you can write the same statement in terms of milli equivalence. You can say milli equivalence of 1 reacted plus milli equivalence of 2 reacted plus milli equivalence of 3 reacted has to be equal directly the milli equivalence of 4 reacted. This is the case when the mixture is containing 3 substances, right? The mixture is containing 3 substances and you are adding the 4th one. And I'm assuming the 4th one is reacting with 1, 2 as well as 3. Okay? But here comes one more case also. If, for example, if 4 reacts only with 1 and 2, if 4 reacts only with 1 and 2, then what do we do at that time? Let's say 4 is reacting only with 1 and 2, it's not reacting with 3. So at that point of time, your equivalent concept says that gram equivalence of 1 reacted plus gram equivalence of 2 reacted has to be directly equal to gram equivalence of 4 reacted, leaving 3 as such. Or you can say milli equivalence of 1 reacted plus milli equivalence of 2 reacted has to be equal to milli equivalence of 4 reacted. Perfect, right? Before showing you the application part, before showing you how to use these statements in the questions, there are few things which I want you guys to remember directly from now onwards. What are those things? What are those things? See guys, first of all, if you talk about KMnO4, tell me the N factor of KMnO4 in acidic medium. From now onwards, you'll remember it directly. N factor of KMnO4 in acidic medium is 5. Because in acidic medium, KMnO4 gets converted into Mn dye positive. So plus 7 to plus 2 changes 5. So its N factor is 5. Number 1. Number 2, for example, imagine that you have got FeSO4. You have got FeSO4. Let's say FeSO4 is going to react either with KMnO4 or K2Cr2O7 in acidic medium. Now, something which you all must be knowing. In case of FeSO4, iron is present in dye positive state. And you know KMnO4 as well as K2Cr2O7 converts Fe dye positive into what? Fe tri positive in acidic medium. If Fe dye positive gets converted into Fe tri positive, so change in the oxidation state is 1. So its N factor is 1. So remember, whenever you see KMnO4 or K2Cr2O7, right, reacting with FeSO4 in acidic medium, remember the N factor of FeSO4 will be taken as 1. Because in FeSO4, Fe dye positive gets converted into Fe tri positive. Plus 2 to plus 3 changes 1. Right? This is the N factor of FeSO4 in the acidic medium when it reacts with KMnO4 or K2Cr2O7. Correct? This is something which I want you guys to remember. Its N factor here is 1. Right? For example, you have got oxalate ion, C2O4 dye negative. Imagine this C2O4 dye negative is reacting with KMnO4 or K2Cr2O7 in acidic medium. You know, K2Cr2O7 as well as KMnO4 in acidic medium converts oxalate into carbon dioxide. Oxalate into carbon dioxide. So carbon here is in plus 3. And in carbon dioxide, carbon is plus 4. So plus 3 to plus 4, change is 1. 1 is the change for 1. I have 2. So its N factor here will be taken as 2 directly. Imagine instead of oxalate ion, you have got oxalic acid. Its N factor will be also 2. Imagine you have got sodium oxalate. Its N factor will be also taken as 2. Imagine you have got potassium oxalate. Its N factor will be also 2. Okay, but if you have ferrous oxalate, FeC2O4, my dear students, in FeC2O4, here you have got oxalate ion, C2O4 dye negative. So this should be Fe dye positive. And when it's treated with KMnO4 or K2Cr2O7, I would say KMnO4, K2Cr2O7, first of all, will convert Fe dye positive into Fe tri positive and will convert oxalate into carbon dioxide. So this becomes that species in which the oxidation state of more than one element changes. Iron is going from plus 2 to plus 3. Carbon is going from plus 3 to plus 4. And how do we calculate its N factor? If you remember, it is always equal to N1 plus N2. Therefore, its N factor will come out to be 3, which this is something which we have discussed already in the N factor calculation. So here I want you guys to remember it directly. For example, you have got ferric oxalate, Fe2, C2O4 whole thrice. Now this is, for example, reacting with KMnO4 or K2Cr2O7. Here iron is already in plus 3 oxidation state. So KMnO4 or K2Cr2O7 is not going to react with this part because iron is already in plus 3. If it was plus 2, then it would have got converted into plus 3. But here iron is in plus 3 oxidation state. So KMnO4 or K2Cr2O7 is not going to react with this one. So I would say KMnO4 K2Cr2O7 is going to react only with this one in acidic medium and will convert this oxalate into carbon dioxide. So plus 3 to plus 4. Change is 1. 1 is the change for 1. We have 3 to the 6. So its N factor you will directly remember as 6. Yeah? Its N factor you will directly remember as 6. Perfect, people? Its N factor directly you will remember at 6. Similarly, if you have got more salt, I hope you would have heard about more salt somewhere. When KMnO4 or K2Cr2O7 is treated with more salt, in more salt, only Fe dye positive gets converted into Fe tri positive. Therefore, change is 1. N factor is 1. n factors 1. If KMnO4 or K2Cr2S1 reacts with H2O2, you know, KMnO4, K2Cr2S1 converts H2O2 into O2, right? So, H2O2 into O2. Here oxygen is in -1. In O2, oxygen is in 0. -1 to 0. Change is 1. 1 is the change for 1. I have 2. So, its n factor will be directly taken as 2. Right? Its n factor will be directly taken as 2. Perfect, guys? So, these are some of the n factors which I want all of you to remember, because if you remember them, then easily we can solve the questions. Easily we can solve the questions. Okay, one more. Cu2S. When it reacts with KMnO4, K2Cr2S1, takes n factor as 8, and CuS takes n factor as 6 on reaction with KMnO4 or K2Cr2S1 in acidic medium. So these are some of the common n factors which you will see in the redox titrations. Okay, perfect. Actually, tell me one thing. Imagine you have got Fe2SO4 whole thrice. Tell me, is it going to react with KMnO4 in acidic medium? Just check it out. See, first of all, crisscross things. So take this 3 over here, take this 2 over here. So iron here is in +3. KMnO4 does not react with Fe +3. Right? It does not react with Fe +3. That reacts with Fe +2 and converts Fe +2 into Fe +3. But here already iron is in +3. So KMnO4 is not going to react with this part. Sulfur already here is in +6 oxidation state, maximum oxidation state. So KMnO4 is the oxidizing agent, right? That oxidizes others. So KMnO4 cannot oxidize this part also, because sulfur is already present in its maximum oxidation state. So in short, KMnO4 K2Cr2S1 cannot react with ferric sulfate in acidic medium. I hope I'm clear. Because iron already +3, sulfur already in maximum. So KMnO4, which is a strong oxidizing agent that oxidizes others, that increases the oxidation state of others. Here, sulfur is already in maximum oxidation state. So KMnO4 cannot increase its oxidation state. Right? Here, iron is in tri-positive. If it was in di-positive, then it would have converted it into tri-positive. I hope it's clear. So now, let's try to use all this stuff in the questions so that you'll understand what kind of questions are asked from the titration part. This is the first question, guys. What volume of 0.1 molar KMnO4? What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar, 0.3 molar ferric oxalate? So, as per the question, these two are going to react. These two are going to react. Calling this as number 1, calling this as number 2. The question says what volume of 0.1 molar KMnO4? Molarity of KMnO4 is given. Volume of KMnO4 is to be calculated. Is required to oxidize 100 ml of 0.3 molar. Molarity of ferric oxalate is 0.3. Volume of ferric oxalate is 100 ml. Perfect, right? So since these two are going to react, they'll form the products as well. Now, do we remember their n factors? N factor of KMnO4 in acidic medium is 5. N factor of ferrous oxalate in acidic medium is 3, right? If you know molarity of KMnO4, N factor of KMnO4, if you multiply these two, can't we get normality of KMnO4? 0.5, this multiplied by this. Similarly, this multiplied by this, can't we get normality of ferrous oxalate? 0.9. Now, since these two are going to react, correct? Since these two are reacting, KMnO4 is reacting with ferrous oxalate. So, what is law of chemical equivalence all about? Law of chemical equivalence says that gram equivalence of KMnO4 reacted will be equal to gram equivalence of ferrous oxalate reacted, or milli equivalence of first reacted is equal to milli equivalence of second reacted. Now, which statement you are going to use? Are you going to use the statement in terms of gram equivalence or milli equivalence? That depends on the unit of volume. Volume here is in ml. If volume is in ml, that means I'll be using the statement in terms of milli equivalence. I'll say milli equivalence of KMnO4 reacted has to be equal to milli equivalence of ferrous oxalate reacted. How do we calculate milli equivalence? There are 3 formulas to calculate milli equivalence. One in terms of mass, one in terms of millimoles, one in terms of normality. So instead of milli equivalence of 1, I'll write normality of 1 multiplied by volume of 1 in ml. Instead of milli equivalence of 2, I'll write normality of 2 multiplied by volume of 2 in ml. Correct? So normality of 1 here will be 0.5. Volume of 1 is to be calculated. Normality of 2 is 0.9. volume of 2 is 100 ml. So V1 after solving comes out to be 180 ml. What is the meaning of this 180 ml? Tell me that. What is the meaning of this 180 ml? It means that 180 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in which medium? In acidic medium. The class will run for 1 hour more. Okay? It will run for 1.5 hour more. Right? I hope this particular question is clear and you will be able to solve this sort of a question on your own from now on. Let's have a look on the second question. Let's see what the question is. Simple, guys. What volume of 0.1 molar KMnO4? What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar FeSO4 in acidic medium? So now these two are reacting as per the question, right? Let me call this as number 1. Let me call this as number 2. Before writing any sort of data, tell me, do you remember their N factors in acidic medium? N factor of KMnO4 in acidic medium is 5. N factor of ferrous sulfate in acidic medium is 1. Few minutes back only we discussed. Okay. Now, molarity of KMnO4 is given to me as 0.1. Volume of KMnO4 is to be calculated. Molarity of ferrous oxalate is given to me as 0.2. Its volume is also given to me in ml, that is 100 ml. Now, the first thing, molarity multiplied by N factor, that gives me normality. So this 0.5. Molarity multiplied by N factor, that gives me normality. So it is going to be 0.2. So I got the normalities of both these, right? Now, what does equivalent concept say? Equivalent concept is going to say us that milliequivalence of KMnO4 reacted has to be equal to milliequivalence of your FeSO4 reacted, right? So I can say milliequivalence of 1 reacted has to be equal to milliequivalence of 2 reacted. Now, milliequivalence of 1 reacted can be written as normality of 1 multiplied by volume of 1 in ml. Milliequivalence of 2 can be written as normality of 2 multiplied by volume of 2 in ml. Normality of 1 we know 0.5. Volume of 1 is to be calculated. Normality of 2 is 0.2. Volume of 2 is 100 ml. So V1 from here after solving comes out to be 40 ml. What is the meaning of this 40 ml? It means that 40 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar FeSO4 in which medium? In acidic medium. I believe these sort of questions you can easily solve from now on. Am I clear with this? Am I clear with this, people? Quick. In the chats. Yeah? Perfect. Let's see a few more different types of questions which can be asked from titration part. Well, it's a similar question. This is a similar question. What volume of 0.2 molar K2Cr2O7 is required to oxidize 50 ml of 0.3 molar sodium oxalate in acidic medium? As per this particular question, your K2Cr2O7 is reacting with what? Your K2Cr2O7 is reacting with sodium oxalate, Na2CO2O4. In which medium? Acidic medium. So these two are reacting now. Calling this as 1, calling this as 2. Molarity of K2Cr2O7 is given to me. Volume of K2Cr2O7 is to be calculated. Molarity of sodium oxalate is given to me as 0.3 and its volume is given to me as 50 ml. Well, first thing, do we remember their N factors? N factor of K2Cr2O7 in acidic medium is 6. N factor of K2Cr2O7 in acidic medium is 6 because K2Cr2O7 gets converted into Cr tripositive. Plus 6 to plus 3, change is 3. 3 is the change for 1, we have 2, right? It's 6. Similarly, N factor of sodium oxalate, right? N factor of sodium oxalate is 2. So molarity multiplied by N factor, that gives me normality. So normality of 1 will be 1.2. Normality of 2 will be this multiplied by this. So 0.6. Now we use the equivalent concept. Equivalent concept directly is going to tell you that milliequivalence of 1 reacted should be equal to milliequivalence of 2 reacted. Milliequivalence of 1 reacted should be equal to what? Milliequivalence of 2 reacted. Milliequivalence of 1 will be nothing but normality of 1 multiplied by volume of 1 in ml. This is going to be normality of 2 multiplied by volume of 2 in ml. Now, normality of 1 is 1.2. Volume of 1 is to be calculated. Normality of 2 is 0.6. Volume of 2 is 50. So V1 comes out to be equal 25 ml. If I ask you what is the meaning of this 25 ml, it means that 25 ml of 0.2 molar K2Cr2O7 is required to react with 50 ml of 0.3 molar sodium oxalate in acidic medium. Am I clear? Am I clear, people? Perfect. Now, let's see what kind of different questions can be asked from the titration part. See, guys, look at this question. How many moles of KMnO4? How many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate in acidic medium? Calling this as number 1, calling this as number 2. Do you remember the N factor of KMnO4 first of all in acidic medium? 5. N factor of potassium oxalate in acidic medium is 2. Right? Now, how many moles of KMnO4? So moles of KMnO4 are to be calculated. Are required to oxidize. How many moles of potassium oxalate? 1 mole of potassium oxalate. Right? This is the data. How many moles of KMnO4 are required to react with 1 mole of potassium oxalate in acidic medium? Now again use the equivalent concept. So gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted, or milli equivalence of 1 reacted has to be equal to milli equivalence of 2 reacted. Now, in which format you'll write the statement? Are you going to write the statement in terms of gram equivalence or in terms of milli equivalence? Since we are given with the data for moles, right? So I'll be writing the statement in terms of gram equivalence. I'll write gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted. And how many ways did we have? How many formulas did we have to calculate gram equivalence? 3 formulas. One was in terms of mass, one was in terms of moles, one was in terms of normality volume, right? Correct? So my dear students, instead of gram equivalence of 1, I'll write moles of 1 multiplied by n factor 1. This is going to be moles of 2 multiplied by n factor 2. Moles of 1 I need to calculate. N factor 1 is 5. Moles of 2 is 1. N factor 2 is 2. So N1 value will just come out to be 0.4. So I would say 0.4 moles of KMnO4 are required to react with 1 mole of potassium oxalate in acidic medium. Now, it's not necessary they'll ask you to calculate the moles of KMnO4. They can ask you to calculate the mass of KMnO4. And if they ask you to calculate mass of KMnO4, how do you convert moles into mass? Moles multiplied by molar mass of KMnO4. So it will be 0.4. Molar mass of KMnO4 is 158 grams per mole. This is going to be the answer in grams also. Anything can be asked. Anything can be asked. Yes, you can take milli equivalence as well here. But if you take milli equivalence, then you'll have to write millimoles of 1 into n factor of 1, millimoles of 2 into n factor of 2. From that equation, you'll be calculating millimoles of 1. And once you get millimoles of 1, then millimoles divided by 1000 gives you moles. Anything is fine. Anything, everything is fine here. Okay. One more question of the same format. I believe this is something which you can easily solve. This is something which you can easily solve. Right? Can you solve this on your own? Can you solve this question on your own? Quickly. What do you think is the answer of this question? Quickly, give it a try. Give it a try. It's a similar question. It is a similar question, people. It is a similar question. Tell me the answer. Don't write yes or no. Tell me the answer of the question. I don't need yes, no. I need the answer, exact answer. Solve it first. I'll be waiting for 1 minute. Give it a try quick. Yeah. Done? 3.33, huh? Let's exactly see what is going to be the answer of this question. As far as the question is concerned, K2Cr2O7 now is reacting with what? It is reacting with Cu2S. Calling this as 1, calling this as 2. Simple. What about N factor of K2Cr2O7 in acidic medium? 6. N factor of Cu2S in acidic medium? It is 8. How many moles of K2Cr2O7? So this to be calculated, right? Moles of Cu2S are given to us 8.5. So simple. Gram equivalence of 1 reacted should be equal to gram equivalence of 2 reacted. Gram equivalence of 1 will be moles of 1 multiplied by N factor 1 is equal to moles of 2 multiplied by N factor 2. Simple. Moles of 1 we need to calculate. N factor 1 is 6. Moles of 2 is 2.5. N factor 2 is 8. So from here, you can calculate the value and it will approximately come out to be 3.33. So 3.33 moles of K2Cr2O7 are required to react with 2.5 moles of Cu2S in which medium? In acidic medium, right? Am I clear? Am I clear, people? Yeah? Done? Look at this one. Look at this one, guys. Look at this particular question. The question is 6 moles of An positive. 6 moles of An positive requires 2 moles of Cr2O7 dinegative. Require 2 moles of Cr2O7 dinegative. For the oxidation of An positive into what? For the oxidation of An positive into AO3 negative. In which medium? Acidic medium. And you know, in acidic medium, Cr2O7 dinegative gets converted into Cr tripositive. The value of N will be, we have to calculate this N value, the charge on A. See, guys. First of all, 6 moles of An positive are reacting with 2 moles of Cr2O7 dinegative. If I call this as number 1, if I call this as number 2. So first of all, what is the N factor of An positive? See, plus N to plus 5. Plus N to plus 5. Change in the oxidation state. Final minus initial. Right? And here we have got 1 atom only. So this is the N factor. Similarly, N factor of Cr2O7 dinegative. Plus 6 to plus 3. Plus 6 to plus 3. Change is 3. 3 is the change for 1 atom. I have 2. So 3 2s are 6. I'm calling this as N1. I'm calling this as N2. Now we use the equivalent concept. Equivalent concept says that gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted. Gram equivalence of 1 is going to be number of moles of 1 multiplied by N factor of 1. Gram equivalence of 2 is going to be number of moles of 2 multiplied by N factor of 2. Number of moles of 1 here are 6. N factor 1 will be 5 minus N. Number of moles of 2 is 6. N factor 2 is 2. 6, 6 cancel. So N value directly comes out to be 3. So N is 3. That means the charge present on A over here is plus 3. This is something I was supposed to check. That's all. This is something I was supposed to check. That's it. Yeah? I hope you can solve these sort of questions easily from now on. I hope you can solve these sort of questions easily from now on. Now, there is one more type of question that can be asked. Look at this one. Since recently we have discussed the percentage purity, right? And this question is based on percentage purity. First of all, if you ask me, if I ask you, how do we calculate percentage purity of a compound in a sample? Do you remember? Percentage purity of a compound in a sample. How do we calculate it? How do we calculate it? I gave its formula in the mole concept. It used to be equal to mass of pure compound in grams divided by the mass of the impure sample in grams multiplied by 100. This is how you used to calculate percentage purity of a compound in a sample, right? This is how we used to calculate the percentage purity of a compound in a sample. So people, as far as this particular question is concerned, 2.5 grams sample of more salt. So we have got a sample of more salt. Sample of more salt. So that means there is a container that contains more salt plus some impurities, right? What is the mass of the entire sample? What is the mass of impure sample of more salt? It is given to me as 2.5 grams. This is the mass of impure sample of more salt. Now, as per the question, in this more salt, you are adding KMnO4. You are adding KMnO4, right? You are adding KMnO4, whose volume is this much, normality is this much. In acidic medium. What is the percentage purity of more salt in the sample? See guys, it's simple. The KMnO4 which you are adding, whose normality you are keeping as 1 by 10, whose volume you are keeping as 50 ml, right? Now, the KMnO4 which you are adding, that entire KMnO4 is going to react with pure more salt only. It is not going to react with impurity. The KMnO4 which you are adding, it's going to react with pure KMnO4 only. Perfect? Pure KMnO4 only. Right? So, what I can do over here? Since KMnO4 is completely reacting with more salt, so I can equate the equivalents of more salt and KMnO4. Since volume is in ml, so I can say milli equivalence of more salt has to be equal to the milli equivalence of what? Milli equivalence of KMnO4. Correct? Their milli equivalence will be equal. Now, milli equivalence of more salt will be mass of more salt divided by equivalent mass of more salt multiplied by 1000 is equal. Milli equivalence of KMnO4 will be normality of KMnO4 multiplied by volume of KMnO4 in ml. Now, mass of more salt I'll be calculating from here, divided by equivalent of mass of more salt means molar mass of more salt divided by n factor of more salt multiplied by 10 raised to power 3, sorry. Normality is 1 by 10. Volume is given to me as 50 ml. So from this particular equation, you can calculate the mass of more salt. You can calculate the mass of more salt. So from here, this is going to give you that mass of more salt which has reacted with KMnO4. And with KMnO4, only pure mass of more salt would have reacted, right? So if I ask you to calculate percentage purity of more salt in the sample, it is going to be equal mass of pure more salt, which we have calculated from here, divided by mass of the whole sample. The mass of the entire sample is 2.5 grams multiplied by 100. From here, you are going to get the percentage purity of more salt in the sample. Am I clear with this question as well? Am I clear with this particular question as well, people? Quick in the chats. One more type of question that can be asked. What is that? See. The question is calculate the moles of KMnO4 required to oxidize a mixture containing 1 mole each of this and this in acidic medium. So guys, imagine this is the container, and in this particular container we have got a mixture containing FeSO4, number 1. Number 2, we have got FeC2O4. Number 3, we have got Fe2SO4 whole thrice. We have got 1 mole of this in the container. We have got 1 mole of this in the container. We have got 1 mole of this in the container, right? Do you remember their n factors though? N factor of FeSO4 is 1. N factor of ferrous oxalate is 3, right? Fe2SO4. Is it going to react with KMnO4? I've told you already when I started the titration, it's not going to react with KMnO4. Yeah, it's not going to react with KMnO4. So I've got nothing to do with this. So the KMnO4 which you are adding, I'll say some part of KMnO4 will be reacting with this and some part of KMnO4 will be reacting with this. KMnO4 is not going to react with this one. So we have to calculate moles of KMnO4, and n factor of KMnO4 we already know in acidic medium is nothing but 5. So I'll be using the statement in terms of gram equivalence. I'll say gram equivalence of FeSO4, that is N1 multiplied by n factor 1, plus gram equivalence of this one, it is N2 multiplied by n factor 2, has to be equal to gram equivalence of KMnO4, which is N4 multiplied by n factor 4, right? So N1 is 1, n factor 1 is 1, plus N2 is 1, and this is 3. N4 we have to calculate, and this is 5. So 3 plus 1, 4. 4 by 5 is 0.8. So N4 value comes out to be 0.8. What was this N4? These were the moles of KMnO4. So I would say 0.8 moles of KMnO4 are required to react with this mixture containing 1 mole each. Am I clear? Am I clear, people? So I believe you can solve this sort of a question on your own from now onwards. This was based on case 2 of titration, right? When you have got a mixture containing 2-3 substances, then you are adding something. First of all, you'll be checking that something which you are adding, is that reacting with all or not? Yeah? Correct, people? Is it clear? Is it clear? Let me know once in the chats, quick. Let me know once in the chats, quick. Look at one more question then. Look at one more question which can be asked from the titration part. The question is 0.4 grams of a mixture. 0.4 grams of a mixture containing sodium oxalate, and potassium oxalate. We have got a mixture whose mass is 0.4 grams. Mixture is containing 0.4 grams of, we have got 0.4 grams of this mixture in the container. Requires 50 ml of K2Cr2O7 in acidic medium for the complete reaction. Calculate the mass of sodium oxalate in the container. Dear students, one very simple thing. Imagine that there are X grams of sodium oxalate in the container. Therefore, mass of potassium oxalate will be 0.4 minus X grams. Right? Okay? As simple as that. So the mass of sodium oxalate in the container is X, and therefore, I would say the mass of potassium oxalate in the container will be 0.4 minus X grams. Right? Now, in this particular container, as per the question, what are we adding? We are adding K2Cr2O7. Right? Molarity of K2Cr2O7 here, which we are adding, is 1/60, and its volume is how much? Its volume is 50 ml. Perfect. Now, first of all, since K2Cr2O7 in acidic medium, its N factor is 6, and molarity multiplied by N factor gives you its normality. So 1/60 multiplied by 6 will be nothing but 1/10. So normality of K2Cr2O7 is 1/10. Okay. So my dear students, this K2Cr2O7 which you are adding, it is going to convert oxalate into carbon dioxide, this oxalate into carbon dioxide as well. So my point here is the K2Cr2O7 which you are adding, some part of K2Cr2O7 is going to react with this one, and some part of K2Cr2O7 is going to react with this one. Okay. And we know their N factors as well. Its N factor is 2, and N factor of potassium oxalate is also 2. Since volume is given in ml, so I'll use the statement in terms of milliequivalence. I'll say milliequivalence of sodium oxalate reacted plus milliequivalence of potassium oxalate reacted has to be equal to milliequivalence of K2Cr2O7 reacted. Right? Because K2Cr2O7 is sending this oxalate into carbon dioxide, this oxalate into carbon dioxide as well. So your K2Cr2O7 is reacting with this one as well as this one. So one statement I wrote in terms of milliequivalence. Why in terms of milliequivalence? Because the volume is given in ml here. Volume is given in ml here. If the volume was in liter, then I should have written the statement in terms of gram equivalence. Right? Now, milliequivalence of sodium oxalate will be equal to mass of sodium oxalate in the container divided by equivalent mass of sodium oxalate will be molar mass of sodium oxalate divided by N factor of sodium oxalate multiplied by 10 raised power 3. This gives me the milliequivalence of sodium oxalate in the container plus milliequivalence of potassium oxalate will be equal to mass of potassium oxalate divided by equivalent mass of potassium oxalate, that will be molar mass of potassium oxalate divided by N factor multiplied by 10 raised power 3. Because I'm calculating milliequivalence, right? Is equal. Milliequivalence of Na2Cr2, K2Cr2O7 will be normality of K2Cr2O7, which is how much? 0.1, 1/10 multiplied by volume of K2Cr2O7 in ml, that is 50. Right? So if you see, we have got one equation that just contains one unknown, that's X. Just cross multiple things and get the value of X over here after doing the calculation. And if you got the X, that means you got the mass of sodium oxalate in the container. And once you get X, 0.4 minus X, that's going to give you the mass of potassium oxalate in the container. Right? The session PDF I'll be sharing in my Telegram. right? Wassim Bhat Chemistry Official. You can check it out afterwards. Now, guys, I hope this sort of a question you can easily solve from now on. Even there is one more question of the same format. There is one more question of the same format. You can check it out. 5.5 grams of a mixture of this and this requires 5.4 ml of 0.1 normal KMnO4 for complete oxidation. Calculate the moles of hydrated ferric oxalate, ferric sulfate. Ferric sulfate means this one in the mixture. So basically you have got a mixture containing ferrous sulfate and ferric sulfate. And you are adding KMnO4 into that. Just tell me one thing. The KMnO4 which we are adding, is that going to react with both or just one? I just need that answer. Rest, I believe you can solve it. I just need that answer. The KMnO4 you are adding in the mixture, is that going to react with both the substances or just one? Let me know in the charts. Is that going to react with both or just one? Quickly. Quickly in the charts. Both of them or just one? Okay, you are saying one. Now tell me which one? Which one? First one or second one? First one or second one? It is just going to react with ferrous sulfate, right? Because if you remember, this is ferrous plus 2 and KMnO4 is going to send Fe di positive into tri positive. Here iron is already in plus 3. Perfect, it's plus 3. So it's not going to react with plus 3. And sulfur already in plus 6. Don't you remember I told you in the beginning itself? Ferric sulfate, KMnO4, K2Cr2O7 is not going to react with ferric sulfate in acidic medium. Because here iron is in plus 3 and sulfur is already in maximum. So KMnO4 is not going to react with this one. So it will only react with what? This particular substance. So just equate their milli equivalence and get whatever things you are supposed to get. This is something which I'm keeping as the homework. This is something which I'm keeping as the homework, right? Now guys, there are few more questions which can be asked from the redox titration. There are few more questions basically which can be asked based on equivalent concept. So, take a note of one simple statement which will solve all those questions which I'm talking about. First of all, imagine that I'm writing a thing over here. Equivalent mass of the compound AXBY. Equivalent mass of the compound AXBY, right? See, AXBY, it contains two elements, A and B. Now, equivalent mass of this compound is always equal to equivalent mass of A plus equivalent mass of B. So, equivalent concept says that in a compound, the equivalent mass of the compound is always the sum of equivalent masses of its elements, right? So, equivalent mass of AXBY will be nothing but equivalent mass of A plus equivalent mass of B. For example, if I write equivalent mass of metal oxide, equivalent mass of metal oxide will be nothing but equivalent mass of metal plus equivalent mass of oxygen. And you know, equivalent mass of oxygen is nothing but 8 as per the definition. Let's say sometimes if I write equivalent mass of metal chloride, it will be always equal to equivalent mass of metal plus equivalent mass of chlorine, which will be 35.5. Let's say sometimes if I write equivalent mass of metal sulfate, it will be always equal to equivalent mass of metal plus equivalent mass of sulfate ion. And what will be the equivalent mass of sulfate ion? It will be molar mass of sulfate, which is 96, divided by n factor of sulfate. What is the n factor of SO4 dinegative? N factor of an ion is charged on it, right? So 96 divided by 2 will be 48. Similarly, if I sometimes write equivalent mass of metal nitrate, if I sometimes write equivalent mass of metal nitrate, it will be nothing but equivalent mass of metal plus equivalent mass of NO3 negative. What is the equivalent mass of NO3 negative? Molar mass of NO3, that is 62 divided by n factor of NO3 negative. It's ion. For the ion, n factor is the charge on it. So charge on it was 1. So its n factor is 1. So it's Em plus 62. Right? These are the things which we can easily write. Why am I telling you all this stuff? Because there are some types of the questions which can be asked here too. For example, a basic question. 1 gram of metal oxide gives 0.2 grams of metal. 1 gram of metal oxide, 1 gram of metal oxide gives 0.2 grams of metal. Calculate the equivalent mass of metal. Okay? 1 gram of metal oxide gives 0.2 grams of metal. Again, use the equivalent concept only. Equivalent concept says that gram equivalence of this reacted has to be equal to gram equivalence of this. Simple. So you will say gram equivalence of metal oxide reacted has to be equal to gram equivalence of metal formed. So it will be gram equivalence of metal oxide will be equal to mass of metal oxide divided by equivalent mass of metal oxide is equal. Gram equivalence of metal will be mass of metal divided by equivalent mass of metal. Now mass of metal oxide is 1 gram divided by equivalent mass of metal oxide will be equal to equivalent mass of metal plus equivalent mass of oxygen, that's 8, is equal. Mass of metal is nothing but 0.2 grams. Equivalent mass of metal, I'm writing as such. Now, do you see one equation? Just cross multiple and get the equivalent mass of metal from here, which is something I was supposed to calculate. Right? A simple and basic question. Aaj live class chal rahi hai abhi. I hope this sort of a question is clear to you. Just equate their gram equivalence and you're done. For example, one more simple question. 3 grams of metal chloride. So we have got 3 grams of metal chloride. 3 grams of metal chloride gives 2 grams of metal. Calculate the equivalent mass of the metal. You should be able to solve this one as well. Calculate the equivalent mass of the metal. So as per the question, gram equivalence of metal chloride reacted has to be equal to gram equivalence of metal. Right? Just equating their gram equivalence or mill equivalence, right? So I would say gram equivalence of metal chloride has to be equal to what? It has to be equal to gram equivalence of metal. Now, gram equivalence of metal chloride will be nothing but mass of metal chloride divided by equivalent mass of metal chloride. This will be equal. Gram equivalence of metal will be mass of metal divided by equivalent mass of metal. So make an equation from here. Mass of metal chloride is equal to 3 divided by equivalent mass of metal chloride will be equivalent mass of metal plus 35.5 is equal to mass of metal is 2 divided by equivalent mass of metal. Now cross multiple and get the equivalent mass of metal from here. Right? So what am I exactly doing? I'm just replacing this equivalent mass of metal chloride with equivalent mass of metal plus 35.5. Right? Something which I already gave you. Right? The list of the things I gave you already. Equivalent mass of metal chloride is equal to equivalent mass of metal plus 35.5. All these things I already gave you. Okay. Look at this one. 3 grams of metal oxide is completely converted to 5 grams of its chloride. So as per the question, metal oxide is getting converted to metal chloride. Metal oxide is getting converted into metal chloride as per the question. 3 grams of metal oxide is getting converted into 5 grams of its chloride. So just equate their gram equivalence. I can say gram equivalence of metal oxide has to be equal to what? Gram equivalence of metal chloride. Okay. So gram equivalence of metal oxide will be equal to mass of metal oxide divided by equivalent mass of metal oxide is equal to mass of metal chloride divided by equivalent mass of metal chloride. Now make an equation. How you will be making the equation here? It's a very simple job now. Mass of metal oxide, how much? 3 grams. Divided by equivalent mass of metal oxide will be equivalent mass of metal plus equivalent mass of oxygen is equal. Mass of metal chloride is 5 grams. Divided by equivalent mass of metal chloride will be equivalent mass of metal plus equivalent mass of chlorine, 35.5. Across multiple things and get the equivalent mass of metal from here, which you are supposed to calculate. Done? Done, people? Just tell me, can you solve this sort of equation on your own? Metal nitrate is getting converted into metal sulfate. You are supposed to calculate equivalent mass of metal. Can you solve this one on your own? Say yes or no in the chats. If yes, then I can give this question as the homework. If yes. If yes, then I can give this question as the homework. Quickly. Can this be done? I want everyone to say it. Yeah? What do you have to do? Just equate the gram equivalence of these two substances. That's it. Okay, so this question I'm giving you as the homework again. Now, my dear students, in the acid-base titration, we again use the similar concept. In acid-base titration. What kind of concept basically? Imagine you have got a strong acid, for example, and it is going to neutralize strong base. And what it's going to form? It's going to form salt and water. Acid plus base forms salt and water. Correct? So, law of equivalence says that at the end point of the reaction, gram equivalence of acid reacted has to be equal to the gram equivalence of base reacted. Simple. Or you can say milli equivalence of acid reacted has to be equal to milli equivalence of base reacted. That's all. That's all. That's all, people. You just, when it comes to your acid-base titration, right? For acid and base, you just have to equate their equivalence. That's it. And how do we calculate gram equivalence? How many formulas are there to calculate gram equivalence? 3 formulas. Mass, moles, normality. How do we calculate milli equivalence? 3 formulas. Mass, millimoles, normality into volume in ml. Correct? So, let me show you some basic questions so that you'll understand what kind of questions can be asked. See, guys. Calculate the volume of one normal H3PO4. Calculate the volume of one normal H3PO4 required to react with calcium hydroxide. Do you see the question is based on acid and base titration? So this is acid and it's going to get neutralized by this base over here. Okay? So calling this as 1, calling this as 2. Normality of this acid is given to me as per the question 1. Volume of the acid I need. Normality of the base is given to me as 2 and volume of this base is given to me as 20. So since it is a case of acid-base neutralization, so I can say, and volume is already given in ml, so I can say milli equivalence of acid reacted is equal to milli equivalence of base. So N1 V1 in ml has to be equal to N2 multiplied by V2 in ml. N1 is 1 into V1 is equal to N2 is 2 multiplied by V2. So isn't it simple? So can I say 40 ml of one normal H3PO4 is required to completely neutralize 20 ml of two normal calcium hydroxide in acidic, not in acidic medium, it is acid-base neutralization now. Yeah? Simple. Just equate the gram equivalence or milli equivalence of acid and base. You are done. You are sorted. Let's try to solve one more. Calculate the volume of one normal H2SO4. One normal H2SO4. We have to calculate its volume. Required to react with. required to react with 20 ml of 1 molar AlOH whole thrice. Okay. So since acid and base, again, they are going to react. Okay. So volume is in ml. So we'll use the concept in terms of milliequivalence because volume is in ml. So milliequivalence of acid reacted has to be equal to milliequivalence of base. Milliequivalence of acid is going to be normality of 1 multiplied by volume of 1 in ml. Similarly, milliequivalence of base is going to be normality of 2 multiplied by volume of 2 in ml. Now, normality of 1 is 1. Volume of V1 is to be calculated. N2 will be, what is the N factor of AlOH whole thrice? N factor of this will be 3 because it's going to donate 3 H positives, 3 OH negatives, right? So this multiplied by this gives me its N factor. So, sorry, not N factor, it gives me its normality. Normality of 2 will be 3 only. So 3 multiplied by V2 is 20. So from this particular equation, I got to know V1 is nothing but 60 ml. So I would say 60 ml of 1 normal H2SO4 is required to react with 20 ml of 1 molar aluminum hydroxide over here. This is something I was supposed to calculate. Itna late, is this the live class going on? Yes. There are always night classes happening on this channel. Look at this question. 0.45 grams of an acid whose molar mass is given was exactly neutralized by 20 ml of 0.5 normal NaOH. So again, acid-base reaction. So what do you have to do? What do we have to do? Volume is in ml. Again, you will write milliequivalence of acid reacted has to be equal to what? Milliequivalence of base. Right? Now, milliequivalence of acid. I'm given with mass of acid. So instead of milliequivalence of acid, I'll write mass of acid divided by equivalent mass of acid multiplied by 1000 is equal. Milliequivalence of base, its normality and volume is given. So normality of base multiplied by volume of base in ml. Now, mass of acid is given to me as 0.45. Equivalent mass of acid I'll calculate from here. Right? Multiplied by 1000 is equal. Normality of base as per the equation is 0.5 and volume of the base is 20 ml. So from this particular equation, can't we calculate equivalent mass of acid? Yes. From this particular equation, can't we calculate equivalent mass of the acid? Yes, we can easily calculate equivalent mass of the acid. Once we get equivalent mass of acid from this equation, right? From this particular equation, equivalent mass is nothing but molar mass of the acid divided by N factor of acid. And N factor of acid is basis T of the acid. N factor of acid is basis T of the acid, right? It is basically what I call as equivalent mass of the acid. So this term I would have calculated. Molar mass of the acid is given to me as per the question. From this particular equation, you can calculate easily the basis T of the acid. Yeah? You can easily calculate basis T of the acid. Is it clear? Will you be able to solve this sort of equation on your own from now onwards easily? Tell me in the chats. Tell me in the chats. So from this particular stuff, you got the equivalent mass of acid, and equivalent mass of acid, since you got, so it's molar mass by basis T. Molar mass we know, equivalent mass of acid we know. From here we can calculate basis T of the acid. Okay? Have a look on this question. Have a look on this question. How many milliliters of 0.1 molar HCl are required to react completely with 1 gram mixture of sodium carbonate and sodium bicarbonate containing equimolar amounts of both? See guys, I think this is the question which is given in NCERT. Yes, I've seen this sort of a question in NCERT as well, long time back. Anyways, have a look. As far as the question is concerned, we have got Na2CO3 and sodium bicarbonate in the container. Perfect. Sodium bicarbonate in the container. Mass of this entire mixture as per the question is 1 gram. Mass of this entire mixture is equal to 1 gram. Well, first of all, Na2CO3, its N factor has to be 2, and NaHCO3, its N factor has to be 1. Because this is This is going to be what? Take the LCM of cation and anion, charge on cation and anion. So 2 and 1. LCM is going to be 2. Na positive, HCO3 negative. 1 and 1 LCM is going to be 1. I hope you can do that. I hope you know what is happening basically. Na2CO3. It is basically Na positive, CO3 di negative. So 2, 1 LCM is going to be 2. Right? N factor of salt. LCM of charge on cation and anion. So 2, 1 LCM is 2. Here I would say NaHCO3. It is basically Na positive, HCO3 negative. So 1, 1 LCM is 1. So you got the N factors of these Na2CO3 and sodium bicarbonate, which is given to me as per the container. Now the mass of the mixture as per the question is 1 gram. Let's assume out of 1 gram, there are X grams of sodium bicarbonate in the container. And similarly, I would say 1 minus X grams, this is going to be the mass of bicarbonate in the container. Perfect. Now, as per the question, if I divide this X grams with the molar mass of Na2CO3, I'll be getting moles. So these are the moles of carbonate in the container. Similarly, 1 minus X divided by its molar mass is 84. So I got the moles of sodium bicarbonate in the container. Right? Right, people? Is it clear? Is it clear? So I would say in this particular container, we have got these many moles of carbonate and these many moles of bicarbonate present in the container. As per the question, they are mentioning that the mixture is equimolar. That means moles of carbonate and moles of bicarbonate in the container, they are equal. And when you equate this particular term, X divided by 106, as well as this particular term, can we get the value of X from here? Can we get the value of X from here? And X value, I'll check it out from the solution itself. What is the value of X which we get from here? X value is equal to 0.56. X is the mass of sodium carbonate. Okay, 0.56. So X value after solving is equal to 0.56 grams. So basically, I got the mass of sodium carbonate in the container. Therefore, bicarbonate is going to be 1 minus X, which will be 0.44 grams. So first of all, I got the mass of both in the container. Now, as per the question, we are adding HCl into it. The HCl which we are adding, its molarity is 0.1. If its molarity is 0.1, that means its normality will be 0.1 also, because N factor of HCl is 1. Right? Let's say volume of HCl which we are adding is V, which we need to calculate. Now use the equivalent concept. Since the HCl which you are adding here in the container, it's going to react with this one as well as this one. So you'll be using the concept here like this. Milli equivalence of sodium carbonate in the container reacted plus milli equivalence of sodium bicarbonate present in the container, right, is equal to milli equivalence of HCl reacted. Now, milli equivalence of sodium carbonate in the container will be equal to mass of carbonate, which is 0.56, divided by equivalent mass of carbonate will be molar mass of carbonate divided by N factor of carbonate multiplied by 10 raised power 3 plus milli equivalence of sodium bicarbonate will be equal to mass of bicarbonate, which is 0.44 grams, divided by equivalent mass of bicarbonate will be molar mass of bicarbonate divided by N factor multiplied by 10 raised power 3 is equal to milli equivalence of HCl will be normality of HCl, which is 0.1 multiplied by volume of HCl in ml. So do you see this particular equation? In this particular equation, there is only one unknown, that is V. So from here, you can calculate volume of HCl in ml, which I was supposed to calculate. Got it? And when you solve this, people, let me show you the final answer. Its answer will come out to be 158 ml. This is something which we were supposed to get. Yeah? Perfect, guys. Is it clear? Is it clear? Is it clear? Did you understand how I solved this particular question? First of all, I used one point over here. In the question they asked, they said that the mixture is equimolar, right? That means the moles of these two components are equal. By means of which I got the mass of carbonate and bicarbonate in the container. Since I got the mass of bicarbonate and carbonate in the container, right? After that, I used the equivalent concept. And the equivalent concept says milliequivalence of this reacted plus milliequivalence of this reacted has to be milliequivalence of this reacted, nothing else. Perfect. Now, guys, there is one topic left here in this chapter. What is that? That is volume strength of H2O2. This is not going to take more than like 15 minutes. So let's be alive for 15 minutes and let's get it done. Yeah? All right. Perfect, guys. Let's get to know about volume strength of H2O2. So, guys, here, first of all, I'm going to write a reaction. H2O2 aqueous. It gives H2O liquid plus half of O2 gas. This is one of the reaction which all of you would be already knowing. My dear students, if sometimes you would have seen the bottle in which hydrogen peroxide is kept. Okay. Mohammad Ashfaq, electrode potential will be discussed in the next chapter, basically, electrochemistry. Right? That's something we will do in electrochemistry. Electrode potential is given in NCERT in this chapter itself, redox only, but we study that in electrochemistry, and electrochemistry is our next chapter. Okay, don't worry about that. Don't worry about that. Okay, so what I was trying to tell you, if you see a bottle which contains hydrogen peroxide, the bottle in which hydrogen peroxide is kept, my dear students, in that bottle, a statement is written with a red colored line. A statement is written with red color, which is what you call as a labeling of H2O2. The bottle containing hydrogen peroxide. Maybe you can see it in the salons, right? Or in the labs. Perfect. On the bottle, there will be a statement written with a red color. And that statement will be in this format. Like this. V volume H2O2. V volume H2O2. This is going to be the format of the statement. For example, 10 volume H2O2, 20 volume H2O2, 5 volume H2O2. This is going to be the format of the statement. Now, what this statement exactly means? How do you decode this particular statement? My dear students, this V volume H2O2, it means that 1 volume H2O2 produces V volume O2 gas at STP. V volume O2 gas at STP. Now, instead of volume, you can take, volume you can take in liters, volume you can take in ml, the choice is all yours. So you can write a statement, 1 liter H2O2 is going to give us V liters of O2 gas at STP. Or you can write the same statement in terms of ml. You can say 1 ml H2O2 gives us V ml of O2 gas at STP. Let me make it a bit more clear. See, guys, for example, if you see a statement written like this, let's say I'm writing 20 volume H2O2. What does it mean? Let me first of all tell you, I can decode this statement in liters as well as I can decode this particular statement in milliliters. If I decode this statement in liters, I can say 1 liter H2O2 produces 20 liters of O2 gas at STP. if you want to decode this particular statement in milliliters, you can say 1 ml H2O2 gives 20 ml of O2 gas at STP. This is how you can decode this particular statement. Or sometimes if I write the statement like this, if I write 2 liters of 10 volume H2O2, let's say I'm writing a statement like this. 2 liters of 10 volume H2O2. First of all, let me try to decode this part. 10 volume H2O2. Let me decode it in liters. It means that 1 liter H2O2 gives 10 liters of O2 gas at STP. Now, if 1 liter H2O2 gives 10 liters of O2 gas, therefore, 2 liters of H2O2 are going to give us 10 to the 20 liters of O2 gas at STP. Perfect. I believe this is clear. Right, people? So, if you first of all have this sort of a statement, let's say you've got a statement like this: 20 ml of 2 volume H2O2. How can you decode this particular statement? It's again simple. Let's try to decode this part first of all in ml. Let's try to decode this part in ml. It means that 1 ml H2O2 gives us 2 ml of O2 gas at STP. But as per the statement, do we have 1 ml of H2O2 or 20 ml? We have got 20 ml. So I would say 20 ml H2O2 is going to give us 20 multiplied by 2. So I would say 40 ml of O2 gas at STP. At STP, right? Is this clear? Is this clear, people? Yeah? So I believe you can easily decode these sort of statements on your own. And one more thing, guys. One formula I'm giving you, which is going to be used at many of the places. There's a formula to calculate molarity of H2O2 aqueous solution. And molarity of H2O2 aqueous solution is always equal to volume strength of H2O2 aqueous solution, volume strength divided by 11.2. This is one direct result which you guys are going to use at STP condition. Whenever you are asked to calculate molarity of H2O2 aqueous solution, if you know the volume strength of H2O2, divide with 11.2, you'll be getting the molarity of H2O2. You'll be getting the molarity of H2O2. Or if you are sometimes asked to calculate normality of H2O2 aqueous, normality of H2O2 aqueous is going to be volume strength of H2O2, volume strength of H2O2 divided by 5.6. These are the two results with the help of which you can calculate either molarity of H2O2 aqueous solution or normality of H2O2 aqueous solution. Let me show you some questions so that it will be properly clear to you. Okay? Look at the first question, guys. Look at the first question. For a 16.8 volume H2O2 solution whose density is given, calculate molarity, weight by weight of solute, weight by volume of solute, mole fraction, ppm. So this question is directly linked with the mole concept. As per the question, we are given with the H2O2 solution whose volume strength of H2O2 is given to me as 16.8. Perfect. Density is given. So first thing, if volume strength is given, can't I calculate molarity of this particular solution? Molarity is going to be volume strength divided by 11.2. The value comes out to be 1.5. So the first part of the question is done. I calculated molarity. If you calculated molarity, do you remember in the mole concept, I gave you one result. Molarity is equal to 10 multiplied by density of solution multiplied by weight percentage of solute divided by molar mass of solute. Do you remember? Now molarity I calculated from here. Molar mass of solute, molar mass of H2O2, we know. Density of solution is given to me as per the question. So we can easily calculate weight by weight percentage of solute from here. Weight by weight percentage of solute can be easily calculated from here. Once you calculate weight by weight percentage of solute, if you remember, my dear students, I've given you one result. What was that? In the mole concept. Weight by volume percentage of solute is nothing but weight by weight percentage of solute multiplied by density of solution. Weight by weight percentage of solute you will calculate from here. Density of solution in the question. So from here, weight by volume you will get. Similarly, mole fraction, right? ppm, anything can be asked. We already know all the direct results, people. We already know all the direct results. Right? Let's see a different type of question. These are the formula-based ones. And if you have studied mole concept few days back with me, you should be in a position to solve all of this. Since I calculated molarity, from molarity, you can calculate molality also. Once you get molality, you can convert that into mole fraction also. Everything you can do. And this sort of a question, I think I've already discussed with all of you once. Anyways, have a look on this question. How many moles of water can be produced from 2 liters of 22.4 volume H2O2 aqueous solution? Now, I already gave you one reaction, H2O2 aqueous. What does it give? It gives H2O liquid plus half of O2 gas. The question says how many moles of water can be produced from what? From 2 liters of 22.4 volume H2O2. First of all, have a look properly. Volume strength of H2O2 is given, so I can calculate molarity of H2O2. Molarity of H2O2 solution is going to be volume strength divided by 11.2. So I would say the molarity of the solution here is 2. If molarity is 2, volume is 2 liters. Molarity multiplied by volume in liters, that gives me moles of solute. You must be remembering the mole concept. Moles of solute is equal to molarity multiplied by volume of solution in liters. Now you have got a solution, H2O2 aqueous solution. Solute here is H2O2, right? So number of moles of H2O2, number of moles of solute, I can say is equal to molarity multiplied by volume in liters. So 2 multiplied by 2 is 4. So technically we have got 4 moles of H2O2 here. Technically we have got 4 moles of H2O2. How did I calculate moles of H2O2? Let me quickly show this again to you so that it becomes properly clear to you. My dear students, if you think logically, we are given with H2O2 aqueous solution. So this is solute and this water is solvent. Well, volume strength of H2O2 is given. So I calculated molarity of this solution as 2. Volume of this solution is given to me as 2 liters as well. Molarity multiplied by volume in liters gives me moles of solute. Solute here is H2O2. So we are basically given with 4 moles of H2O2. Now understand, 1 mole H2O2 gives 1 mole water. If 1 mole H2O2 gives 1 more water, so 4 moles H2O2 are going to give us 4 moles of water. So you got to know that 4 moles of water are produced through the reaction. Right? 4 moles of water are produced through the reaction. Done. And guys, one last question. Yeah. Tell me its answer right now in the chats. Everybody. Give it a try. Tell me its answer right now in the chats. I want the correct answer of this question. Quickly. Done? Guys, it's simple. You're not supposed to solve this question though, because I've already shown you how to decode this particular statement. Just a second. Okay. You can solve this question with the help of decoding the statement. The statement is given to me as 200 ml of 15 volume H2O2. What would be the volume of O2 gas produced? Now, first of all, try to decode this 15 volume in terms of ml. I can say 1 ml H2O2 gives 15 ml O2 gas at STP. Therefore, 200 ml of H2O2 gives 15 multiplied by 200 means 3000 ml of O2 gas at STP. This is something which you are supposed to calculate. The volume of O2 gas produced from 200 ml of 15 volume H2O2. So I would say 300 ml of O2 is produced, or you can say 3 liters of O2 is produced at STP. Perfect. So with this, your redox is done and dusted. Next chapter is going to be electrochemistry, which will happen on coming Monday, 5 p.m. Right? Asani, what are you trying to say? Catalysts, they always speed up the rate of the reaction, right? A positive catalyst timing. Okay. So this particular chapter is done and dusted. So do you know in chemistry how many chapters are we done with? We are done with mole. We are done with chemical bonding. Today we are done with redox. HSP sir is done with isomerism, right? Alkanes, and one more chapter, D and F block elements. So technically 6 chapters we are done with in chemistry. Yeah. And guys, the PDF of this particular chapter I'll share in the Telegram. Okay, let me just save it in front of you, otherwise I'll forget it. PDF. So this is your redox. Redox PDF. Redox PDF already exists. Let me name it as Redox PDF new. Okay. Yeah, we are done with solution chapter as well. I forgot that. Yes, we are done with solution as well. I hope today's session was, damn clear to you. If you have any sort of difficulty in understanding anything, just recap the session again, wherever you face any sort of difficulty, right? Just drag the video back. It'll be a replay for you. And I'm pretty much sure you'll be able to do things properly, right? So do let me know in the comment section of this particular video, how did you like the session? And let me tell you, I have taught every single thing, whatever can be asked from this particular chapter, whether easy to difficult. I've taught every single thing here in detail. Okay. So next chapter is going to be electro. So I would want one thing in the comments, that is going to be redox done and dusted like never before. Yeah. And do let me know in the comment section in detail, right? Whatever you would want to tell me in the comments. So with this, I'm taking a leave. Take care. God bless you all and love you all. The session PDF I'll be sharing in the Telegram.